Why most Salesforce architects fail.
Most Salesforce architects fail not because they lack technical knowledge, but because they limit their thinking to tools and patterns that already exist. In 2026, top employers are looking for architects who can build solutions for problems that have not even been fully defined yet. This series is not about learning standard integration patterns. This is about mastering integration architecture at the level companies expect from lead and enterprise architects, problems involving AI governance, multi-cloud orchestration, future-proofing, performance stability, and strategic decision-making under pressure. Across this series, we'll go through real interview-style scenarios. They're not copied from books, not drawn from typical mock sessions, and not available in free online suggestive resources. These are architect-level simulations based on the next wave of Salesforce transformation. In each episode, I will give you a scenario exactly as it might be asked in an interview, and then break it down like I would in a live whiteboard session with a CTO or in a system design challenge.
The expectation.
Expect depth. Expect complexity. And expect to think like an architect who builds for tomorrow. Section 1, Legacy and Transformation Scenarios.
Objective.
Can you modernize, optimize, and mitigate risk while ensuring stability?
The reality of modern interviews.
Even though we're entering an AI-driven Salesforce era, architects are still failing interviews on legacy integration scenarios. Why? Because companies don't hire you only to build tomorrow's solutions, they hire you to ensure today's systems survive the transition. You may architect an AI-powered streaming integration, but what if the company's ERP still runs batch jobs from the 90s, using no APIs, and survives purely through nightly file transfers? This section covers scenarios that have not changed in over a decade, and still eliminate candidates in 2026 interviews. Let's start with the most underrated but high-risk scenario that real enterprises are still struggling with today: legacy ERP integration via nightly batch. This is typically asked as a modernization challenge in senior interviews to assess risk-based thinking, migration planning, and data reliability strategy.
A note on code syntax.
In this series, we use architectural pseudocode. While the syntax resembles Apex or Java, it is designed to demonstrate logic, data flow, and resilience patterns rather than compile-ready syntax. As architects, we focus on system behavior, allowing you to apply these logic patterns to Apex, Java, MuleSoft, or any enterprise integration layer. Let's begin. Scenario 1, Legacy ERP/DB2 integration via nightly batch ETL, no APIs available. This one still kills candidates, not due to complexity, but because interviews expose gaps in practical resilience and modernization strategy.
Scenario 1, Legacy ERP integration via nightly batch.
You join as a Salesforce architect in a company running mission-critical finance operations on a 25-year-old ERP. There are no APIs available. Data is transferred using nightly flat file batch via FTP. If integration fails even once, finance reporting is disrupted globally the next morning. What's your architecture? This is a real interview question for principal architects. Pause and think.
Context and challenge.
1. System, legacy ERP, DB2, no API, mainframe era. 2. Data transfer, nightly batch via ETL or SFTP. 3. Impact, incorrect or missed sync leads to revenue loss and audit failures. 4. No real-time capability on ERP side. 5. File-based transmission only. 6. Batch job failure must not stop business flow. 7. High risk of data drift between Salesforce and ERP. 8. Manual correction windows are limited.
The interview question.
How would you design a Salesforce integration with a legacy system that only supports nightly file-based batch? How do you ensure data consistency, performance, and future readiness without disrupting mission-critical operations?
Architectural strategy.
1. Use a stage, validate, process pattern. File received via SFTP into staging object or table. Perform validation and fault isolation before merge. 2. Map data through middleware like MuleSoft, Talend, or Informatica. Track changes using FIFO buffer for reconciliation. Use Delta logic, not full export, if possible. 3. Use Bulk API 2.0 for ingestion to ensure parallel and scalable processing. 4. Compare previous day snapshot to prevent data drift. 5. Store batch job status and transaction logs in Salesforce. 6. Trigger reconciliation alerts if records mismatch. 7. Set up progressive modernization path, leading to an API simulation layer for future migration. Here is the Apex implementation, staging validation and idempotent upsert logic. Disclaimer: always test code in a non-production environment. We strictly validate staging records before attempting to load them into the main account object. Any record missing critical fields is logged as an error immediately and skipped, preventing batch failures. We use the database.upsert method with the all or none parameter set to false. This is crucial for partial success. It allows valid records to save even if others fail. Every failure is written to a custom integration log object. This provides a clear audit trail for the finance team to review the next morning without needing to dig into system logs.
Strategic decision justification.
1. Staging, validation, and upsert prevents direct ingestion errors. 2. Using Bulk API improves time-bound batch performance. 3. Error isolation prevents total job failure. 4. Using external ID supports idempotency in absence of APIs. 5. Maintaining full sync logs critical for audit. 6. Never directly push file content into Salesforce objects. 7. Don't use real-time integration techniques not supported by legacy system. 8. Plan path to replace file-based integration with simulated API layer over time.
Failure modes and mitigation.
1. File corrupted, auto-retry with fallback file copy. 2. Partial ingestion, send alert and rerun only failed subset. 3. Data mismatch, generate drift report and compare with ERP snapshot. 4. FTP outage, store file in temporary middleware repository. 5. Large volume, split file greater than 500k rows and load via parallel bulk API jobs.
High-value interview answer.
I'd implement a staged batch-based integration, with pre-ingestion validation to prevent corrupted records from reaching Salesforce. I'd use Bulk API and external ID-based upserts for performance and idempotency. To manage data drift, I'd generate nightly reconciliation reports comparing ERP snapshots with Salesforce records. Finally, I'd position this architecture as an interim design, gradually transitioning towards API-based integrations by simulating APIs via middleware.
Architect-level innovation.
1. Introduce AI-powered anomaly detection in staging area to auto-flag suspicious updates. 2. Use predictive failure models based on historical batch success rates. 3. Store legacy sync metrics to justify modernization investment. 4. Allow batch overrides via emergency retry triggers in Salesforce. 5. Use API facade over ETL process for future migration readiness.
Your turn.
1. Have you faced a legacy integration like this before? Comment your approach along with section and scenario. I want to hear your war stories. 2. Like this video if you'd answer this differently after watching. 3. Next scenario, SOAP to REST migration with zero downtime. People underestimate it. Don't.
Scenario transition.
Now that we've covered how to work with systems that never supported APIs, let's look at the next common legacy challenge: systems that do have APIs, but are outdated, hard to scale, and impossible to evolve. This is one of the most widely seen migration projects in enterprises today, moving from SOAP to REST without causing downtime, data loss, or business disruption. Most candidates talk about replacing endpoints, that's not architecture. Let's build this right.
Scenario 2, SOAP to REST migration, zero downtime.
Your Salesforce org is integrated with an order management system using SOAP APIs. That system is now being modernized to REST microservices. But business operations cannot stop, orders continue 24/7. How do you migrate the integration without any downtime?
Context and challenge.
1. Current state, SOAP-based synchronous API integration used for order submission and status sync. 2. Migration goal, move to REST-based service while maintaining compatibility during transition. 3. Constraint, cannot modify Salesforce callouts immediately. 4. Constraint, must support old and new API versions concurrently. 5. Constraint, allow rollback in case of REST failure. 6. Constraint, ensure consistent data responses across versions.
The interview question.
Design a migration strategy from SOAP to REST for an enterprise-critical integration. Ensure continuous service availability and provide rollback capability. How would you architect this?
Architectural strategy.
1. Introduce API facade layer, version gateway. Expose a stable endpoint to Salesforce and route internally to SOAP, current, and REST, new. 2. Use parallel run with dark launch strategy. Send the same request to both SOAP and REST in shadow mode. Compare responses and track discrepancies. 3. Switch traffic gradually using percent-based routing. Start with 5%, scale up, and monitor failures. 4. Enable instant rollback. If the REST service fails, route back to SOAP immediately. 5. Use circuit breaker pattern to handle service outages. Here is the Apex implementation, API facade and circuit breaker logic. Disclaimer, always test code in a non-production environment. We fetch the active API version from a custom configuration setting. This allows us to switch between SOAP and REST instantly without deploying code changes. When the config is set to REST, we attempt the new callout first. This is where we can implement percentage-based routing or dark launching in a real scenario. This is the critical rollback mechanism. If the new REST service fails or times out, we immediately fall back to the legacy SOAP service, ensuring zero downtime for the business.
Trade-off and decision analysis.
1. API facade isolates Salesforce from backend changes. 2. Parallel shadow testing ensures REST stability before commit. 3. Gradual rollout minimizes risk. 4. Rollback minimizes business impact. 5. Avoid instant endpoint switching as it is too risky. 6. Avoid full cutover without testing as it is unacceptable for 24/7 ops.
Failure and risk mitigation.
1. REST fails, retry via SOAP automatically. 2. REST latency spikes, circuit breaker triggers fallback. 3. Schema mismatch, validate during dual call monitoring phase. 4. Multiple versions active, use message hashing to avoid duplicates. 5. Business exception, log and route internally for manual correction.
High-value interview answer.
I'd introduce an API facade layer to expose a single, abstracted endpoint to Salesforce. Initially, the facade routes calls to the SOAP service, while the REST service runs in dark launch mode for monitoring. Once the REST API passes performance and response validation, I'd gradually shift traffic using weighted routing. A circuit breaker protects against REST failures by automatically reverting traffic to SOAP without disruption. This allows zero downtime migration with rollback protection.
Architect-level enhancement.
1. Maintain API call logs across both protocols for audit. 2. Use AI to compare SOAP versus REST performance for decision validation. 3. Implement auto-switched rollback if error threshold exceeded. 4. After full migration, deprecate SOAP via time-based config flag.
Your turn.
1. Would you have cut over directly, or run both versions temporarily like this? Comment your approach along with section and scenario. 2. If this gave you a new way to think about API migration strategies, hit like. 3. Next scenario is one where microservices sound great, until they fail at enterprise scale.
Scenario transition.
In the previous scenario, we saw how to evolve APIs without breaking the integration contract. But what happens when the problem is not the API, but the architecture behind it? When enterprise applications grow beyond original design limits, integrations start failing under scale. And many architects jump to microservices as a solution. But in an interview, if you say, "We'll move to microservices," without explaining how you'll get there without breaking what's working today, you're out. Let's do this properly.
Scenario 3, monolith to microservices migration, scale overload and risk control.
Your company's core CRM integration logic runs through a monolithic middleware layer built 8 years ago. It handles millions of transactions per day, but performance is degrading. You've been asked to migrate to microservices, without risking business continuity. How do you architect this transformation?
Context and challenge.
1. Current state, monolithic integration layer handling many processes via a single point. 2. Current state, high latency under load with limited scalability. 3. Change requirement, transition to microservices architecture without impact to existing flows. 4. Change requirement, no downtime during incremental migration with rollback capability. 5. Constraint, enterprise using 24/7 interconnected systems. 6. Constraint, few services can be paused or replaced in one go.
The interview question.
You're redesigning an integration built on monolithic middleware that can't scale. How do you migrate to microservices architecture incrementally while ensuring high availability, rollback capability, and no disruption to Salesforce's operations?
Architectural strategy.
1. Use Strangler Fig pattern. Keep monolith active and gradually introduce microservices for specific functions. 2. Use an API gateway or integration facade for central control of request routing. 3. Apply dark launch or shadow mode. Send requests to both monolith and microservice to validate consistency. 4. Gradual traffic diversion. Start with low-risk use cases and expand to write operations. 5. Monitoring and circuit breaking. Real-time performance comparison and failover handling. Here is the Apex implementation, Strangler Fig router with dark launch and circuit breaker. Disclaimer, always test code in a non-production environment. This is the starting state. The router sends 100% of traffic to the legacy monolith, ensuring stability while we build the new system. This is the dark launch or shadow mode. We call both systems, but only return the monolith's response. Crucially, we highlight the comparison logic here. We validate the microservice accuracy in the background without risking the user experience. Finally, we switch to the microservice as primary. However, we wrap it in a try-catch block. Notice the catch block. If the new service throws any exception, we instantly fall back to the monolith, guaranteeing system uptime.
Strategic trade-offs.
1. Strangler pattern provides the lowest risk migration. 2. Dark launch allows safe validation before users see changes. 3. Hybrid mode supports gradual adoption. 4. Big bang migration carries high failure risk and is avoided. 5. Direct deployment is avoided as it cannot test against monolith output. 6. API gateway makes the system future-friendly for progressive refactoring.
Failure modes and risk mitigation.
1. Microservice latency, auto-route traffic to monolith. 2. Output mismatch, send alert and hold migration. 3. High error rates, rollback config change. 4. Scaled load, use horizontal auto-scaling on microservices. 5. Data inconsistency, implement temporary write-through sync.
High-level interview answer.
I'd apply the Strangler pattern by keeping the monolith active while gradually transitioning specific integration capabilities to microservices via a routing gateway. I'd initially run microservices in dark launch mode to compare responses, while traffic continues to the monolith. Once we confirm reliability and performance, I'd progressively increase microservice traffic using config-based routing. A circuit breaker ensures automatic failover to the monolith, guaranteeing zero disruption.
Architect-level enhancements.
1. Include service canary releases for segment testing. 2. Leverage Kafka for decoupled data transfer between systems. 3. Use AI to auto-tune routing thresholds based on performance. 4. Document migration readiness with metrics to justify cutover decision.
Your turn.
1. Would you trust microservices on day 1 or keep monolith as backup? Drop your migration philosophy below in comments with section and scenario. 2. Like this if you've seen a microservices implementation fail due to lack of risk management. 3. Next, what happens when integrations retry themselves into failure? Let's talk idempotency and poison queues.
Scenario transition.
So far we've migrated legacy systems without breaking them. But what happens when integration failures happen inside a modern system? Message queues like Kafka, RabbitMQ, or Salesforce's platform events are excellent at retrying failed deliveries, until they're not. If a retry keeps failing, your integration could accidentally create duplicate records or worse, spam downstream systems endlessly. This scenario tests your understanding of architectural resilience and operational risk.
Scenario 4, Message queue retries, no idempotency and poison queue risk.
Imagine a system keeps retrying a failed message, and instead of fixing the issue, it keeps updating the same Salesforce record 147 times. Who's at fault? The queue, the record logic, or the architect who didn't design idempotency?
Context and challenge.
1. System, middleware or event queue pushes messages into Salesforce. 2. Failure type, downstream update error like validation or timeout. 3. Core issue, no idempotency check leads to duplicate processing. 4. Challenge, retry happens endlessly creating a poison queue effect. 5. Challenge, duplicate API calls lead to multiple updates or insertions. 6. Challenge, risk of partial updates leads to data corruption. 7. Requirement, must allow retry but prevent data duplication.
The interview question.
How would you design a message retry mechanism so that integration failures can recover automatically without causing data duplication or endless retry loops?
Architectural strategy.
1. Introduce idempotency control. Generate a unique transaction ID for each message and store it in Salesforce to avoid reprocessing. 2. Apply retry with exponential backoff. First retry quickly, then subsequent retries slower, up to a limit. 3. Identify poison messages. If still failing after threshold, push to a dead letter queue or DL queue and alert the support team. 4. Allow safe reprocessing. Human or automated correction followed by controlled replay only after resolving the issue. Here is the Apex implementation, idempotency check with exponential backoff and DLQ logic. Disclaimer, always test code in a non-production environment. This is the most critical line. Before processing anything, we check if this specific transaction ID has already been handled. If it has, we skip it immediately, preventing duplicate records regardless of how many times the queue retries. Once business logic succeeds, we log the transaction ID as success. This locks the transaction so that any future replays of this event will be caught by the idempotency check. Here is the resilience logic. If we fail, we check the retry count. If we are under the limit, we requeue the event for a later attempt. If we exceed the limit, we stop the infinite loop and move the message to a dead letter queue for manual investigation.
Strategic decision analysis.
1. Idempotency token prevents duplicate creation. 2. Retry threshold prevents infinite loops. 3. Dead letter queue isolates unfixable issues. 4. Exponential retries optimize latency impact. 5. Blind retry is avoided as it is the worst solution. 6. Solution includes business SLA for resolution.
Failure handling.
1. Duplicate event processing, use unique transaction key. 2. Malformed payload, auto-fail to DLQ. 3. Processing timeouts, retry with exponential backoff. 4. Missing master data, skip and raise issue. 5. Continuous failure, circuit breaker activates.
High-value interview answer.
I'd build an idempotent event handler that checks if a message has already been processed, using a transaction identifier. I'd apply controlled retries with exponential backoff and a maximum retry cap. If the integration still fails, the message moves into a dead letter queue for human intervention. This supports resilience without harming downstream systems and ensures retries don't generate duplicates or performance issues.
Architect-level enhancements.
1. Add AI-based anomaly detection to spot repetitive failures. 2. Forecast fault patterns based on time or input type. 3. Use central dashboard to monitor integration retry pipeline. 4. Implement trigger guard during Salesforce maintenance windows.
Your turn.
1. Have you seen a retry that caused more damage than the failure itself? Share your experience below by mentioning section and scenario. 2. Like this if you'll never say, just retry again after watching. 3. Next scenario, COBOL and mainframe integration, solving proprietary system limitations like an architect.
Scenario transition.
When your integration involves an ERP or middleware, there's still some structure. But when you integrate with a proprietary mainframe system, especially one written in COBOL, things change completely. There's no REST. No SOAP. Sometimes no database access. Only proprietary file formats or terminal-based data retrieval. Here's the scenario: if your architecture can't work with this today, you're not enterprise ready.
Scenario 5, mainframe integration, COBOL and proprietary data engine.
Your company runs core billing and compliance logic on a 35-year-old mainframe system written in COBOL. There's no API, just nightly flat files or terminal screen scrapes. Leadership wants Salesforce to pull data from this system and push data back into it. You cannot touch the mainframe. How do you architect this?
Context and challenge.
1. Mainframe system, COBOL-based, tightly coupled business logic. 2. Limitations, no APIs, no modern DB connectors, often uses VSAM or flat file formats. 3. History, past outages caused major business impact, so risk aversion is high. 4. Requirement, Salesforce must ingest daily updates. 5. Requirement, Salesforce must trigger updates back to mainframe for certain transactions. 6. Constraint, cannot modify mainframe code. 7. Constraint, data extraction only via staged files, copybooks, or middleware. 8. Constraint, no real-time transactional support.
The interview question.
How would you design an integration with a COBOL-based mainframe system that does not support APIs, ensuring accuracy, traceability, and minimal risk, while building towards modernization?
Architectural strategy.
1. Use middleware layer as digital gateway. Connect with mainframe via data transform adapters and transform proprietary formats into normalized schemas. 2. Implement staged bulk sync approach. For inbound to Salesforce, use staging object and bulk API. For outbound, write transformation then pass through gateway. 3. Introduce transaction control layer. Use a change control table in middleware and add approval workflow for high-impact updates. 4. Future-proofing. Create virtual API facade over legacy logic to enable future system replacement without Salesforce changes. Here is Apex implementation, COBOL fixed-length payload transformation. Disclaimer: always test code in a non-production environment. Legacy mainframes often do not understand JSON or XML. They require fixed position strings. Here, we format the account ID to occupy exactly 10 characters, padding with spaces if necessary, to match the COBOL copybook definition. Every field must be precise. If the risk rating is 3 characters but the mainframe expects 5, the entire transaction will shift and fail. This apex logic ensures perfect alignment before the data ever leaves Salesforce. We append a specific termination marker. Legacy file parsers look for these specific flags to know when a record ends. In a real-world scenario, middleware like MuleSoft would likely handle this transformation, but understanding the concept is crucial for an architect.
Strategic trade-offs.
1. Middleware handles protocol and format translation. 2. Salesforce sync happens via structured APIs like bulk or REST. 3. Mainframe remains untouched, which is safest for operations. 4. Real-time interaction is impossible without major investment. 5. Long-term facade layer enables gradual replacement. 6. Never allow Salesforce to directly write into mainframe file systems.
Failure and risk mitigation.
1. Mainframe job failure, use sync status monitor. 2. Invalid data format, pre-validate before outbound. 3. Performance issues, window-based dispatch during nightly off-peak. 4. Incorrect update rules, require change approval step. 5. Lost files, auto-checksum verification before load.
High-value interview answer.
To integrate with a COBOL-based mainframe, I would implement a middleware-led orchestration approach. The middleware extracts and transforms data using legacy adapters and copybook mappings and sends structured files or messages into Salesforce via bulk or REST processing. For outbound, Salesforce generates changes only into middleware, never directly into the mainframe. That layer validates format, applies business logic, and queues updates for COBOL execution. This ensures minimal disruption to legacy systems while establishing a facade that supports future modernization efforts.
Architect-level enhancements.
1. Use file versioning and gold backup before ingestion. 2. Run test replay against mainframe offline database clone. 3. Introduce event simulation to evolve toward an API-based replacement. 4. Predict mainframe transaction cost using AI-based performance modeling.
Your turn.
1. Have you ever integrated with a system older than you? Drop how you handled it in the comments section along with section and scenario. 2. Like this if you now see mainframe integration differently. 3. Final scenario of this section, CSV via SFTP ingestion, sounds harmless until compliance fails.
Scenario transition.
If you think CSV ingestion is a junior-level integration task, think again. Almost every major enterprise has experienced a production incident due to CSV file load failures, resulting in data corruption or improper customer communication. And yet, this question appears in senior and lead architect interviews, not to test your knowledge of file handling, but your ability to design a safe, auditable ingestion pipeline. Let's dive into the most underestimated integration failure.
Scenario 6, CSV via SFTP ingestion, audit risk and harm minimization through staged processing.
Imagine a 5 megabyte CSV file is uploaded via SFTP nightly, but this time, someone accidentally swapped 2 columns. The next morning, 18,000 customer addresses were replaced with incorrect billing codes. Can your architecture prevent that? This is asked to see if you're thinking about harm prevention, not just data processing.
Context and challenge.
1. Data source, CSV via SFTP. 2. Use case, daily ingestion for customer updates or invoices. 3. Risk, manual file creation leads to human error. 4. Risk, no schema enforcement. 5. Risk, full ingestion without validation leads to mass corruption. 6. Risk, missing audit logging means no rollback is possible. 7. Risk, no data quarantine mechanism.
The interview question.
How would you design a CSV-based data ingestion integration from an SFTP source into Salesforce, ensuring data accuracy, full audit traceability, and protection against malformed file loads?
Architectural strategy.
1. Step 1. Receive CSV into staging area. Do not directly ingest into Salesforce target objects. 2. Step 2. Validate structure. Check columns, format, null values, and duplicates. 3. Step 3. Store file metadata and checksum. 4. Step 4. Load into staging table or custom object. 5. Step 5. Process row-by-row rules with error isolation. 6. Step 6. Move successful records to target objects. 7. Step 7. Send failed rows to an error repository and trigger alerts. 8. Step 8. Generate audit log and load confirmation. Apex implementation, staged processing with row-level error isolation. Disclaimer: always test code in a non-production environment. Before we even attempt to create an account object, we validate the staging data. This prevents bad data from ever polluting the memory heap or the target object. The try-catch block is placed inside the loop. This is crucial. It ensures that one malformed row does not crash the entire file processing. We isolate the failure, log it, and continue processing the rest of the file. We write every failure to a custom error log object linked to the staging record. This allows the operations team to see exactly which rows failed and why, facilitating manual correction and re-upload.
Strategic analysis.
1. Staged load prevents corruption of core data. 2. Validation before commit protects data integrity. 3. Error isolation allows targeted reprocessing. 4. Full audit trace supports compliance like SOX and GDPR. 5. Never process files directly in target objects. 6. Middleware pre-validation is best practice. 7. Avoid bulk insert without row-level handling in CSV uploads.
Failure handling and prevention.
1. Corrupted CSV, quarantine file and notify data steward. 2. Missing columns, block ingestion and auto-reject. 3. Partial errors, only reject failed rows, not full file. 4. Mass update risk, control volume using batch windows. 5. No monitoring, create ingestion confirmation dashboard.
High-value interview answer.
I designed CSV ingestion using a multi-stage approach. The SFTP file is first loaded into a staging layer where we validate structure, mandatory fields, and duplicates. Only validated rows proceed into Salesforce via bulk API, and failures are logged with full error tracking. This protects core data from accidental corruption and supports compliance for audit traceability. We also implement checksum validation and escalation workflows for malformed files, ensuring no data bypasses control points.
Architect-level enhancements.
1. Use AI to detect abnormal data patterns pre-ingestion. 2. Automate schema recognition using metadata tracking. 3. Perform redaction on sensitive fields before loading. 4. Allow pre-approval workflow for high-impact ingestion files. 5. Apply version history tracking for complete traceability.
Engagement.
1. Have you ever seen a CSV load go wrong? Share your story, no names needed in the comments section along with section and scenario. 2. Like this if you'll never say, just ingest the file again.
Section 1 complete.
That completes Section 1, Legacy and Transformation Scenarios. These are still asked today not to check memory, but to test maturity and risk awareness. If you can handle legacy architecture in complex ecosystems, you are ready to build future solutions.
Coming up next.
Now let's step into Section 2, Modern Integration Practices. You may think you know them, but we're going deeper than REST versus SOAP. We're going enterprise level.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Salesforce jobs interviews like Salesforce LWC developer jobs, Salesforce technical architect jobs, Salesforce Solution Architect jobs, Salesforce Service Cloud Consultant or Specialist jobs, Salesforce Test Engineer jobs, Salesforce DevOps Engineer jobs, Salesforce Marketing Cloud Developer or Consultant or Specialist jobs, Salesforce Admin jobs, Salesforce Developer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based interview questions and answers, real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Section 2, Core Enterprise Integration Patterns.
The foundation, but often answered at surface level. Here, we go architect deep. Now that we've successfully navigated high-risk legacy integrations, it's time to step into what most people think they know. The reality? Even experienced architects lose points because they answer these present-day integration questions with surface-level textbook knowledge. In interviews, enterprise leaders don't want to hear what you use, they want insight into why and when not to use it. In this section, we go beyond patterns and into system thinking.
What this section covers.
This section covers modern enterprise integration patterns, REST versus SOAP versus gRPC, platform events versus CDC, API-led connectivity, authentication strategies, cloud cross-connectivity, and more. Most candidates list patterns. Architects demonstrate trade-off mastery, system governance awareness, and performance risk understanding. Your answer in these scenarios should never be tool-centric, it should be impact-centric. Let's begin with a foundational question that catches even senior architects off guard. How do you choose the correct integration style when scale, latency, and data consistency conflict?
Scenario 1, REST versus bulk versus streaming integration.
Your Salesforce org must synchronize 2 million customer records from an external system. Some updates must reflect within seconds, priority leads, while others can wait, profile enrichment. Additionally, the marketing team consumes real-time engagement signals. Which integration mechanism do you choose, REST API callouts, bulk API, or streaming events? This is asked in technical architect panels to assess depth in performance, impact, and scalability thinking.
Context and challenge.
1. Data volume range, 20 records per minute to 2 million plus daily. 2. Requirements. High priority updates need near real-time processing. 3. Requirements. Bulk updates are scheduled or high volume. 4. Requirements. Marketing team needs event notifications. 5. Constraints. API call limits. 6. Constraints. Latency critical for specific flows. 7. Constraints. Upstream system performance varies. 8. Constraints, risk of data drift if methods mix poorly.
The interview question.
How would you design the integration strategy for large-scale data sync with varying latency needs? When would you use REST, bulk API, or streaming? How do you avoid duplication, data inconsistencies, and performance throttling? Pause and consider, this is about trade-offs, not listing patterns.
Strategic integration strategy.
1. use REST API for low-volume, real-time transactional updates. 2. Use Bulk API, v2, for high-volume, non-urgent batch sync. 3. Use streaming events or platform events for event-driven, near real-time notifications. 4. Apply CDC only when data is changed inside Salesforce, not external. 5. Isolate sync logic via integration service to avoid logic inside triggers. 6. Apply orchestration for resolution if multiple methods touch same data. Here is the Apex implementation of using REST for immediate priority updates. Disclaimer: always test code in a non-production environment. This implementation specifically targets high-priority records. We use a future method to handle the callout asynchronously but near real-time. The critical check is the priority flag. Only high-priority records trigger the immediate REST update, preventing API limit exhaustion. Here is the Java implementation of routing updates between REST and bulk sync. Disclaimer: always test code in a non-production environment. This middleware routing logic demonstrates the decision engine. If the incoming request is high priority, it routes instantly via the REST client. Otherwise, it offloads the data to a bulk queue, ensuring system stability under load.
Trade-off analysis.
1. REST, fast, but limited throughput, governor limits. 2. Bulk API, scalable, but slower and async. 3. Streaming, real-time notifications, but not designed for data load. 4. Using bulk for real-time updates, unacceptable delay. 5. Hybrid model, best fit. 6. CDC for external system-driven sync, misuse.
Failure modes and risk mitigation.
1. High API usage, throttle via dynamic batch allocation. 2. REST failure, retry with exponential backoff. 3. Bulk processing errors, partial batch isolation. 4. Event delivery failures, use durable subscriptions. 5. Multiple sync paths, apply field-level sync arbitration logic.
Interview-ready answer.
I design a hybrid model, using REST for high-priority real-time updates, Bulk API v2 for scheduled high-volume sync, and streaming events for customer engagement notifications. I'd introduce a sync orchestration layer to prevent overlapping updates and apply priority-based routing. CDC would only be used for Salesforce origin updates. This ensures scalability without compromising responsiveness or causing data drift.
Architect-level enhancements.
1. Add AI-based routing to dynamically decide between REST and bulk. 2. Use governance tags to prevent unauthorized real-time sync. 3. Implement change collision detection if same record touched by multiple sync paths. 4. Monitor API usage and auto-switch to bulk during peak load.
Your turn, Section 2 Scenario 1.
What would you add or modify in this hybrid strategy to further optimize performance or concurrency control? Comment using this format, Section 2 Scenario 1, your answer. Now that we understand how to choose the right integration style, let's move from how data moves to when data should move and who controls the flow. In the next scenario, platform events versus change data capture, most architects answer incorrectly because they miss the critical governance layer behind the decision.
Scenario transition.
In the previous scenario, we explored how to choose the right integration mechanism based on scale and latency. Now, let's shift focus from how we move data to how we react to changes. This next question is deceptively simple: when should we use platform events, and when should we use CDC? Most candidates answer using Salesforce documentation terms. But senior architects are expected to assess governance, replay strategy, system of record responsibility, and data consistency impact across multi-system architectures. The difference between a strong answer and a great answer. Understanding control versus consequence.
Scenario 2, Platform events versus change data capture, CDC event replay and ordering strategy.
Salesforce and an external order management system must stay in sync. When Salesforce updates a customer record, external systems need to know immediately. When external systems update data, Salesforce must reflect those changes reliably. You're asked to choose between platform events and change data capture. Which do you choose, and why? Pause. This is not about real-time events. This is about data authority and event replay.
Context and challenge.
1. Integration direction, Salesforce to external system, sales-triggered events. 2. Integration direction, external to Salesforce, system-driven sync. 3. Required, real-time response and event recovery on failure. 4. Required, prevent circular updates and maintain sequence integrity. 5. Constraints, data ownership varies per field. 6. Constraints, events must replay for up to 72 hours, or more. 7. Constraints, some fields shouldn't trigger integration, internal only.
The interview question.
How would you choose between platform events and CDC when integrating Salesforce with external systems? How do you ensure that events are replayable, data is not overwritten incorrectly, and event order is preserved even under failure recovery? Remember, this is about reliability and control, not just technology.
Integration strategy, architect level.
1. Use platform events when you want Salesforce to proactively trigger an integration. 2. Use platform events when the event must represent an intentional business action. 3. Use platform events when the data does not exist yet, pre-save action or intent-based. 4. Use platform events when you need custom payload, governance, or logic filtering. 5. Use CDC when the change is database-driven, record-level update. 6. Use CDC when a specific field update triggers sync, post-save. 7. Use CDC when you need delta-based system recovery after downtime. 8. Use CDC when the external system is not the authoritative source. Here is the apex implementation of publishing a platform event after a strategic update. Disclaimer: always test code in a non-production environment. This check is crucial. We only fire the event when the specific customer segment field changes. This represents an intentional business action, not just a random data update. Here we define a custom payload. Unlike CDC, which sends all changed fields, platform events allow us to send exactly what the downstream system needs, providing better governance and decoupling. Here is the Java-based CDC consumer logic ensuring sequence and replay handling. Disclaimer: always test code in a non-production environment. This represents the data-driven nature of CDC. The consumer must filter the stream to ensure we only react to relevant field changes, preventing noise from unrelated updates. Finally, we synchronize the data. Since CDC is system-generated, it acts as a reliable audit trail for recovery, allowing us to replay missed events exactly as they happened in the database.
Trade-off analysis.
1. Platform events, intent-driven, customizable, governance support. 2. CDC, automatic, data-driven, replayable, ideal for recovery. 3. Platform events cons, harder for event recovery, no inherent replay window. 4. CDC cons, can cause recursion if not filtered. 5. CDC field filtering essential. 6. Combine both when strategic plus data sync required.
Failure modes and mitigation.
1. Event storm from massive updates, use field filtering. 2. Data bounce loop, external to SF add integration source tracking field. 3. Missed CDC event, replay from last sequence ID. 4. Platform event lost, use downstream queue with confirmation. 5. Out-of-order events, use timestamp-based sequence resolution.
The interview-ready answer.
I'd use platform events when the change is intentional and operation-driven, such as business-triggered updates where the payload can be tailored. For system-level synchronization, especially where recovery is required, I'd use CDC with field filtering and replay tracking. To avoid recursion, I'd include an integration source field and implement ordering logic using sequence IDs. This ensures event governance while maintaining audit trail and data consistency across integration layers.
Architect-level enhancements.
1. AI-based anomaly detection to auto-stop high-risk change events. 2. Use encryption for sensitive CDC data before streaming externally. 3. Route CDC to platform event translator in hybrid models. 4. Switch from CDC to platform events if change is action triggered.
Your turn, Section 2 Scenario 2.
How would you prevent an integration recursion loop between Salesforce and another system using CDC? Comment using this format, Section 2 Scenario 2, your answer. Now that we've tackled integration triggers and data ownership, let's move outward. In the next scenario, we're not just moving data, we're governing it. We'll explore MuleSoft and integration middleware, API-led connectivity with layered governance across enterprise systems.
Scenario transition.
In the previous scenario, we explored how data moves and when events should trigger. Now let's go one level deeper, not about data flow, but about integration control, governance, and evolution. Many architects mention MuleSoft in interviews but fail to explain why an API-led model matters architecturally, beyond tool capability. If your answer only says, MuleSoft connects systems, you'll sound like a developer. If you explain how it enables governance, layered security, and future extensibility, you sound like an architect.
Scenario 3, MuleSoft/middleware integration strategy.
You're designing the integration framework for a multi-cloud enterprise. Stakeholders ask why they should invest in MuleSoft or similar middleware, when Salesforce can directly call REST APIs. The CTO challenges you to justify, why use middleware? What is the architecture? How does it future-proof integrations? Pause, this question tests whether you design integrations or architect integration strategy.
Context and challenge.
1. Goal, centrally govern integrations across Salesforce, SAP, AWS, and internal apps. 2. Goal, reduce coupling between Salesforce and back-end systems. 3. Goal, support future systems being added without modifying existing Salesforce flows. 4. Goal, provide security, version control, API lifecycle, and monitoring. 5. Constraints, high transaction volume. 6. Constraints, enterprise-grade security and audit. 7. Constraints, need to support both synchronous and event-driven integrations.
The interview question.
How would you architect an enterprise integration model using MuleSoft or equivalent middleware, ensuring flexibility, layered governance, scalability, and minimizing direct dependency between Salesforce and back-end systems?
Integration strategy, API-led connectivity.
1. System APIs, directly connect to DB/legacy systems, handle low-level transformation, restricted change access. 2. Process APIs, orchestrate logic across systems, apply business rules, expose normalized contracts. 3. Experience APIs, optimized for Salesforce consumers, reduce API coupling, support versioning. 4. Benefit, can modify backend without impacting Salesforce. 5. Benefit, can onboard new external systems quickly. 6. Benefit, supports governance, throttling, logging, and caching. 7. Benefit, reduces point-to-point chaos. Here is the Java/MuleSoft style implementation of routing through API-led layers. Disclaimer, always test code in a non-production environment. The system API abstracts the complexity of the legacy database. It speaks the language of the backend, isolating those details from the rest of the architecture. The process API is where the logic lives. It combines data, applies rules, and creates a unified data model. This allows us to change business rules without touching the database connectors. Finally, the Experience API delivers the data in the exact format Salesforce expects. If Salesforce needs a new field, we update this layer only, without breaking the underlying process or system APIs.
Strategic trade-off analysis.
1. Middleware enables contract stability for Salesforce consumers. 2. API-led separation allows independent evolution of backend systems. 3. Governance for throttling, monitoring, token rotation, caching. 4. Multi-consumer support, Salesforce, mobile app, data cloud. 5. Direct Salesforce to backend connection, too rigid. 6. Process logic inside Salesforce, violates multi-system orchestration principles. 7. Middleware centralizes decisioning logic.
Failure handling and risk mitigation.
1. Backend service failure, gracefully fallback via cached response. 2. Latency spike, circuit breaker or queue. 3. Breaking change in backend, shielded by contract at process API level. 4. Unauthorized external access, secured using OAuth, MuleSoft policy gates. 5. Integration overload, adaptive throttling with backpressure.
Interview-ready answer.
I'd architect an API-led connectivity model using 3 tiers: system APIs, optimizing system-level access, process APIs, applying business logic, and experience APIs, consumer-aligned interfaces. Salesforce would consume experience APIs only, preventing direct dependency on back-end changes. This improves scalability, governance, and makes future integrations plug-and-play without altering Salesforce logic. Middleware also provides rate limiting, circuit breaking, token rotation, and monitoring, making it ideal for enterprise-grade resilience.
Architect-level enhancements.
1. Introduce caching layer in Experience API to reduce callouts. 2. Use AI-based decision routing to select best downstream service in multi-cloud. 3. Include API versioning strategy with rollback support. 4. Apply policy-driven access control, geo-based routing, usage limits. 5. Support headless integrations via process API exposure.
Your turn, Section 2 Scenario 3.
If the backend system undergoes frequent change, how would you ensure Salesforce stays insulated from those changes using middleware? Comment using this format, Section 2 Scenario 3, your answer. Now that we have control over integrations through governance, let's talk scalability. In the next scenario, you'll decide between bulk API and streaming, but this time, not just based on volume. We'll factor in performance, change impact, and data lifecycle.
Scenario transition.
In the previous scenario, MuleSoft governance, we focused on how integrations are controlled. Now, let's focus on how data sync happens at scale. This is where architects must go beyond explaining API types and instead justify decisions based on data lifecycle, synchronization impact, and performance models. In interviews, anyone can say, use bulk API for large data, only real architects talk about when that's not enough or even wrong.
Scenario 4, Bulk API versus Streaming Integration.
Designing the right sync framework based on urgency, volume, and business risk.
The scenario.
A Salesforce org needs to receive product inventory updates from an external system. High volume, 1M records or day. Some updates must reflect within seconds, critical availability changes. Others can be processed in off-peak hours. Business has strict limits on API usage. What's the correct integration pattern? Surface-level answer, use bulk for high volume plus streaming for real-time. Architect-level answer, not that simple, let's break it down.
Context and challenge.
1. Data characteristics, high-frequency change but not always high priority. 2. Data characteristics, latency important for critical updates. 3. Data characteristics, high volume may exceed rest or batch limits. 4. Data characteristics, may require change traceability for audits. 5. Constraints, API limits apply. 6. Constraints, external system load sensitivity. 7. Constraints, must avoid data override conflicts.
The interview question.
How would you design a large-scale integration with both real-time and bulk requirements, ensuring that critical updates are instantly reflected while cost and performance are optimized? Think prioritization, segmentation, and sync orchestration.
Hybrid integration strategy.
1. Use bulk API v2 for high-volume non-urgent data, full sync or update batches. 2. Use streaming events or platform events for critical low-volume change notifications. 3. Use middleware for update prioritization plus conflict arbitration. 4. Implement time-windowed ingestion for bulk loads, off-peak. 5. Use change flag to determine if record goes streaming versus bulk. 6. Segmentation logic, if inventory 5 units to send real-time, streaming. 7. Segmentation logic, else to send via bulk, queued for off-peak. Here is the Java implementation of routing updates using priority-based sync. Disclaimer, always test code in a non-production environment. This decision logic is the core of the architecture. We instantly evaluate the business impact, here, low stock levels. If critical, it bypasses the queue and triggers a real-time event. For standard updates, we prioritize system health over speed. We queue the data for a bulk batch, preserving API limits and reducing platform load. Here is the Apex implementation of sending critical updates via platform event. Disclaimer, always test code in a non-production environment. This snippet creates the platform event payload. Notice we explicitly mark the change type as real-time update, allowing the subscriber to distinguish this from a bulk load. The publish call sends the critical update immediately to the Salesforce event bus, bypassing the standard database transaction commit time.
Strategic trade-off analysis.
1. Bulk API v2, best for mass updates, parallel processing, minimal API impact. 2. Streaming, best for urgent update propagation. 3. Hybrid ensures performance and urgency balance. 4. Using bulk API only, unacceptable delay for priority changes. 5. Using streaming only, will breach event limits plus performance risk. 6. Add routing layer, deciding update path based on business rules.
Failure modes and mitigation.
1. Streaming event loss, subscribe with durable replay, store replay ID. 2. Bulk ingestion failure, use failed record extraction plus retry pipeline. 3. Update conflicts, add field-level ownership tags. 4. Too many real-time calls, throttle via dynamic routing. 5. API limits breach, auto-switch to queued bulk processing.
The interview-ready answer.
I'd architect a hybrid integration model, using bulk API v2 for large-scale synchronization during off-peak processing, and using streaming events for high-priority inventory updates that impact user decisions. A decision routing service would categorize incoming updates based on business impact, for example, low stock threshold, and, if an update is marked urgent, Salesforce receives it instantly via platform event. This avoids latency issues while managing API consumption efficiently. Bulk failures are reprocessed with error isolation, and streaming is configured with durable replay for reliability.
Architect-level enhancements.
1. AI-driven routing to classify urgency dynamically. 2. Automatic escalation if same record triggers frequent real-time updates. 3. Caching recent inventory status to avoid redundant streaming calls. 4. Use secondary sync pipeline to clean inconsistencies post-bulk load.
Your turn, Section 2 Scenario 4.
How would you handle potential data conflict if the same inventory record is updated via both bulk and streaming within a short time window? Comment using this format, Section 2 Scenario 4, your answer. Now that we've mastered the data sync trade-off, let's expand beyond Salesforce. In the next scenario, we tackle cloud integration, Salesforce to AWS or Azure, and how to architect async systems with security, cost, and event orchestration in mind.
Scenario transition.
In the last scenario, we explored data synchronization inside Salesforce. Now, let's step outside the Salesforce ecosystem. In modern enterprise integration, Salesforce rarely works alone. AI models might run in Azure, analytics in AWS, and core records may still sit in internal systems. In interviews, candidates usually answer with "use REST API" or "use middleware." Architects must demonstrate cloud integration models that honor data privacy, event prioritization, async resilience, and cross-system accountability.
Scenario 5, Salesforce to AWS or Azure integration.
Architecting async cloud synchronization with resilience, cost control and event-first orchestration.
The scenario.
You need to send customer and activity data from Salesforce to Azure for AI processing and AWS for analytics. Updates must reflect within minutes. Cost efficiency is critical. A failure must never block Salesforce operations. Cloud services must process data independently. How do you architect this? This question tests async architecture, integration decoupling, and reliability strategy.
Context and challenge.
1. Integration direction, Salesforce to Azure, AI, and AWS, analytics. 2. Requirements, Salesforce must never wait for external system response. 3. Requirements, multi-cloud support. 4. Requirements, low-cost processing, millions of daily events. 5. Requirements, resilience against cloud service outages. 6. Requirements, eventual consistency acceptable. 7. Constraints, rate limits from Salesforce and cloud endpoints. 8. Constraints, cloud platforms may process asynchronously. 9. Constraints, network instability risk.
The interview question.
How would you design an integration from Salesforce to external cloud platforms, AWS or Azure, where real-time insights are needed but external failures must not affect Salesforce? Think decoupling, async, cost awareness, and event lifecycles.
Integration strategy, architect level.
1. Use platform events or CDC to publish changes from Salesforce. 2. Middleware or event router picks up events asynchronously. 3. For Azure, AI model route via async REST or queue, low latency. 4. For AWS, analytics or lake use batch or async streaming, Kinesis or S3. 5. Add durable event storage for recovery. 6. Apply circuit breaker to avoid failing external calls affecting Salesforce. 7. Include cost governance logic to optimize resource usage. Here is the apex implementation of publishing data to external cloud via platform event. Disclaimer: always test code in a non-production environment. We start with a logic check. Not every contact update needs to go to the cloud. Filtering here reduces noise, lowers API costs, and ensures we only transmit relevant data. By publishing to the event bus, we decouple the transaction. Salesforce finishes its work immediately without waiting for Azure or AWS, ensuring zero impact on user performance. Here is the Java-based implementation of routing Salesforce event to AWS and Azure async endpoints. Disclaimer: always test code in a non-production environment. The middleware router handles the specifics. For Azure AI, which likely needs near real-time data, we push to a low-latency async queue. For AWS Analytics, which often handles massive volume, we route to a Kinesis stream. This allows for batch processing and cost optimization, treating the two destinations according to their unique needs.
Strategic trade-off analysis.
1. Event-first integration, avoids dependency on external systems. 2. Asynchronous processing, ensures Salesforce performance unaffected. 3. Dual routing to AWS and Azure supports multi-cloud architecture. 4. Batch streaming reduces API costs. 5. Synchronous API calls, very high failure risk. 6. Circuit breaker plus async queuing equals resilience.
Failure modes and mitigation.
1. Azure or AWS service outage, store event in DLQ, retry later. 2. Overloading costs, use threshold trigger, pause high volume. 3. Data order conflict, use timestamp-based sequencing. 4. Event process twice, idempotency check in middleware. 5. Latency spike, add fallback cache until sync completes.
Interview-ready answer.
I'd use an event-first async architecture using platform events to push relevant data from Salesforce. Events are consumed by a middleware or routing service that sends data to Azure AI via low-latency async queue and to AWS analytics streams via batch or streaming methods. Salesforce never depends on external response, and failures route to DLQ with retry logic. This ensures scalable, resilient multi-cloud integration while preserving Salesforce performance and enforcing governance on cost and API usage.
Architect-level enhancements.
1. Include predictive failure routing, avoid sending events to unhealthy services. 2. Use AI-based load balancer to decide between Azure or AWS. 3. Implement event-level priority tagging, urgent versus analytic. 4. Add centralized dashboard with sync latency tracking.
Your turn, Section 2 Scenario 5.
How would you prevent integration overload if millions of records are updated in a short period? Comment using this format, Section 2 Scenario 5, your answer. We've now mastered secure async cloud integration. But speaking of security, let's address one of the most common architect-level interview challenges. How do you manage authentication in enterprise integrations while handling token expiration and rotation securely?
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked and system design. Required for your Salesforce jobs interviews like Salesforce LWC developer jobs, Salesforce technical architect jobs, Salesforce solution architect jobs, Salesforce service cloud consultant or specialist jobs, Salesforce test engineer jobs, Salesforce DevOps engineer jobs, Salesforce marketing cloud developer or consultant or specialist jobs, Salesforce admin jobs, Salesforce developer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based interview questions and answers, real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Scenario transition.
We just explored how Salesforce integrates with external clouds. But there's one silent failure that breaks more integrations than code issues: authentication. In interviews, many candidates say, use OAuth or configure named credentials. Seniors mention JWT flow. Architects explain how to prevent integration failure during token expiry, how to rotate tokens with zero downtime, and how to intercept unauthorized calls before they break production.
Scenario 6, OAuth, JWT, and named credentials.
Designing secure authentication with token rotation and zero downtime renewal.
The scenario.
Your Salesforce org connects to an external API using OAuth. At 2:12 a.m., the access token expires due to a policy update and all integrations start failing, causing a critical data sync backlog. How would you design the integration so token expiration never affects runtime execution? This is often asked for lead or enterprise architect interviews.
Context and challenge.
1. Integration method, OAuth 2.0, named credential. 2. Direct dependencies, Salesforce to external API. 3. Critical risks, token expiry during processing. 4. Critical risks, downtime during token refresh. 5. Critical risks, token rotation enforced by security team. 6. Required outcome, no integration failure due to token expiry. 7. Required outcome, automated rotation. 8. Required outcome, secure storage, no hard-coded tokens.
The interview question.
How would you design authentication in an enterprise Salesforce integration using OAuth or JWT so access tokens rotate securely without causing downtime or failed API calls? Think lifecycle, fallback, proactive detection.
Secure authentication strategy.
1. Use named credentials with OAuth or JWT-based token flow. 2. Implement token refresh using background scheduled flow/process. 3. Architect with pre-expiry refresh, for example, 10% lifetime remaining. 4. Use middleware as backup to handle authentication drift. 5. Add proactive alerting when token expiry nears or renewal fails. 6. Implement fail-safe, fallback to cached token for a short window. Here is the apex implementation of calling external API using named credentials with graceful error handling. Disclaimer: always test code in a non-production environment. Using callout named credential abstracts the authentication complexity. Salesforce handles the header injection, keeping our code clean and secure. This is the reactive safety net. If the call fails with a 401 unauthorized, we do not just crash. We immediately queue an asynchronous job to refresh the token, ensuring self-healing. Here is the Java implementation of token lifecycle monitoring and renewal mechanism. Disclaimer: always test code in a non-production environment. This represents the proactive architect mindset. We do not wait for failure. We monitor the token's lifetime and refresh it when it reaches a threshold, for example, 10% remaining. The fail-safe. If the primary token is dead and refresh failed, we switch to a backup token to keep the system running while alerting operations.
Trade-off evaluation.
1. Named credentials, best for Salesforce managed OAuth. 2. JWT flow, useful when refresh token not allowed. 3. Proactive refresh prevents runtime impact. 4. Backup token, minimizes API downtime risk. 5. Refresh on demand, may cause race conditions. 6. Must refresh before scheduled expiry.
Failure modes and mitigation.
1. Token renewal fails, retries plus alert to admin/SSE ops. 2. Token expired at runtime, fallback plus queued retry. 3. Unauthorized access attempt, block and alert. 4. Policy change invalidates tokens, auto-validation via heartbeat check.
The interview-ready answer.
I'd use OAuth via named credentials, implementing a proactive token refresh before expiration. A scheduled background process would renew the token when the lifetime drops below a threshold, for example, 10%. If a runtime call fails due to token expiry, my design would allow a fallback cached token and retry logic to delay failure. In case of renewal failure, an automated alert would be triggered to integration or security teams. Using JWT-based flow can additionally eliminate the need for storing refresh tokens in cases with stricter security.
Architect-level enhancements.
1. Implement token rotation dashboard with remaining lifetime tracking. 2. AI-based anomaly detection for abnormal authentication failures. 3. Use zero trust policy and allow token rotation per region. 4. Implement integration kill switch during token breach scenario.
Your turn, Section 2 Scenario 6.
How would you ensure that token refresh logic never creates conflicting authentication attempts from parallel integration processes? Comment using this format, Section 2, Scenario 6, your answer. So far, we have mastered resilience, synchronization, and security. Now let's move from back-end integrations to customer experience orchestration. Next scenario, integrating Salesforce with Marketing or Commerce Cloud for real-time personalization. Learn how to architect instant engagement without draining system performance.
Scenario transition.
So far in Section 2, we've focused on back-end integrations, APIs, events, middleware, security, and async cloud sync. Now let's shift focus from back-end reliability to customer experience impact. Integrations with Salesforce Marketing Cloud and Commerce Cloud are often answered with Use Journey Builder or Use MC Connect. That's a mechanical answer. Architect-level answers focus on when personalization is worth the system load, how to avoid latency-driven revenue losses, and how to design fail-safe experiences if integrations delay or fail.
Scenario 7, Salesforce to Marketing or Commerce Cloud integration.
Architecting near real-time personalization without compromising performance or data consistency.
The scenario.
A user adds items to cart on Salesforce Commerce Cloud. You must send real-time data to Marketing Cloud to trigger personalized email or push notification, without slowing down checkout. If the personalization event delays, revenue loss is expected. How do you design this integration? Most candidates say, use API callout. Architects design for latency isolation.
Context and challenge.
1. Integration path, Commerce or Core Salesforce, to Marketing Cloud. 2. Requirements, personalization event must deliver within seconds. 3. Requirements, transaction, checkout or interaction, must not wait. 4. Requirements, failures must not impact user flow. 5. Requirements, high spike volume during promotional marketing. 6. Constraints, API rate limits in Marketing Cloud. 7. Constraints, event spam risk. 8. Constraints, no guaranteed immediate processing. 9. Constraints, must comply with regional preference rules, GDPR, unsubscribe.
The interview question.
How would you design integration between Salesforce and Marketing or Commerce Cloud so that personalization happens in near real time without impacting transaction performance or risking failures? Think async, event-driven, prioritization, and customer impact hierarchy.
Integration strategy, architect level.
1. Use event-driven architecture, platform event or CDC. 2. Do not call Marketing Cloud synchronously during transaction. 3. Apply middleware or queue to deliver personalization trigger. 4. Maintain user interaction priority over marketing engagement. 5. Use fallback logic if personalized engagement delay exceeds defined threshold. 6. Apply rule-based filter to avoid redundant marketing triggers. Here is the apex implementation of asynchronously publishing personalization trigger post-transaction. Disclaimer: always test code in a non-production environment. We qualify the trigger immediately. Only confirmed orders initiate the marketing flow. This prevents abandoned carts or draft orders from clogging the event bus with irrelevant data. We construct a lightweight event and publish it asynchronously. Crucially, this eventBus.publish call is non-blocking, meaning the checkout transaction completes instantly for the user, while the marketing logic processes in the background. Here is the Java-based implementation of routing personalization event to Marketing Cloud asynchronously. Disclaimer: always test code in a non-production environment. The middleware router applies intelligent segmentation. If the customer is high value, we prioritize them, making a direct API call to ensure immediate engagement. For standard traffic, we queue the event. This allows us to batch updates to Marketing Cloud, preserving API limits and reducing costs during high-traffic promotional periods.
Strategic trade-off analysis.
1. Async event publishing protects transactional flow. 2. Real-time processing applied selectively, high-value triggers. 3. batch delivery minimizes marketing platform rate limit issues. 4. Direct API call during checkout, unacceptable latency risk. 5. Fallback, if event delayed beyond threshold, send delayed campaign. 6. Do not trigger marketing events on every minor interaction.
Failure modes and safeguards.
1. Marketing Cloud unreachable, store in DLQ and retry. 2. Duplicate triggers, use dedupe key, order ID plus event type. 3. Customers who opted out, enforce privacy rule filter. 4. Spike volume, auto-convert to batch processing. 5. Time-sensitive use case, track SLA versus user interaction.
The interview-ready answer.
I'd architect this using asynchronous platform event publishing from Salesforce so that the personalization trigger does not interfere with transactional flow. A middleware or routing logic would determine if the event must be sent immediately or queued for batch processing based on customer value and event priority. Fallback logic ensures customer experience isn't impacted if Marketing Cloud is delayed, and trigger deduplication prevents redundant campaigns. This design balances performance, engagement quality, and compliance.
Architect-level enhancements.
1. Use AI to score customer engagement urgency before sending. 2. Integrate caching to avoid duplicate sending in promotional bursts. 3. Implement journey gating based on real-time inventory state. 4. Use streaming for ultra-priority campaigns, for example, abandoned carts.
Your turn, Section 2 Scenario 7.
How would you ensure the same event doesn't trigger multiple marketing messages during high-traffic campaigns? Comment using this format, Section 2 Scenario 7, your answer. We've optimized integration for user engagement. Next, let's optimize integration for performance and API call reduction. In the following scenario, we'll look at how GraphQL can improve multi-system data fetch efficiency and help reduce API governance issues.
Scenario transition.
In the previous scenario, we optimized integration for user engagement without impacting performance. Now, let's address a major architectural challenge in multi-system environments. How do we retrieve complex, multi-entity data efficiently without exhausting API limits or overfetching data? Most candidates still propose REST with multiple callouts or discuss caching. But modern architects explore contract optimization, data shaping, and client-driven querying using GraphQL. This scenario challenges how well you understand performance scalability, API governance, and integration efficiency.
Scenario 8, GraphQL for integration efficiency.
Reducing API calls and optimizing data transfer in multi-system request architectures.
The scenario.
Your Salesforce Lightning UI retrieves account details, associated cases, and open opportunities from 3 different external systems via API. Each page load makes multiple sequential REST calls, increasing load time by 3 to 5 seconds. Leadership wants performance under 1 second, without increasing API call volume. How do you solve this? Most candidates answer, use batch API or combine endpoints. Architects answer, change the integration contract.
Context and challenge.
1. Current setup, Salesforce UI calls REST API 1, account details. 2. Current setup, Salesforce UI calls REST API 2, cases. 3. Current setup, Salesforce UI calls REST API 3, opportunities. 4. Issue, high latency due to sequential calls. 5. Issue, high API consumption. 6. Issue, dependent network round trips. 7. Issue, front-end waits for everything to complete.
The interview question.
How would you redesign the integration so Salesforce retrieves required multi-entity data in a single optimized call with minimal latency and maximum flexibility? Hint, think data shaping in contract flight.
Architectural strategy.
1. Implement GraphQL API wrapper in middleware. 2. Combine requests into a client-defined query. 3. Allow UI or Salesforce Apex to specify only required fields. 4. Reduce REST call count from 3 to 1. 5. Ensure performance via caching, schema versioning. 6. Use backend throttling to protect downstream services. Here is the GraphQL implementation of fetching account, cases, and opportunities in a single call. Disclaimer: always test code in a non-production environment. This query defines a single entry point. Instead of 3 separate HTTP requests, Salesforce sends one payload requesting exactly the data it needs for the 360-degree view. Here is the power of data shaping. We ask for related cases and opportunities in the same nested structure. Notice the arguments. We limit cases to 5 and filter opportunities by open stage directly in the query, preventing overfetching. Here is the Java implementation of executing GraphQL query via middleware orchestrator. Disclaimer: always test code in a non-production environment. The middleware acts as the orchestrator. It constructs the query string dynamically based on the Salesforce request context. The execution happens in one go. The GraphQL engine behind this client handles the complexity of calling the 3 underlying REST services in parallel and aggregating the response, shielding Salesforce from that complexity.
Trade-off analysis.
1. Eliminates overfetching by asking only what's needed. 2. Reduces REST calls to a single optimized call. 3. Improves UI performance via client-driven query. 4. Enables future changes without modifying API endpoints. 5. Requires middleware layer, not native in Salesforce. 6. Can be integrated via MuleSoft or AWS AppSync. 7. Must monitor query complexity to avoid system strain.
Failure modes and mitigation.
1. Excessively complex queries, limit query depth. 2. Slow downstream API, implement async or caching. 3. Schema evolution issues, use versioned GraphQL schemas. 4. High costs, implement field query governance. 5. Query sprawl, restrict which fields are externally exposed.
The interview-ready answer.
To optimize multi-system data retrieval, I'd introduce a GraphQL-based API wrapper in middleware. This allows Salesforce to request only required fields from multiple backends in a single call, reducing API traffic and improving UI performance significantly. The query structure can be client-driven, supporting Salesforce Lightning UI and future integrations. Caching mechanisms and schema governance ensure performance and resiliency.
Architect-level enhancements.
1. Integrate caching layer to return near-instant responses. 2. Dynamically determine required fields based on page context. 3. Use AI to predict most requested fields and pre-cache them. 4. Apply cost-based query throttling to prevent misuse.
Your turn, Section 2 Scenario 8.
How would you prevent performance issues if developers query too many nested data fields using GraphQL? Comment using this format, Section 2 Scenario 8, your answer. We've now optimized API efficiency and improved real-time personalization. Next, we're moving into operational integration, incident-driven workflows. In the next scenario, we'll design how Salesforce should integrate with ServiceNow or Jira, ensuring incidents are logged and tracked without breaking operational systems.
Scenario transition.
So far, we've looked at integrations that improve user experience, performance, and scalability. Now let's shift toward operational resilience. In large enterprises, critical system failures, integration errors, and business exceptions must automatically raise incidents in platforms like ServiceNow or Jira. Most candidates answer, use REST API to create tickets. That's operationally risky. Architects design incident workflows that don't depend on real-time success and do not cause cascading failures.
Scenario 9, Salesforce to ServiceNow/Jira integration.
Designing incident-driven integration that is reliable, non-intrusive and audit-compliant.
The scenario.
An integration process failed multiple times due to upstream API issues. You're asked to automatically raise an incident in ServiceNow or Jira each time a failure occurs. But you must prevent duplicate incident creation, overloading ServiceNow with minor failures, dependency on external system uptime, and internal security violations, PII exposure. How do you design the integration? A junior creates a ticket. An architect designs incident intelligence.
Context and challenge.
1. Requirement: automatically log incidents when integration failure occurs. 2. Requirement: prevent repeated logs for same issue. 3. Requirement: differentiate minor failures from P1 incidents. 4. Requirement: must work even if ServiceNow or Jira is down. 5. Requirement: include failure metadata without exposing sensitive data. 6. Constraint: ServiceNow API rate limits. 7. Constraint: multi-system dependency. 8. Constraint: security and compliance, GDPR, PI masking.
The interview question.
How would you design an incident-driven integration from Salesforce to ServiceNow or Jira that reliably captures system failures, avoids duplication, and remains resilient even if the incident platform is unavailable? Think queuing, risk tiering, and classification.
Integration strategy, architect level.
1. Detect failure via integration monitoring or exception handler. 2. Classify issue severity, using predefined rules. 3. Add failure to incident queue object or message bus, decoupled. 4. Apply deduplication via hash, for example, error code plus source plus timestamp window. 5. Sync incident to ServiceNow or Jira asynchronously. 6. Retry or store in DLQ if platform unavailable. 7. Mask sensitive fields, never send PI. Here is the Apex implementation of queuing incident for async creation in ServiceNow. Disclaimer: always test code in a non-production environment. We start by generating a unique hash based on the error message and source. This signature is the key to our deduplication strategy, ensuring that a flood of 100 identical errors results in only one ticket. Before logging, we check if this signature was recently recorded. This simple check prevents log pollution and protects the downstream ServiceNow API limits. Here is the Java implementation of pushing logged incident to ServiceNow via middleware. Disclaimer: always test code in a non-production environment. The sync job processes incidents asynchronously. It attempts to create the ticket in ServiceNow. If successful, the local log is marked resolved, closing the loop. If ServiceNow is down, we do not lose the incident. We increment a retry counter. If retries are exhausted, the incident moves to a dead letter queue, DLQ, for manual review, ensuring zero data loss.
Trade-off analysis.
1. Asynchronous logging prevents integration delays. 2. Deduplication stops incident flooding. 3. Classification supports correct severity reporting. 4. DLQ ensures retries if ServiceNow or Jira fails. 5. Synchronous ticket creation, slows business flow. 6. Avoid sending full exception message, PI risk. 7. Retry logic improves incident reliability.
Failure modes and mitigation.
1. Incident created multiple times, signature-based deduplication. 2. ServiceNow outage, queue for retry. 3. Sensitive data exposed, mask fields before sending. 4. Minor failures triggering alerts, classification rules. 5. Incident logging failure, isolated, not blocking main flow.
The interview-ready answer.
I design incident-driven integration using an asynchronous queuing approach. Failures are recorded in Salesforce or middleware with unique signatures for deduplication and severity level identification. Only critical incidents are sent to ServiceNow or Jira asynchronously, ensuring no impact on transactional operations. If the platform is down, the incident remains in retry queue and moves to DLQ if retries exceed limits. Sensitive fields are masked before syncing, ensuring compliance and operational stability while still providing troubleshooting value.
Architect-level enhancements.
1. Use AI to predict whether repeated failures require escalation. 2. Implement incident correlation to cluster-related failures. 3. Connect alerting to Microsoft Teams or Slack for rapid response. 4. Prioritize incidents based on business impact, not only error code.
Your turn, Section 2 Scenario 9.
How would you design incident escalation logic, for example, when should an automated incident convert to P1 with stakeholder alerting? Comment using this format, Section 2 Scenario 9, your answer. Now let's move from incident resolution to environment orchestration. In the next scenario, we will tackle a question often overlooked in architecture interviews: how do you integrate across multiple Salesforce orgs without creating data conflict or governance chaos?
Scenario transition.
So far, we've designed integrations between Salesforce and external systems: structured, governed, resilient. But what happens when Salesforce isn't just one system, but multiple? Many enterprises operate several Salesforce orgs, regional orgs, business unit orgs, M&A legacy orgs. And at some point, they must share data or processes. Most candidates suggest use MuleSoft or use CRM to CRM API. True architects explain how to prevent data conflict, enforce governance, and ensure synchronization consistency across orgs.
Scenario 10 Multi-org integration strategy.
Designing data flow and federation between Salesforce orgs without compromising security, consistency, or autonomy.
The scenario.
Your enterprise has 3 Salesforce orgs: Global, Asia-Pacific, and EU, each managed independently. Leadership wants consolidated customer visibility and unified reporting, without merging orgs. Data must sync selectively, based on region, ownership, and compliance, GDPR. How do you design this integration? Incorrect answer: integrate every org in real time. Correct answer: architect federation intelligently.
Context and challenge.
1. Current setup: multiple Salesforce orgs, possibly on different licenses/governance models. 2. Current setup: partial data overlap, same customer record in multiple orgs. 3. Current setup: regional compliance rules, for example, EU GDPR. 4. Current setup: different integration priorities per org. 5. Requirement: maintain org autonomy. 6. Requirement: enable selective data sync. 7. Requirement: resolve record conflicts. 8. Requirement: track data lineage, where data originated. 9. Requirement: avoid expensive full merge or replication. 10. Constraint: limited API quotas. 11. Constraint: different metadata models, fields different per org. 12. Constraint: data sovereignty laws, regional restrictions.
The interview question.
How would you architect a multi-org integration strategy where certain records must sync between orgs with reliable conflict resolution, governance, and data compliance support? Think federation, not duplication.
Integration strategy.
1. Define primary system of record, SOP, per domain, for example, EU owns EU data. 2. Use middleware as central orchestration point. 3. Sync selective fields only, minimize redundancy. 4. Introduce global ID to track data lineage. 5. Use CDC or scheduled batch sync, depending on rules. 6. Conflict resolution via ownership plus last modified strategy. 7. Implement region-based policy filters, GDPR enforcement. Here is the Java implementation of cross-org sync routing logic using a centralized identity model. Disclaimer: always test code in a non-production environment. The first gate is compliance. Before we move any data, we check for regional restrictions like GDPR. If consent is missing, the sync is blocked immediately to prevent legal exposure. This logic enforces the system of record strategy. We only propagate changes if they originated in the owning org, preventing data pollution from downstream systems. Finally, we handle the inevitable, concurrent updates. The architecture must have a predefined rule, either last one wins or system of record wins, to resolve conflicts automatically without user intervention.
Trade-off analysis.
1. Federation allows autonomy plus data sharing. 2. Selective sync reduces API and storage cost. 3. Global ID supports lineage tracking. 4. Middleware gives central control. 5. Full real-time sync across all records, overkill. 6. Better, hybrid, real-time for critical, scheduled for standard. 7. Conflict resolution is key to prevent inconsistent records.
Failure modes and mitigation.
1. Cross-org update loop, use integration source field. 2. GDPR violation, block sync based on policy. 3. Record conflict, apply precedence plus merge logic. 4. Different field schemas, use transformation models. 5. Massive sync volumes, leverage bulk API plus throttling.
Interview-ready answer.
I'd architect a federated integration approach where each org maintains autonomy and serves as the system of record for its region or domain. A central integration layer would handle selective synchronization using CDC for critical updates and bulk API for scheduled sync. A unique global identifier is assigned to each entity to track lineage and prevent duplication. Conflict management rules would prioritize either last modified or owning region, and sync operations would enforce compliance rules such as GDPR before execution.
Architect-level enhancements.
1. Use AI to predict cross-org sync conflicts proactively. 2. Introduce sync approval workflow for high-risk updates. 3. Support event streaming for high-value real-time changes. 4. Auto-adjust sync frequency based on data priority. 5. Central dashboard tracking sync status per org.
Your turn, Section 2 Scenario 10.
How would you handle synchronization if sales teams from two different orgs modify the same account at near the same time? Comment using this format, Section 2 Scenario 10, your answer.
Section 2 Wrap-up.
We've now mastered core enterprise integration strategies, scalable, secure, and architecturally sound for today's environments. But senior interviews don't stop at what's stable. They push into what's complex. Section 3 is where online resources fall short, and real enterprise architecture begins, handling mergers, multi-org operating models, ERP modernization, real-time financial flows, multi-region deployment failures, and integration under stress. These are the scenarios interviewers use to distinguish integration leads from enterprise solution architects.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked and system design. Required for your Salesforce jobs interviews like Salesforce LWC developer jobs, Salesforce technical architect jobs, Salesforce solution architect jobs, Salesforce service cloud consultant or specialist jobs, Salesforce test engineer jobs, Salesforce DevOps engineer jobs, Salesforce marketing cloud developer or consultant or specialist jobs, Salesforce admin jobs, Salesforce developer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based interview questions and answers, real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section. These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Section 3, Complex Cloud and Enterprise Scenarios, Advanced Present.
If Section 2 was about building the system right, Section 3 is about keeping it working under real enterprise pressure.
Topics we will cover.
1. Multi-org integration, M&A event mesh versus org consolidation. 2. Integration with SAP or Workday, master data strategy. 3. ERP migration to cloud, hybrid interim architecture. 4. Third-party pricing, CPQ, velocity performance governance. 5. Real-time payment processing, PCI plus transactional resilience. 6. Governor limits under stress, circuit breakers. 7. Multi-region deployment, time zone plus consistency control. 8. Quoting in DX mode, metadata sync strategies. 9. Distributed caching, TTL, cache invalidation.
Section 3 Introduction.
In Section 3, we simulate the most complex scenarios faced by global Salesforce architecture, the integration challenges that don't fail because of technology, but because of extreme scale, geopolitical constraints, and enterprise restructuring. Brace yourself. This is the section that defines whether you are interview ready for chief architect roles.
Scenario Transition.
In Section 2, we mastered stable enterprise integration. Now we move into the realm where architecture is impacted not just by technology, but by boardroom decisions. In real-world enterprise environments, mergers or acquisitions force architectural shifts that no developer documentation prepares you for. The question isn't how to integrate systems. It's how to maintain business continuity while two companies technically, and operationally, become one.
Scenario 1, Multi-org integration during M&A.
Choosing between event mesh versus org consolidation while preserving operational continuity.
The scenario.
A global conglomerate acquires another company. Both have deeply customized Salesforce orgs with full business operations. Leadership requests a 360 degrees unified customer experience across regions immediately, without impacting existing business operations or waiting 18 months for org consolidation. How do you architect this? This is one of the most common CTO panel questions, and most senior architects fail here.
Context and challenge.
1. Setup, Org A, existing enterprise Salesforce, and Org B, acquired company's Salesforce org. 2. Setup, both actively used for customer operations. 3. Requirement, unified customer visibility and process alignment. 4. Requirement, no disruption to active sales or customer processes. 5. Requirement, preserve regional autonomy until process convergence. 6. Constraint, metadata customization conflicts and different object models. 7. Constraint, unsynchronized master data, product, pricing, rules. 8. Constraint, legal compliance, data sovereignty by region.
The interview question.
How would you architect multi-org strategy in an M&A scenario? Would you consolidate the orgs immediately, or use event mesh or data federation? How do you manage conflicting record ownership, data model mismatches, and business continuity during the transition? Assume this is asked at enterprise or chief architect level.
Integration strategy.
1. Short-term, event mesh/data federation, use Pub Sub or MuleSoft. 2. Exchange selected data only, contract level sync. 3. Mid-term, data model harmonization, master data alignment, global identity. 4. Long-term, org consolidation, only after operational and metadata convergence. 5. Prevent recursion, add source system field and implement change arbitration. Here is the Java implementation of org integration decision logic using event mesh versus direct sync. Disclaimer: always test code in a non-production environment. For critical accounts, visibility is the priority. We use an event mesh to federate the data immediately, ensuring the business gets a 360-degree view without waiting for a complex database merger. This is the safety valve. If the metadata is incompatible, say, conflicting field types or validation rules, we defer the sync. Trying to force this data through would break the target org, so we wait for the consolidation phase. For standard records, we take a selective approach. We sync only the high-value fields needed for reporting, keeping the integration lightweight and reducing the risk of data pollution.
Trade-off analysis.
1. Event mesh, fastest to enable cross-org visibility. 2. Consolidation, best for long-term governance, but high disruption risk. 3. Selective sync reduces risk of model collisions. 4. Federation keeps org stable during transition. 5. Full real-time sync, dangerous if metadata differs. 6. Recommended, hybrid strategy.
Risk scenarios and mitigations.
1. Data conflict between orgs, use org role plus source system for arbitration. 2. Performance impact due to high sync volume, priority-based sync scheduling. 3. Legal constraints, EU versus US apply regional regulatory filters. 4. Over-synchronization, implement explicit subscribe-only logic.
The interview-ready answer.
In an M&A scenario, I'd avoid immediate org consolidation due to disruption and metadata conflicts. Instead, I'd use event mesh federation via pub sub or MuleSoft to selectively sync high-value data while maintaining org autonomy. A master identity system would track data lineage and prevent recursion. Only once data models and processes are harmonized would we plan full org consolidation. This ensures business continuity while progressing toward a unified data strategy.
Architect-level enhancements.
1. Implement MDM with AI-driven reconciliation. 2. Predict cross-org data conflicts before processing. 3. Use GraphQL federation to provide merged customer view. 4. Manage region-aware sync flows with dynamic routing.
Your turn, Section 3 Scenario 1.
If consolidation is a long-term goal but federation is interim, how would you determine which data should be federated versus held back? Comment using this format, Section 3, Scenario 1, your answer. In M&A scenarios, the CRM systems often evolve, but what about the connected backend systems like ERP? Next, we tackle integration with systems like SAP or Workday, and the bigger question, how to architect the master data strategy before integration breaks everything.
Scenario transition.
In the previous scenario, we explored M&A multi-org integration where Salesforce orgs had to collaborate strategically. But what happens when the system you are integrating with is not just another org, it's the system that runs the company? ERP platforms like SAP or Workday are often the enterprise's core system of record. Architect-level interviewers don't care how to call SAP APIs. They want to know if you understand data ownership, control, lifecycle, and the impact of syncing data incorrectly.
Scenario 2, Integration with SAP or Workday.
Architecting enterprise-level integration where the problem isn't technology, it's who owns the data.
The scenario.
Salesforce must sync product, pricing, and employee hierarchy data from SAP/Workday. But here is the friction: SAP holds master data, Salesforce enriches and uses it, and both systems modify similar data at different lifecycle stages. What's your integration strategy? Incorrect answer: sync via MuleSoft. Correct answer: establish master data control before sync.
Context and challenge.
1. Data domains, product catalog, SAP to Salesforce CPQ. 2. Data domains, employee structure, Workday to Salesforce HR roles. 3. Data domains, pricing adjustments, Salesforce to SAP reapproval. 4. Challenge, ownership conflicts. 5. Challenge, batch versus real-time sync requirements. 6. Challenge, data versioning, ERP versus CRM. 7. Challenge, limited API flexibility in ERP. 8. Challenge, high integration failure impact, for example, pricing error leads to revenue loss.
The interview question.
Before integrating Salesforce with SAP or Workday, how would you architect master data strategy? How do you prevent data drift, manage ownership conflicts, and safely orchestrate lifecycle-based sync? Hint: you either control data now or clean it up for years.
Integration strategy, master data first.
1. Define system of record, SR, per entity, SAP for product base, Salesforce for deal context. 2. Use lifecycle-based sync orchestration, SAP to active price lists to Salesforce. 3. Govern sync speed based on change risk. 4. Pricing, real-time via event. 5. Catalog, batch, nightly. 6. Hierarchy updates, on-change trigger. 7. Use data stewardship workflow for complex syncs, don't auto-sync high-impact data. Here is the Java implementation of lifecycle-based sync from SAP to Salesforce CPQ. Disclaimer: always test code in a non-production environment. For base price updates coming from SAP, we use the bulk API. These changes are voluminous and low-risk, making batch processing the most efficient choice. For negotiated prices, the logic shifts. We first verify approval status. Only approved changes are published to the event bus for real-time synchronization, preventing draft or invalid pricing from polluting the downstream system. Here is the Apex implementation of sending discount change back to SAP after approval. Disclaimer: always test code in a non-production environment. The trigger logic is strict. We explicitly check the "is discount approved" flag. This ensures that Salesforce only acts as the system of record for pricing overrides after the internal business process is complete. We publish an ERP event. This decouples the transaction. The save happens immediately for the user, while the sync to SAP happens asynchronously, respecting the external system's boundaries.
Trade-off analysis.
1. Lifecycle-based sync avoids pushing unstable data. 2. Real-time sync only for validated transactions. 3. Data ownership clearly defined. 4. Middleware handles API format mismatch. 5. Full bidirectional sync without ownership, disaster. 6. Use approval gates for sensitive data.
Risk mitigation.
1. SAP or API outage, queue sync and retry. 2. Data conflict, use change authority rules. 3. Wrong pricing, rollback via ERP reference value. 4. Slowed ERP, limit sync frequency. 5. API overload, implement adaptive throttling.
The interview-ready answer.
Before syncing Salesforce with SAP or Workday, I'd establish data ownership using a lifecycle strategy. SAP remains the master for static pricing and product data, which is synced in batch to minimize risk. Salesforce may override values during negotiation, but only after approval. Those updates go back to SAP asynchronously. This ensures validated changes flow correctly without risking systemic data corruption. Sync is based on risk, not only technology. High-risk changes go through approval before integration.
Architect-level enhancements.
1. Apply event-outbox pattern for reliable ERP integration. 2. Use prediction models to detect abnormal ERP to SF data updates. 3. Introduce sync simulation mode before actual push. 4. Track data lineage end-to-end for audit and rollback.
Your turn, Section 3 Scenario 2.
How would you handle a scenario where both SAP and Salesforce modify the same field, for example, pricing, within a short time span, without losing intentional updates? Comment using this format, Section 3, Scenario 2, your answer. We have handled system of record responsibility in ERP integration. But what happens when the ERP itself is being modernized during a migration? In the next scenario, we architect the interim sync strategy while ERP is moving to cloud, without breaking existing integrations.
Scenario transition.
In the previous scenario, we integrated Salesforce with SAP or Workday assuming a stable ERP system. But what if the ERP itself is being replaced or modernized? In real-world enterprise transformations, companies move from on-premise SAP to SAP S/4HANA, from Oracle to Workday, or from proprietary ERP to cloud-based models. During migration, both systems must often run in parallel. Integrations must continue without duplication or corruption. And Salesforce must keep functioning even while ERP is changing under the hood.
Scenario 3, ERP migration to cloud.
Designing a safe interim integration strategy while ERP transitions to cloud-based architecture.
The scenario.
Your enterprise is migrating from an on-premise SAP system to SAP S/4HANA Cloud. Salesforce currently integrates with the legacy ERP and must continue to integrate seamlessly during and after migration. For 6 to 12 months, both systems will run in parallel during the transition. How do you architect the integration strategy so that Salesforce maintains operational integrity? Most candidates give a direct cutover strategy. Architects design parallel coexistence.
Context and challenge.
1. Current state, Salesforce connected to legacy ERP, on-prem SAP. 2. Migration state, legacy ERP being replaced by SAP Cloud. 3. Requirement, Salesforce should work with current plus new ERP. 4. Requirement, no double processing, duplicate sync. 5. Requirement, ensure data consistency during phased rollout. 6. Requirement, allow instant rollback if migration phase fails. 7. Constraint, timeline uncertainty, risky cutover. 8. Constraint, ERP APIs differ, SOAP versus REST or OData. 9. Constraint, some modules may coexist across systems.
The interview question.
How would you design an enterprise-grade integration strategy where Salesforce continues to function while the ERP is being migrated to cloud, ensuring no operational failure or data loss? Hint, think parallel mode, routing strategy, rollback safety.
Architectural strategy.
1. Introduce integration gateway layer, route integration requests based on module go-live status. 2. Use feature toggle approach, config-driven routing, legacy ERP versus cloud ERP. 3. Implement dual write mode, write to both systems, shadow mode, but consume from primary. 4. Use read from active system strategy, if module live in cloud, read from cloud, else read from legacy. 5. Enable rollback switch, one config change reroutes back to legacy system if failure occurs. Here is the Java implementation of routing logic based on ERP migration phase. Disclaimer, always test code in a non-production environment. The routing logic is dynamic, not hard-coded. We check the configuration for the specific module involved. If the module, for example, inventory, is still marked legacy, we route to the on-premise adapter. Once a module is successfully migrated, we simply update the config. The gateway instantly switches traffic to the cloud adapter without requiring a code deployment in Salesforce. This is the dual write or shadow mode. We write to the new cloud system as primary, but also write to legacy as a fallback. This ensures that if we need to roll back, the legacy system is up to date and ready to take over.
Trade-off analysis.
1. Config-driven routing allows phased rollout. 2. Dual write reduces migration risk. 3. Read from active prevents inconsistent values. 4. Single source system per module ensures controlled transition. 5. Full cutover, very high risk. 6. Progressive migration, safe and reversible.
Risk handling.
1. Inconsistent data across ERPs, periodic reconciliation. 2. Cloud ERP latency, implement queue-based async handling. 3. Module fails post-production, rollback via feature toggle. 4. API format mismatch, handle via transformation layer. 5. Dual write overload, apply timebox strategy.
The interview-ready answer.
I'd introduce an integration gateway that routes ERP interactions based on migration stage. A feature toggle determines whether Salesforce calls the legacy ERP or SAP Cloud. During transition, we used dual write in controlled windows for risk mitigation and shadow validation. When a module is fully stable in the cloud, the gateway shifts routing and disables legacy sync. Rollback is instant via config if issues arise. This protects Salesforce from migration instability while enabling a phased ERP transition.
Architect-level enhancements.
1. Add fallback logic, graceful degradation if cloud ERP down. 2. Predictive rollback triggers using anomaly detection. 3. Enable migration timeline simulation before go-live. 4. Use MDM for data consolidation post-go-live.
Your turn, Section 3 Scenario 3.
How would you avoid invoice duplication if dual write mode is active and both systems process transactions? Comment using this format, Section 3 Scenario 3, your answer. Now that we've stabilized ERP coexistence, let's focus on an advanced real-time complexity. In the next scenario, we explore how to integrate Salesforce with third-party pricing engines, like CPQ or Velocity, without performance degradation. This one is mission-critical. Architects who answer this incorrectly risk seven-figure revenue impacts.
Scenario transition.
We just navigated one of the hardest transformation scenarios, ERP system migration. But now let's tackle a challenge that affects revenue in real time. In enterprise sales cycles, pricing engines like Salesforce CPQ, Velocity, or external partner systems calculate commercial pricing dynamically. Under real-time stress, like quota periods, thousands of reps request pricing simultaneously. When integration architecture isn't optimized, performance crashes, delaying quoting, sales sign-offs, and revenue closure. This is one of the most frequently asked principal architect interview challenges.
Scenario 4, Salesforce to pricing engine integration.
How to architect high-concurrency pricing without breaking performance or causing revenue risk.
The scenario.
Your Salesforce org uses an external pricing engine, CPQ/Velocity/custom API. During quarter end, sales reps simultaneously request price updates for thousands of deals. You experience timeouts, governor limit errors, and pricing mismatches due to late responses. How do you architect the integration for high reliability under pressure? Most candidates say, increase timeout or use async. But in real enterprise, this will fail.
Context and challenge.
1. Requirement: pricing must return in less than 2 seconds. 2. Requirement: 1000 plus concurrent calls possible. 3. Requirement: if pricing engine is slow to must not block user. 4. Requirement: must allow provisional quote approval. 5. Requirement: retry logic without duplicate pricing risk. 6. Constraint: Salesforce synchronous call restrictions. 7. Constraint: pricing engine CPU throttling under load. 8. Constraint: API call limits. 9. Constraint: high revenue impact if incorrect pricing.
The interview question.
How would you design Salesforce integration with a pricing engine to ensure price requests are handled reliably, even under peak system load, without impacting sales operations? Hint: think request decoupling, caching, and governance control.
Integration strategy.
1. Cache last approved pricing, for interim user experience. 2. Use async pricing update, future call/platform event. 3. Apply failover logic, use last known good price. 4. Use circuit breaker, route to fallback if pricing engine slow/unavailable. 5. Throttle requests to engine during congestion. 6. Apply pricing window rule, for example, recalculated every X min. Here is the apex implementation of smart pricing call with fallback and circuit breaker. Disclaimer: always test code in a non-production environment. Before making the call, we check the circuit breaker. If the external engine has been failing repeatedly, the breaker is open. We immediately return the last known good price, preventing the user from experiencing a timeout. If the circuit is closed but the call fails, for example, timeout or 500 error, we catch the exception. We record the failure to update the circuit breaker state and gracefully return the fallback price, ensuring the sales process continues. Here is the Java implementation of throttled request queuing in middleware. Disclaimer: always test code in a non-production environment. In the middleware layer, we implement rate limiting. If the request volume exceeds 1000 transactions per second, TPS, we instantly reject excess calls and return the fallback. This protects the pricing engine from crashing under load.
Trade-off evaluation.
1. Caching allows immediate UX response. 2. Circuit breaker prevents system collapse during slowdowns. 3. Throttling avoids engine meltdown. 4. Async refresh ensures correct pricing later. 5. Direct synchronous call in high volume, high failure risk. 6. Optimistic price strategy plus approval pending finalization.
Risk handling.
1. Pricing engine outage, auto switch to cached pricing. 2. Price miscalculation, delta revalidate during contract approval. 3. Too many requests, queue or throttle. 4. Duplicate pricing calls, request fingerprinting. 5. Timeout, switch to fallback, reprocess async.
The interview-ready answer.
I'd architect pricing integration using a hybrid model. The user receives cached last approved pricing instantly, while an async process retrieves the latest price from the pricing engine. A circuit breaker prevents reliance on the engine during latency spikes, and throttling ensures system stability during peak hours. If the updated price comes later, it is validated before final quote approval. This protects performance while ensuring commercial accuracy.
Architect-level enhancements.
1. AI-based dynamic price prefetch when opportunity probability increases. 2. Use Kubernetes autoscaling for pricing engine demand. 3. In-memory distributed cache, for example, Redis, for instant retrieval. 4. Event-based pricing recalculation when deal complexity changes.
Your turn, Section 3 Scenario 4.
If cached pricing is used temporarily, how would you enforce revalidation before final contract signing to avoid revenue leakage? Comment using this format, Section 3 Scenario 4, your answer. Pricing failures hurt revenue, but payment processing failures can escalate to compliance breaches. In the next scenario, we tackle real-time payment integration with PCI compliance, one of the toughest real-time enterprise challenges.
Scenario transition.
Pricing failures impact revenue forecasting, but payment failures impact actual revenue processing, and potentially legal compliance. Many architects can explain REST APIs and async syncs, but when it comes to real-time payment processing, only enterprise-level experts understand PCI constraints, retry mechanics, transaction idempotency, fraud prevention, and full rollback in case of failure. This is one of the most difficult real-time integration scenarios asked in senior-level interviews.
Scenario 5, Real-time payment integration.
How to integrate Salesforce with payment gateways under PCI standards, ensuring resilience and data protection.
The scenario.
Salesforce submits payment authorization to an external payment gateway, for example, Stripe, CyberSource, Adyen. If the payment fails, it should not create an order. If the user refreshes, duplicate authorization must be prevented. And all payment data must remain PCI compliant, no sensitive card handling in Salesforce. How do you architect this? Incorrect answer, make a synchronous call and show result. Correct answer, build a secure payment orchestration model.
Context and challenge.
1. Requirement, real-time payment status must be confirmed. 2. Requirement, duplicate payment attempts must be prevented. 3. Requirement, full PCI compliance, no card data stored in Salesforce. 4. Requirement, retry strategy without double charging. 5. Requirement, full rollback if order or payment flow fails. 6. Constraint, Salesforce cannot store payment details. 7. Constraint, integration must complete threes. 8. Constraint, gateway downtimes must not block Salesforce sales.
The interview question.
How would you design a PCI-compliant, real-time payment processing integration from Salesforce to an external gateway that supports resilience, prevents duplicates, and avoids compliance breaches? Think tokenization, idempotency, circuit breakers, secure orchestration.
Integration strategy.
1. Use tokenization. Salesforce stores only payment token, not card data. 2. Send payment request with unique transaction ID to gateway. 3. Apply idempotency key to avoid double charges. 4. Circuit breaker if gateway is down, mark as payment pending, retry. 5. Order creation only after payment success. 6. Use async completion callback for final confirmation. Here is the Apex implementation of secure payment authorization using token plus idempotency. Disclaimer, always test code in a non-production environment. This is the most critical line for financial safety. We generate a unique idempotency key. If the network flakes and we send this request twice, the gateway will see this key and refuse to charge the customer a second time. We handle exceptions gracefully. If the gateway is down, we do not crash the transaction. We record the failure in our circuit breaker and mark the payment as pending retry. This allows the user to continue or the system to retry later without data loss. Here is the Java implementation of secure payment retry mechanism with idempotency enforcement. Disclaimer, always test code in a non-production environment. In the middleware layer, we strictly enforce the idempotency key header. This contract between Salesforce and the gateway ensures that even if a retry loop goes rogue, the financial system remains consistent.
Trade-off analysis.
1. Tokenization, ensures PCI compliance. 2. Idempotency, prevents double charging. 3. Circuit breaker, provides payment flow isolation. 4. Async finalization, prevents UX blocking. 5. Order only after success, avoids financial corruption. 6. Direct synchronous order creation, dangerous.
Risk mitigation.
1. Gateway down, mark payment as pending and retry later. 2. Duplicate retry, prevented via idempotency. 3. User refresh page, transaction still referenced by key. 4. Partial payment but order created, rollback order. 5. PCI violation, never store card data locally.
The interview-ready answer.
I'd use a token-based authentication model with idempotent payment authorization, so Salesforce only handles tokens, not card data. A unique transaction ID prevents duplicate charging. In case of failure or gateway latency, I'd use circuit breaker and mark payment as pending rather than fail the transaction. Order creation only happens once payment is confirmed asynchronously, ensuring resilience and PCI compliance.
Architect-level enhancements.
1. AI-based fraud detection inline with transaction scoring. 2. Real-time orchestration platform using event-based retry logic. 3. Multi-gateway fallback, route via alternative processor dynamically. 4. Payment reconciliation with ERP for financial integrity.
Your turn, Section 3 Scenario 5.
If a payment request is marked as pending due to gateway failure, How would you safely retry without accidentally triggering a second real charge? Comment using this format. Section 3, Scenario 5, your answer. Now, we go from financial risk to platform risk. Up next, how to architect Salesforce integration under extreme performance stress when governor limits hit fast, and failure is not an option. Next, handling governor limits under high-stress integrations, circuit breakers, bulkification, retry design.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Salesforce jobs interviews like Salesforce LWC developer jobs, Salesforce technical architect jobs, Salesforce Solution Architect jobs, Salesforce Service Cloud Consultant or Specialist jobs, Salesforce Test Engineer jobs, Salesforce DevOps Engineer jobs, Salesforce Marketing Cloud Developer or Consultant or Specialist jobs, Salesforce Admin jobs, Salesforce Developer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based interview questions and answers, real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Scenario transition.
We just designed real-time payment orchestration under compliance pressure, arguably one of the most sensitive flows. But there's another kind of failure that architects must be able to predict before it kills a system: Salesforce governor limits hitting under peak load. In enterprise interviews, when asked how to handle high-volume integration or batch failure due to limits, most candidates answer, we bulkify or use queuable. Architects show how to prevent system collapse via circuit breakers, throttling, scaling strategy, and governor limit prediction.
Scenario 6, governor limits under stress.
How to ensure large-scale integrations don't hit limits and stay crash-proof at runtime.
The scenario.
During a major data synchronization, 50,000 records are pushed into Salesforce via integration. Despite bulkification, the batch process intermittently fails due to CPU timeouts, heap size issues, or too many callouts. This leads to partial data updates and business delays. How do you architect so the system self-protects instead of crashing? Retry the batch equals developer response. Circuit break, isolate, redistribute load equals architect response.
Context and challenge.
1. Symptoms, apex CPU limit exceeded. 2. Symptoms, too many DML per transaction. 3. Symptoms, platform event overflow. 4. Symptoms, async retry causing backlogs. 5. Constraint, cannot increase Salesforce limits. 6. Constraint, business must continue uninterrupted. 7. Constraint, no partial commit allowed for critical records.
The interview question.
How would you architect Salesforce integration to gracefully handle governor limits under high-volume stress, ensuring reliability without crashing or losing data? Think load partitioning, circuit breaker, prioritization.
Integration strategy.
1. Use circuit breaker to detect stress conditions, temporarily pause inbound integration. 2. Segment data into priority tiers, critical records processed immediately, non-critical deferred. 3. Apply adaptive batch size dynamically, adjust batch scope based on remaining limits. 4. Use async chaining and queue rebalancing, distribute execution across jobs. 5. Failure isolation, move failed packets to parking queue, DLQ. Here is the apex implementation of adaptive batch execution with circuit breaker logic. Disclaimer: always test code in a non-production environment. The start method acts as the gatekeeper. We check the circuit breaker status immediately. If the system is already flagged as under stress, we throw a custom exception to defer execution, preventing the job from adding fuel to the fire. Inside execute, we use adaptive logic. Adjust batch size parentheses checks current CPU and heap usage. If we are nearing limits, it dynamically processes fewer records than the scope provided, ensuring we stay within safe operational boundaries. This is the fail-safe. If a limits exception occurs, we do not let the job crash silently. We record the failure to trip the circuit breaker for future jobs, and enqueue the current scope to a safe retry queue for isolated processing. Here is the Java implementation of dynamic retry throttling at middleware level. Disclaimer: always test code in a non-production environment. The middleware acts as a traffic cop. Before sending data to Salesforce, it checks the org's health status via API limits headers. If near threshold, it reroutes traffic to a low-priority queue, effectively shedding load.
Trade-off analysis.
1. Circuit breaker avoids complete system crash. 2. Dynamic throttling helps balance throughput. 3. Priority-based processing keeps business alive. 4. Deferred sync prevents lock contention. 5. Single-thread batch retry may escalate failure. 6. Better, load partition plus resiliency framework.
Failure scenarios and mitigation.
1. Governor limit breach, detect early and defer execution. 2. High concurrency, switch jobs to queuable scalable model. 3. CPU spikes, reduce batch size adaptively. 4. Repeat failures, DLQ and notify architect for manual review.
The interview-ready answer.
I'd implement a circuit breaker-based load protection model. If near governor limits, the integration system auto-pauses high-volume jobs, dynamically reduces batch size, and prioritizes critical transactions. Failed packets are stored in a retry queue without repeated job execution. Processing continues only when system stress reduces. This ensures the org remains stable and avoids cascading failures.
Architect-level enhancements.
1. Implement real-time org health telemetry, API plus CPU tracking. 2. Auto-switch to event-based streaming when queues exceed threshold. 3. Predictive backoff using machine learning from previous executions. 4. Adaptive concurrency throttling based on business hours.
Your turn, Section 3 Scenario 6.
How would you prioritize transaction processing during high load to ensure critical updates are not delayed? Comment using this format, Section 3, Scenario 6, your answer. So now that we know how to prevent system overload, let's talk about another silent disruptor, time zone drift and multi-region integration inconsistency, especially for replicated data and transactions. Up next, Scenario 7, multi-region deployment, time zone drift and data consistency.
Scenario transition.
We just learned how to protect system stability under stress using circuit breakers and adaptive execution. Now, let's talk about a challenge that quietly ruins enterprise data integrity: global deployment. In multi-region deployments, failures don't come from code. They come from time zone drift, latency delays, seasonal changes, DST, and inconsistent regional data propagation. Architects must understand how to design globally synchronized data models that don't corrupt transactions when time is treated differently across regions.
Scenario 7, multi-region deployment strategy.
How to prevent data conflicts caused by time drift and ensure consistency across global Salesforce orgs.
The scenario.
Salesforce has users in US, EMEA, and APAC. Integrations are based on timestamp comparison. At DST switch, records from different regions clash, both appear as the latest update. This causes critical logic errors, for example, order override, approval reversal. How do you architect time-safe integration? Incorrect answer, convert to GMT. Correct answer, design time-controlled consistency strategy.
Context and challenge.
1. Problem. API updates rely on last modified date. 2. Problem. DST shift causes time jumps, plus or minus 1 hour. 3. Problem. Regional latency, APAC to US, creates propagation delay. 4. Problem. Customers place orders across regions simultaneously. 5. Requirement. Absolute consistency in update ordering. 6. Requirement. No reliance on local device or system time. 7. Requirement. Support rollback or audit trail. 8. Requirement. Predictable ordering for event-based sync.
The interview question.
How would you design multi-region Salesforce integration to avoid time zone drift issues and ensure record update consistency globally? Think, universal timestamp governance plus sequence logic.
Integration strategy.
1. Enforce the use of UTC only, remove local timestamp use. 2. Add region-neutral, sequence number, for ordering. 3. Use Lamport clocks or event ordering keys in streaming. 4. Apply eventual consistency model with conflict resolution logic. 5. Use middleware to adjust for latency delays, timestamp plus lead time. Here is the Apex implementation using sequence-based ordering instead of timestamp. Disclaimer: always test code in a non-production environment. We query the record, but notice we aren't asking for last modified date. We retrieve a custom last sequence __C field. This is an integer that increments with every change, regardless of time or location. The logic is purely mathematical. If the incoming update has a higher sequence number, it is newer. If it is lower, it is an out-of-order packet, possibly due to network latency, and is safely ignored. Daylight savings time has zero impact here. Here is the Java implementation using event order ID to prevent regional time conflicts. Disclaimer: always test code in a non-production environment. In the middleware layer, we implement the same deterministic logic. By comparing order IDs rather than timestamps, we ensure that a packet delayed by 500 milliseconds does not accidentally overwrite a newer packet that arrived first.
Trade-off analysis.
1. UTC removes time zone reliance. 2. Sequence-based ordering beats timestamp accuracy. 3. Event mesh supports ordered delivery per entity. 4. Latency compensated using safety margin. 5. Timestamp-only resolution, unreliable. 6. Mandatory use of stable ordering mechanisms.
Risk and mitigation.
1. Delayed update overwrites real-time action, use conflict resolution policy. 2. Regional system clock mismatch, UTC only plus server time validation. 3. DST-induced time drift, ignore local time, use epoch-based. 4. Multiple updates at same time, maintain incrementing sequence per record.
The interview-ready answer.
I'd avoid relying solely on timestamps for multi-region data consistency. Instead, I'd enforce UTC-based time normalization and use sequence-based event ordering, like Lamport clock or versioning. Every update carries an ordering ID, ensuring deterministic synchronization regardless of time zone drift or network latency. Conflict resolution is driven by sequence precedence instead of time-based comparison, making integrations globally consistent and reliable.
Architect-level enhancements.
1. Add anomaly detection for delayed event arrival. 2. Use quantum-safe time synchronization for critical systems. 3. Apply CRDT, conflict-free replicated data types, model for limited domains. 4. Shift to logical clock for transaction ordering instead of time.
Your turn, Section 3 Scenario 7.
If two updates arrive with the same sequence number but different sources, for example, US versus EU, how would you prioritize which update to apply? Comment using this format, Section 3, Scenario 7, your answer. Next, let's move from temporal consistency to configuration consistency. In highly dynamic enterprise environments where multiple teams configure solutions in parallel, how do you manage Salesforce quoting in DX mode without metadata collision? Next, Scenario 8, quoting in DX mode, metadata sync and change control under multi-team deployment.
Scenario transition.
So far, we've addressed stress under real-time and global scale. But architecture doesn't fail only under runtime pressure, it often fails during deployment and configuration. In large enterprises, multiple teams, CPQ, pricing, billing, integrations, work in parallel using Salesforce DX. Metadata conflicts, dependency mismatches, configuration drift, and parallel deployments often break quoting logic, leading to production disruption.
Scenario 8, quoting in DX mode.
Designing multi-team Salesforce quoting setup without metadata collision or deployment risk.
The scenario.
Your enterprise has several digital transformation squads. One team updates CPQ pricing rules, another updates quote template logic, and a third modifies discount approval flows. All working in parallel via Salesforce DX, but their deployments cause metadata collisions and runtime quote failures. How do you architect safe configuration management so quoting remains stable? Wrong answer, use source control. Right answer, architect governance around metadata dependencies and anti-collision strategy.
Context and challenge.
1. Challenge, multiple teams modifying related metadata, CPQ, flows, Apex. 2. Challenge, deployment sequences not aligned. 3. Challenge, package dependency mismatches. 4. Challenge, rollback not possible due to stateful configuration. 5. Risk, incorrect quoting in production, financial exposure.
The interview question.
How would you architect a safe Salesforce DX deployment strategy for quoting, ensuring no metadata collisions across multiple teams modifying related configurations? Think versioning, dependency guardrails, deployment pipelines.
Integration strategy, DX orchestration.
1. Implement modular DX packaging, separate CPQ rules, approval logic, UI, and integrations into managed kits. 2. Introduce dependency mapping, each change package must declare upstream or downstream impact. 3. Controlled release windows, only one quoting module deploys per governance cycle. 4. Use deployment validation sandbox, AI-based config compatibility checks. 5. Implement version lock, quote engine always runs on active certified version. Here is the Salesforce DX SFDX project.json config split into modular quoting packages. Disclaimer, always test code in a non-production environment. We define a core package. This contains the foundational data model and immutable logic. It is the base dependency for all other modules. Crucially, we separate volatile logic into distinct modules. Discount rules and approval workflows are decoupled. This means Team A can deploy a pricing change without risking a collision with Team B's approval process update. Here is the command to deploy a specific quoting package with validation. Disclaimer, always test code in a non-production environment. The deployment pipeline enforces a specific path. We deploy only the specific module path, P, and strictly enforce check-only validation against the UAT environment first to detect any dependency conflicts before the actual commit.
Trade-off analysis.
1. Modular packaging reduces collision scope. 2. Pre-deployment validation catches conflicts. 3. Version locking avoids partial state corruption. 4. Controlled deployment windows, stability for quoting engine. 5. Freeform DX branching, dangerous. 6. Promote via orchestrated dev to test to UAT to stage to prod.
Failure modes and mitigation.
1. Conflicting approval flows, enforce dependency mapping. 2. Quote rules overwritten, set metadata reserved by lockdown. 3. Partial deployment, deploy via unlocked packages only. 4. Post-deployment errors, use metadata rollback snapshot.
The interview-ready answer.
I would design a modular DX packaging strategy for quoting, splitting pricing rules, workflows, and UI logic. Each change package passes dependency checks and deploys via controlled release windows. A validation sandbox simulates deployment impact before execution, and only one quoting-related deployment is allowed at a time. Version locking ensures the quoting engine always executes against an approved version, reducing metadata collision risk.
Architect-level enhancements.
1. AI-based deployment predictor, detects impact before deployment. 2. Dependency graph visualization of metadata. 3. Autolock metadata heavily used in quoting. 4. Pre-deployment config simulation using Shadow.org.
Your turn, Section 3 Scenario 8.
How would you handle rollback for critical quoting metadata changes if Salesforce doesn't natively support configuration rollback? Comment using this format, Section 3 Scenario 8, your answer. Next, we go from deployment conflict to runtime acceleration. We're entering the final most advanced scenario in Section 3, distributed caching. How do you cache integration results across multi-system ecosystems without risking stale data or invalidation issues? Next, Scenario 9, distributed caching, TTL management, and intelligent invalidation.
Scenario transition.
In the last scenario, we optimized deployment consistency in high-change environments. Now, let's focus on runtime performance optimization using caching, a topic rarely discussed properly in interviews, but one that defines true enterprise scalability. Most candidates say, use caching to avoid frequent API calls. Senior architects explain when not to use caching, how to prevent stale data propagation, and how to manage cache invalidation safely in a distributed environment.
Scenario 9, distributed caching strategy.
Designing a high-performance caching strategy without risking stale data, sync failures, or business inaccuracies.
The scenario.
Salesforce calls external pricing, inventory, or eligibility APIs. During high-traffic periods, 5000 API calls or min, caching is implemented to improve performance. However, outdated data causes incorrect quotes, overselling inventory, and compliance issues. How do you architect caching with safety, ensuring data is fresh when needed? Incorrect answer, set small TTL. Correct answer, define cache strategy based on data nature, volatility and business risk.
Context and challenge. 1.
Caching use cases, price lookup, eligibility rules, inventory levels, multi-system config, AI recommendations. 2. Key risks, stale pricing, profit loss, inventory oversell, operational damage, compliance breach due to outdated rules. 3. Requirement, fast retrieval. 4. Requirement, controlled expiration. 5. Requirement, safe invalidation strategy. 6. Requirement, multi-region synchronization. 7. Requirement, immutability in critical use cases.
The interview question.
How would you design a distributed caching architecture for Salesforce integrations that improves performance without risking stale or inaccurate business decisions? Think risk categorization, invalidation logic, cache lifecycle.
Integration strategy.
1. Categorize data based on volatility, static or slow, long TTL, semi-dynamic, short TTL, real-time, no cache. 2. Use cache invalidation triggers, based on data change events, scheduled refresh, or user actions. 3. Apply hybrid cache strategy, read-through cache, fallback on miss, write-through for authoritative updates. 4. Track data freshness metadata, cache timestamp, source system, data sensitivity. Here is the Java implementation of intelligent cache validation before using cached data. Disclaimer: always test code in a non-production environment. This is not a blind cache retrieval. We check 3 conditions: is it there? Is it unexpired? And critically, is it low risk? If the data is high stakes, like inventory, we might skip the cache even if it is technically valid. If the cache is stale or risky, we fetch fresh data from the source. Crucially, we store the new value with a specific cache rule, ensuring that pricing data has a different lifecycle than, say, product descriptions. Here is the Apex implementation using event-triggered cache invalidation. Disclaimer: always test code in a non-production environment. We monitor specific field changes. We do not invalidate the cache for a description update, but we absolutely do for price or inventory changes. This precision prevents unnecessary cache thrashing. Instead of trying to clear the cache directly, which Salesforce cannot do for external systems, we publish an invalidation event. The middleware subscribes to this and purges the specific key from Redis or the API gateway.
Trade-off analysis.
1. Caching reduces API cost and latency. 2. Event-based invalidation prevents stale data exposure. 3. TTL strategy based on data risk. 4. Cache metadata aids troubleshooting. 5. Blind TTL, no invalidation risky. 6. Recommended, invalidate based on data change event.
Failure modes and mitigation.
1. Cache returns outdated data, include data freshness check. 2. High-frequency invalidation, use delayed refresh batching. 3. Region inconsistency, use centralized cache, for example, Redis or Event Mesh Sync. 4. Cache stampede, many requests after expiry apply lock-based refresh.
The interview-ready answer.
I design a risk-based caching strategy where data is classified based on volatility. Low-risk data uses longer TTL, while sensitive fields like pricing and inventory use short TTL with event-triggered invalidation. Every cached result holds metadata to determine freshness, and if a cache miss or expiry occurs, Salesforce retrieves fresh data and updates the cache. Quote-level accuracy validation is performed before order finalization to prevent stale use.
Architect-level enhancements.
1. Pre-caching based on AI prediction of high-traffic SKUs. 2. Multi-region in-memory cache replication, for example, Redis, Hazelcast. 3. Adaptive TTL adjustment based on transactional insight. 4. Cache warming during pre-sales high-volume periods. 5. Idempotent event outbox strategy for cache invalidation.
Your turn, Section 3 Scenario 9.
If the system uses cache and the API returns updated data during an active transaction, how would you ensure the cache and record align without introducing latency? Comment using this format, Section 3, Scenario 9, your answer.
Section 3 Wrap-up.
Section 3 Push the limits of enterprise-scale integration, from system migration, pricing orchestration, and multi-region synchronization to metadata governance and advanced caching. These scenarios proved you're capable of handling complexity during scale and change.
Beyond technical capability.
But enterprise mastery doesn't stop at delivering resilient systems. In highly regulated industries, finance, healthcare, defense, government, the architecture must not just scale. It must not break the law, compromise privacy, or allow unauthorized data exposure.
The shift to accountability.
Section 4 shifts the evaluation lens from technical capability to legal and ethical accountability. This is the level where architects protect organizations from million-dollar fines, national exposure risks, and compliance violations.
What is coming next?
Next, we enter regulated, highly secure, enterprise-grade scenarios, where auditability, data locality, encryption strategy, federated identity, feature risk containment, and AI accountability are the true success criteria.
Final thought.
If Section 3 was about surviving architectural chaos, Section 4 is about ensuring systems are so secure and compliant, they can stand up in court, in front of regulators, or even in front of a national cybersecurity review.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Salesforce jobs interviews like Salesforce LWC developer jobs, Salesforce technical architect jobs, Salesforce solution architect jobs, Salesforce service cloud consultant or specialist jobs, Salesforce test engineer jobs, Salesforce DevOps engineer jobs, Salesforce marketing cloud developer or consultant or specialist jobs, Salesforce admin jobs, Salesforce developer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based interview questions and answers, real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Section 4, Regulated, Highly Secure Scenarios.
What would you do if architecting for finance, healthcare, or defense? In sections 1 to 3, we built integration designs that are technically correct and scalable. But enterprise architecture at the topmost level has a different mandate: to protect the organization legally, operationally, and reputationally.
The enterprise mandate.
1. Preventing legal violations, GDPR, HIPAA. 2. Protecting classified data. 3. Ensuring breach survivability. 4. Designing fail-safe release strategies, zero blast radius. 5. Guaranteeing user identity across clouds without weakening security. 6. Making AI decisions traceable and legally explainable.
Why this matters.
These scenarios rarely appear in online resources. They're asked in interviews when you're being evaluated for chief architect or security and compliance authority. Here, every architectural decision must defend itself under audit.
Topics we will cover.
1. GDPR and data residency. Can you actively prevent illegal cross-border data sync? 2. HIPAA-compliant integration, encryption strategy, access traceability. 3. AI audit trail and inference logging. Can AI decisions be legally justified under investigation? 4. Controlled release via feature gating, architecting zero blast radius deployment. 5. Cross-cloud federated identity, multi-cloud SSO without weakening security.
Section 4 Introduction.
From this point onward, integration isn't just about performance, it's about protecting human lives, financial assets, and national security stability. Let's begin with the most commonly failed CTO assessment scenario: GDPR and data residency compliance.
Scenario transition.
Section 3 proved your capability to architect high-scale, high-stress enterprise systems. Now we step into scenarios where failure does not just cause downtime, it causes legal violation. In finance, healthcare, and defense, integration isn't just a technical problem. A single unauthorized data transfer could lead to legal prosecution, multi-million-dollar fines, public scandal, or complete service shutdown. Most candidates explain how to encrypt data. Architects explain how to ensure certain data is never sent at all when laws prohibit it.
Scenario 1, GDPR and data residency.
How would you architect an integration so that Salesforce never violates regional data protection laws?
The scenario.
Your company operates Salesforce in both EU and US. A US sales user tries to access a European patient's record. Laws prohibit personal data from leaving EU. Also, an API job pushes data from EU to a US analytics system for predictive insights. The business says it is needed. The law says it is illegal. What do you do as the architect? Incorrect answer, encrypt the data. Correct answer, never allow the data to be synced or exposed outside the approved jurisdiction.
Context and challenge.
1. Regulation, GDPR, no personal data may leave the EU without a legal basis. 2. Regulation, data residency laws, data must physically remain inside region. 3. Regulation, Salesforce may be multi-region, but integration endpoints may violate jurisdiction. 4. Challenge, how to detect and block restricted data sync. 5. Challenge, how to architect regional segmentation. 6. Challenge, how to audit illegal attempts. 7. Challenge, how to prevent user access from wrong region.
The interview question.
How would you design Salesforce integration to ensure no prohibited personal data leaves the allowed legal jurisdiction, even if someone tries to extract or sync it? Think, blocking, prevention, and legal defense. Not masking.
Architecture strategy, prevent, do not just secure.
1. Data classification at field level, mark GDPR protected fields. 2. Regional processing enforcement, segregate integration endpoints by region. 3. Policy-based access and sync control, middleware checks region of origin before allowing sync. 4. Tokenization or hashing instead of transfer, only irreversible identifiers allowed outside jurisdiction. 5. Illegal sync detection and auto-audit, any blocked sync triggers compliance alert. Here is the Java implementation of regional data compliance filtering before data sync. Disclaimer, always test code in a non-production environment. This is the active blocking mechanism. Before any byte is transferred, the filter checks if the record contains sensitive fields and if the destination matches the origin region. If not, the transfer is killed immediately. For analytics, we allow exceptions only if the data is tokenized. This means the personal data is replaced with a non-reversible token, allowing aggregate analysis without violating privacy laws. Here is the Apex implementation of enforcing region-based access control. Disclaimer, always test code in a non-production environment. We enforce residency at the access layer. Even if a US user has a URL to a European record, this logic checks their user profile location against the record's region tag. If they do not match, access is denied at runtime.
Trade-off evaluation.
1. Prevention over correction, compliance-first strategy. 2. Region segmentation ensures lawful operations. 3. Tokenization allows limited analytical use. 4. Event-based auditing protects organization under legal review. 5. Masking data alone, not sufficient. 6. Must be prevented from leaving jurisdiction at all.
Risk and mitigation.
1. Rogue user API export, block using field-level policy. 2. Data transfer through background batch, apply regional validation before integration. 3. Sync conflict, stop sync and create remediation ticket. 4. Undetected violation, activate compliance alert and log details.
The interview-ready answer.
I would architect region-based integration enforcement. GDPR-sensitive fields are classified in Salesforce and cannot be synced unless a legally valid policy exists. Before any outbound transfer, middleware checks the region of origin tag and blocks unauthorized syncs. If anonymization is required for analytics, only hashed or tokenized fields are allowed. Access control logic prevents users outside the jurisdiction from even viewing the data. Every blocked attempt is logged for compliance and legal review.
Architect-level enhancements.
1. Integrate geofencing at network layer for outbound requests. 2. Dynamic masking using privacy rules based on user region. 3. Multi-tenant instance segregation, for example, dedicated EU instance. 4. DPA, data processing agreement, validation before new integration. 5. AI-based anomaly detection for unauthorized access attempts.
Your turn, Section 4 Scenario 1.
If analytics teams need EU customer insights globally, how would you design a legally compliant architecture that enables analytics without exposing personal data? Comment using this format, Section 4, Scenario 1, your answer. GDPR is about where data is allowed to go. Next, we handle industries where the data itself is medically sensitive and access must be tracked, even internally. Up next, Scenario 2, HIPAA-compliant Salesforce integration, medical data encryption and clinical access tracking.
Scenario transition.
In the previous scenario, GDPR, we learned how to prevent unlawful cross-border data movement. Now we go deeper, into environments where data is not just restricted, it's classified as protected health information, PHI. In healthcare systems, under HIPAA, Health Insurance Portability and Accountability Act, unauthorized access, even internally, can lead to legal violations. This scenario tests whether you can design an integration that protects medical data in use, at rest, and in motion, while preserving usability for authorized clinical teams.
Scenario 2, HIPAA-compliant integration strategy.
Designing healthcare-grade integration, encrypted, access-tracked, and policy-driven.
The scenario.
A hospital uses Salesforce Health Cloud to manage patient care interactions. Data must sync with an external EMR, electronic medical record system. Nurses and doctors need immediate access, but only those assigned to the patient. Even a system admin shouldn't be able to see PHI without justification. How would you architect such an integration? Incorrect answer, use encrypted fields. Correct answer, encrypt plus restrict plus audit plus attribute-based access control.
Context and challenge.
1. HIPAA requirement, encryption at rest and in transit. 2. HIPAA requirement, role plus context-based access. 3. HIPAA requirement, full audit log of every data access. 4. HIPAA requirement, minimal data exposure, only what's necessary. 5. HIPAA requirement, integration cannot bypass clinical access logic. 6. Challenge, external system, EMR, needs full data sync. 7. Challenge, Salesforce users must see partial or masked data. 8. Challenge, backend API cannot expose full PHI without proper authorization.
The interview question.
How would you design Salesforce integration for healthcare data, HIPAA governed, ensuring only authorized clinical roles access sensitive fields, while the external system gets full PHI safely? Think, attribute-based access plus encryption plus integration policy enforcement.
Integration strategy.
1. Enable platform encryption, shield encrypt PHI fields with deterministic encryption. 2. Apply attribute-based access control, ABAC only users assigned to patient case can see decrypted data. 3. Use integration credential segmentation, separate clinical user access from system-to-system API integration. 4. Secure sync with policy validator, block or sanitize outbound PHI if recipient not in compliance. 5. Implement full access audit trail, every view, update, and API access logged with reason. Here is the Apex implementation enforcing clinical access before showing PHI. Disclaimer, always test code in a non-production environment. This is attribute-based access control, ABAC, in action. We do not just rely on the profile or role. We check a dynamic relationship, is this user part of this specific patient's care team? If authorization fails, we do not throw an error, we mask the PHI. Crucially, we log the access attempt regardless of success. This audit log is a legal requirement for HIPAA compliance. Here is the Java implementation ensuring secure integration access handling. Disclaimer: always test code in a non-production environment. Before allowing any data out, the middleware validator checks the request context. Is the destination system certified? Is the channel encrypted, TLS? If not, the sync is blocked to prevent a breach.
Trade-off analysis.
1. Encryption protects PHI from admin exposure. 2. ABAC enables clinical access based on patient assignment. 3. Integration endpoint segmented to avoid user credential misuse. 4. Audit logging supports HIPAA audit investigation. 5. Standard FLS or role-based access is not enough. 6. Must validate clinical context before decrypting.
Risk and mitigation.
1. Unauthorized internal access, ABAC plus encryption. 2. Integration retrieves unfiltered PHI, apply outbound filter policy. 3. Missing audit, enforce audit logging mandatory. 4. Data breach during transfer, use TLS plus secure token handshake. 5. Clinical emergency, override needed implement break glass access with justification.
The interview-ready answer.
I would use platform encryption to secure PHI and enforce attribute-based access so only users assigned to that patient's care team can view unmasked data. For integrations, I'd issue a segregated system credential with HIPAA compliance check in middleware. All outbound transfers go through a security validator to ensure the receiver has legal rights to hold the data. Every access is logged with Y for audit, and override access is only enabled under controlled, emergency workflow, break glass model.
Architect-level enhancements.
1. AI-driven anomaly detection for abnormal PHI access. 2. Token-level temporary access gates, auto-expiring access. 3. Zero-trust access controlled integration channels. 4. Clinical context propagation across event-driven flows.
Your turn, Section 4 Scenario 2.
If a user tries to request unencrypted PHI through API using admin access, how would your architecture prevent exposure and log the attempted violation? Comment using this format, Section 4, Scenario 2, your answer. So far, we've enforced compliance at rest and in motion. Now we go to the next challenge, where AI makes decisions. If AI affects treatment, finance decisions, or risk assessments, can you prove why it made a decision? Next, Scenario 3, AI audit trail and inference logging, explainability and legal justification.
Scenario transition.
In the last scenario, we protected patient data via encryption and context-aware access. Now we face a rapidly emerging challenge, AI making decisions in high-risk industries. If AI influences medical treatment, credit risk decisions, insurance approvals, or defense classifications, regulators demand that every AI decision must be explainable, traceable, and immutable. This is one of the newest and hardest CTO-level interview questions.
Scenario 3, AI audit and explainability architecture.
How to design AI-driven integration so every inference can be audited and justified.
The scenario.
Salesforce sends lead information to an AI model to predict credit approval. Based on AI output, the integration either approves or denies financial onboarding. A rejected applicant files a legal complaint claiming discrimination. Investigators request full traceability of which model version was used. What input data was considered? Was there any human override option? Was bias detected earlier? How do you architect this integration so answers are available instantly? Wrong answer, store scoring result. Correct answer, store decision lineage, inputs, version, metadata, justification path, human oversight triggers.
Context and challenge.
1. Industries, financial lending, AI bias review. 2. Industries, healthcare diagnostics, liability risk. 3. Industries, insurance underwriting, legal fairness. 4. Industries, defense or security, automated risk classification. 5. Challenge, AI often operates as black box. 6. Challenge, model versions change rapidly. 7. Challenge, need full lineage per decision. 8. Challenge, must prove no malpractice or unfair bias.
The interview question.
If an AI system influences regulated decisions, finance, health, defense, how would you architect Salesforce integration to ensure that every AI decision can be fully audited and justified legally? Think, inference log, model version tracking, human in loop, immutable decision ledger.
Integration strategy.
1. Capture AI decision metadata, model ID plus version plus timestamp, input parameters, decision score plus threshold, bias risk score. 2. Store an immutable ledger, use blockchain or write-once audit storage, tamper-resistant. 3. Implement human-in-loop trigger, if AI confidence threshold to manual review before action. 4. Integration design, AI model equals recommendation to decision executed by business rule. 5. Never allow AI to directly trigger final compliance action. Here is the Java implementation of AI inference logging with traceability. Disclaimer, always test code in a non-production environment. Tracking the exact model version is non-negotiable. If a lawsuit happens 2 years later, we must know exactly which algorithm logic was active at that millisecond. We hash the input data. This allows us to verify exactly what data the AI saw without permanently storing PII in the audit log, balancing traceability with privacy. We write to an immutable store. In a regulated environment, a standard database is not enough. We need write-once read-many, worm, storage to prove logs were not tampered with. Here is the Apex implementation triggering human review if AI confidence is low. Disclaimer, always test code in a non-production environment. This is the human-in-the-loop gate. If the AI's confidence is below our threshold, we do not auto-reject. We route for human review, ensuring fairness and preventing automated discrimination.
Trade-off analysis.
1. Full traceability for legal review. 2. Human override ensures no AI-only final decisions. 3. Immutable log provides non-repudiation. 4. Supports ethical compliance frameworks. 5. Storing complete dataset may violate privacy, store hashed reference and pointers instead. 6. Can store mapping in HIPAA or GDPR safe vaults.
Risk and mitigation.
1. AI bias, run fairness validation models. 2. Black box responses, include explainability module. 3. Log manipulation, use immutable ledger. 4. User bypass, enforce manual override gates in workflow. 5. Privacy breach, hash dataset and store reference only.
The interview-ready answer.
I would introduce an AI inference logging framework where every AI decision is captured with model version, source data hash, timestamp, and confidence. The system routes the decision through a human review path when confidence is below threshold. All logs are written to immutable audit storage to prevent tampering. AI models never perform final action, they recommend, and the workflow engine executes based on validation. This ensures that when legally challenged, we can fully reconstruct the AI decision process.
Architect-level enhancements.
1. Use explainable AI, XAI, frameworks, generate reasons for decisions. 2. Store digital signature of model object for authenticity. 3. Detect AI model drift over time to maintain reliability. 4. Trigger AI fairness evaluations based on decision patterns. 5. Use event-driven ledger for decision traceability.
Your turn, Section 4 Scenario 3.
How would you design an architecture that detects if AI decisions are repeatedly biased towards negative outcomes for a specific region or demographic group? Comment using this format, Section 4, Scenario 3, your answer. We've just ensured AI decisions can hold up legally. Now what if a deployment fails in production? In finance or healthcare environments, we can't afford rollbacks that affect live users. Next, Scenario 4, Controlled Release via Feature Gating, Zero Blast Radius Deployment.
Scenario Transition.
In the previous scenario, we established how AI-driven decisions must be auditable. But what happens when you release a critical integration update, and it causes live disruptions for medical users, trading operations, or security teams? In high-risk industries, finance, healthcare, defense, you cannot afford even temporary disruption. A trading failure may cause massive financial loss. A clinical failure may delay patient treatment. That's why enterprise architects use controlled rollout with zero blast radius, meaning even if a failure occurs, it affects no users.
Scenario 4, Zero Blast Radius Deployment Strategy.
How to deploy new integration capabilities without risking production stability in finance, healthcare, or defense environments.
The scenario.
You are deploying a major integration update between Salesforce and the core banking API. Business must continue 24/7 with zero risk. If something goes wrong, rollback must be instant and invisible to users. How do you architect that? Wrong answer, use rollback on failure. Correct answer, feature gating with shadow integration, dark launch, and progressive enablement.
Context and challenge.
1. Deployment complexity, always-on operations. 2. Deployment complexity, multiple user types, traders, bankers, clinical staff. 3. Deployment complexity, integration updates affect transaction logic. 4. Deployment complexity, rollbacks cannot create data state shifts. 5. Goal, enable new integration in isolated manner. 6. Goal, validate with selected users. 7. Goal, ability to switch off instantly if failure. 8. Goal, no data corruption or visible impact.
The interview question.
How would you design integration deployment so that no production users are affected if the update fails? Explain how to avoid any operational impact. Think, dark launch, progressive rollout, real-time disable mechanisms.
Integration strategy, zero impact by design.
1. Shadow integration route, new logic executes silently alongside old logic for validation. 2. Feature gating, allow or block new behavior using config flag. 3. Canary deployment, activate new integration only for test or limited users. 4. Instant kill switch, circuit breaker 1 config change revert system to old path. 5. Impact monitoring, activate only after key KPIs turn stable. Here is the Java implementation of gated new integration logic. Disclaimer, always test code in a non-production environment. This is the gate. We check a dynamic feature flag before routing traffic. This flag resides in a high-speed configuration store, like Redis or custom metadata, allowing us to turn the new integration on or off in milliseconds without a deployment. This is the safety net. If the feature flag is off, or if the new integration fails validation, recorded by the circuit breaker, the system automatically falls back to the legacy, stable path. The user never experiences an error. Here is the Apex implementation of selective rollout based on user or region. Disclaimer, always test code in a non-production environment. In Apex, we combine the feature flag with user context. This enables a canary release. We can enable the new API version globally but restrict access to only the pilot user profile, allowing us to test in production with friendly users before a wider rollout.
Trade-off evaluation.
1. Full control over rollout. 2. Instant toggle to stop impact. 3. No hard rollback or metadata undo required. 4. Shadow validation enables predictive analysis. 5. Direct deployment without gating is too risky. 6. Recommended, dark launch to limited activation to global release.
Failure modes and mitigation.
1. New integration fails under stress, auto switch off. 2. Unexpected output, route old integration immediately. 3. Partial failures, route impacted users only. 4. Deployment issue, release unaffected due to feature off.
The interview-ready answer.
I deploy using a feature-gated architecture with a shadow execution path. Initially, the new integration runs silently for monitoring only, dark launch. Once stability is confirmed, enable it only for a selected user group, canary. In case of failure, an instant kill switch route reverts to the old integration logic with zero runtime impact. This removes dependency on technical rollback and ensures zero blast radius during production deployment.
Architect-level enhancements.
1. ML-based failure prediction before full rollout. 2. Telemetry-based confidence scoring for auto-release. 3. Event-triggered reversion mechanism. 4. Progressive rollout weighting based on transaction success rate.
Your turn, Section 4 Scenario 4.
If the new integration logic begins causing latency after initial rollout, how would you detect and disable it instantly, without interrupting users in session? Comment using this format, Section 4, Scenario 4, your answer. So far, we've secured operations, data, and AI. But what about user identity across multiple regulated platforms? In the next scenario, we solve cross-cloud federated identity and zero-trust authentication for multi-business unit operations. Next, Scenario 5, cross-cloud federated identity and zero-trust authentication.
Scenario transition.
We've already protected data, secured AI decisions, and ensured zero-impact deployments. Now we reach the final frontier of integration architecture, identity security across clouds and business domains. In finance, healthcare, defense, and global enterprises, users may operate across Salesforce, SAP, AWS, and MuleSoft. The integration must authenticate without replicating identities. Passwords must never move. Tokens must be transient. Security must be contextual. A single breach here can lead to system-wide access takeover.
Scenario 5, cross-cloud federated identity and zero trust.
Designing seamless authentication across business units without compromising regulatory security.
The scenario.
A senior user accesses Salesforce to submit a pricing exception. The request is then routed to SAP for approval and an AI engine in AWS for risk scoring. The SAP team rejects storing user credentials in their system. Regulators demand unified identity proof per action. How would you authenticate this transaction across all systems without sharing credentials? Incorrect answer, replicate users across systems. Correct answer, implement tokenized federated identity with zero-trust handshake.
Context and challenge.
1. Problem, multiple clouds mean different identity stores. 2. Problem, password sharing violates security policy. 3. Problem, only the session should know identity, not the systems. 4. Problem, trust must be established dynamically, not assumed. 5. Requirement, single sign-on, SSO. 6. Requirement, per request revalidation, never trust, always verify. 7. Requirement, token failover and expiry enforcement. 8. Requirement, access logging at system of record level.
The interview question.
How would you architect identity management for multi-cloud integrations where no system shares raw user credentials, and every action must be securely attributable to the initiating user? Think, OAuth, STS, Security Token Service, Zero Trust, attribute-based routing.
Integration strategy.
1. Use Central Identity Provider, Keycloak, Okta, Azure AD. Salesforce authenticates via SSO. 2. Generate per request delegated token, based on user identity plus session claims. 3. Zero Trust Validation, each system validates identity independently before processing. 4. Mandatory authorization context, attach action metadata, user role, location, time, to token. 5. Log via central authentication chain, store per action audit data with token ID. Here is the Java implementation of federated identity issuance for integration requests. Disclaimer: always test code in a non-production environment. We issue a token based on claims. We aren't sending a username/password. We are sending signed assertions. This is user X, with role Y, performing action Z. This allows the receiving system to verify authority without needing the user's secret. The token is ephemeral. By setting a hard expiry of 5 minutes, we drastically reduce the attack surface. Even if this token is intercepted, it becomes useless almost immediately, satisfying zero trust principles. Here is the apex logic embedding federated identity into integration requests. Disclaimer: always test code in a non-production environment. In Salesforce, we fetch the current user's context and request a delegated token from our identity provider. We do not store this token, we request it on demand for this specific transaction.
Trade-off evaluation.
1. Zero password sharing. 2. Token-based authentication ensures compliance. 3. Each system validates token independently, zero trust. 4. Full traceability across systems. 5. More complexity, must maintain high token reliability. 6. Recommended for regulated, multi-cloud enterprise systems.
Failure modes and mitigation.
1. Token hijack, sign using asymmetric encryption, JWT plus private key. 2. Token expired mid-action, refresh token protocol. 3. Incorrect role mapping, use real-time user attribute check. 4. No central visibility, enforce unified auth log.
The interview-ready answer.
I would architect a federated identity model using a central identity provider. Salesforce would authenticate via SSO, and downstream systems use short-lived delegated tokens. Each integration call carries token-based identity claims and is validated individually at the receiving system using zero-trust checks. No credentials are replicated, and every request is logged in an immutable authentication ledger. This ensures cross-cloud security, compliance, and accountability.
Architect-level enhancements.
1. Add biometric or MFA if transaction exceeds risk threshold. 2. Use AI to detect suspicious access behavior. 3. Implement anonymous computing, no internal system sees real identity. 4. Rotate keys daily to avoid token replay. 5. Use confidential computing enclaves for sensitive system-to-system passes.
Your turn, Section 4 Scenario 5.
If a federated identity token is being reused repeatedly by system integrations, how would you detect abuse and enforce token revocation immediately without downtime? Comment using this format, Section 4, Scenario 5, your answer.
Section 4 Wrap-up.
Section 4 Evaluated if you can architect legally defensible, highly secure systems. From GDPR and HIPAA to AI accountability and zero-trust authentication, this is where technology meets regulation. Only architects who master this level are trusted in global transformation and public sector programs. Now comes the most elite section, the future. We move beyond compliance-driven architecture into self-healing, AI-driven, autonomous integration patterns for 2026 and beyond. Next, Section 5, Future-Ready and Autonomous Integration Strategies.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked and system design. Required for your Salesforce jobs interviews like Salesforce LWC developer jobs, Salesforce technical architect jobs, Salesforce Solution Architect jobs, Salesforce Service Cloud Consultant or Specialist jobs, Salesforce Test Engineer jobs, Salesforce DevOps Engineer jobs, Salesforce Marketing Cloud Developer or Consultant or Specialist jobs, Salesforce Admin jobs, Salesforce Developer jobs, etc., etc. These questions and answers are carefully curated by industry experts. saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based interview questions and answers, real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Section 5, Next Gen and 2026 Plus Scenarios.
These are the game changers, the scenarios that make our channel unmatched. Everything up to now taught you how to design robust enterprise integration strategies under today's business models. But the organizations that will dominate 2026 and beyond won't be defined by integration. They'll be defined by autonomous orchestration, AI-infused decision engines, and predictive architectural intelligence.
The shift to self-aware systems.
This section is not about solving high-risk problems reactively. It is about designing systems that predict, self-correct, and evolve without disruption. Interviewers at CTO and enterprise transformation levels are already asking, can your architecture self-heal? How does AI modify the integration flow in real time? How do you optimize cost dynamically? This is where integration becomes self-aware.
Key excellence signals.
1. Salesforce Copilot triggered automation, AI action execution with human override gates. 2. Gen AI plus Data Cloud, model-based instruction mapping. 3. Azure to GCP failover, stateful real-time system continuity. 4. Composable enterprise, Zero ESB API plus event mesh plus AI rule engine. 5. AI-driven ETL governance, pre-sync data scoring, mapping via AI. 6. Self-healing integration, predictive rollback, anomaly-triggered reroute. 7. AI-based risk scoring, auto-block high-risk transactions. 8. Cost-aware integration, routing based on API tokens/workload pricing.
Section 5 Introduction.
Section 5 is not about answering interview questions, it's about showing how you would design the integration fabric of 2026. Not just connected systems, but intelligent ecosystems. This is the difference between an integration architect and a systems architect for AI-driven digital enterprises.
Scenario transition.
Everything so far focused on architecting stable and secure integration. But systems of 2026 won't wait for user interaction, they will predict events and act first, with humans intervening only when required. Salesforce Copilot, Gen AI engines, and predictive data cloud analytics are already being embedded into core orchestration flows. The challenge? What if AI takes premature action? How do you govern an AI-driven system acting before humans?
Scenario 1, Salesforce Copilot involved automated actions.
AI-triggered workflows with safe human override and action control governance.
The scenario.
Salesforce Copilot analyzes opportunity trends and suggests moving deal stage to negotiation. In some cases, Copilot automatically sends proposal documents without user clicks. Later, sales leadership disputes an AI-triggered discount applied automatically. They ask, who approved this? Why did the system act on its own? How do you architect this? Incorrect answer, use approval workflow. Correct answer, design AI orchestration with gated execution, rollback trace, and explainable decision logging.
Context and challenge.
1. Intent, AI recommends actions, stage change, email, quote update. 2. Intent, some actions execute automatically, autopilot mode. 3. Risk, incomplete context at decision time. 4. Risk, untraceable decision reasoning. 5. Risk, no revalidation before execution. 6. Solution, AI suggestion only, unless validated by human or AI confidence threshold. 7. Solution, dynamic override rules. 8. Solution, transparent inference logging. 9. Solution, ability to undo AI-originated actions.
The interview question.
How would you architect AI-triggered Salesforce workflows so they execute only under controlled conditions, with override logic and full audit traceability? Think, AI, suggest, versus, act, mode, execution governance, rollback triggers.
Integration strategy, AI-governed orchestration.
1. Define AI action modes, recommend _ only, show suggestion, versus auto _ execute, action allowed. 2. Use confidence threshold with override, if confidence less than 85% points to human review required. 3. Apply AI action firewall, validate against business policy before execution. 4. Create action lineage record, store model version, confidence, input context, action, timestamp. 5. Allow event-based rollback, human or automated trigger can revert decision. Here is the apex implementation of AI action execution with confidence-based control logic. Disclaimer, always test code in a non-production environment. Before taking any action, we log the intent. We capture what the AI wanted to do and how confident it was. This creates the audit trail necessary to debug, why did the system do that, later. This is the control gate. If the AI is not at least 85% sure, we block the auto-update and flag it for human review. If it is confident, we execute the change but tag it as auto-executed so users know a machine made the edit. Here is the Java implementation of AI governance validation before integration triggers. Disclaimer, always test code in a non-production environment. Even if the AI is confident, is it allowed? We check business policies. For example, an AI might want to offer a 50% discount, but policy might restrict AI-driven discounts to 10% maximum.
Trade-off evaluation.
1. Safe AI orchestration, no blind execution. 2. Full logging enables AI audit review and rollback. 3. Confidence-driven action gating. 4. Supports future autonomous workflows. 5. AI acting without governance, risky. 6. Combine AI plus human review for high-impact decisions.
Risk and mitigation.
1. AI triggered wrong stage, rollback action via event. 2. Low confidence, move to approval required status. 3. Human bypass governance, system enforces AI rule layer. 4. Action executed outside business hours, time window guardrails. 5. Multi-AI conflict, arbitration via action prioritization framework.
The interview-ready answer.
I'd architect copilot-driven actions using a governance layer that separates suggestions from executions. Actions are only auto-triggered if AI confidence exceeds the approved threshold and policy validations pass. Otherwise, the action is held as pending AI approval. Each execution is logged with model version and confidence to support audit, and rollback can be initiated if needed. This ensures safe AI automation while enabling accelerated decisioning.
Architect-level enhancements.
1. AI maturity level adaptation, as trust increases, auto-execution threshold decreases. 2. Action simulation mode, run with no impact, compare outcome. 3. Predictive incident alerts before AI makes risky decisions. 4. Segmented capability per user seniority or compliance class.
Your turn, Section 5 Scenario 1.
How would you architect a scenario where AI suggests a price drop automatically during a negotiation, but only a sales manager can approve or override it before being committed? Comment using this format, Section 5 Scenario 1, your answer. Copilot can now make decisions, but what if it is powered by data not yet in Salesforce? Next, We integrate Salesforce plus Data Cloud plus Gen AI models, where decision execution happens across platforms. Next, Scenario 2, Gen AI integration with Data Cloud, model-based decision execution.
Scenario transition.
In the previous scenario, Copilot used local Salesforce context to trigger actions under control. But enterprise AI decisions cannot rely solely on CRM data. AI must consider customer 360 degrees context, across CRM, ERP, marketing, service, transaction history, and behavioral analytics. With Salesforce Data Cloud plus Gen AI models now predict customer likelihood to buy before user interaction, suggest proactive price modifications, initiate service intervention before escalation, activate retention workflows automatically.
Scenario 2, Gen AI integration with Data Cloud.
Architecting AI-driven decisions based on multi-source unified data models.
The scenario.
Salesforce Copilot detects a high churn risk for a premium account using Data Cloud predictive insights. It suggests a retention workflow, discount plus success call. For top-tier accounts, AI wants to trigger it automatically if likelihood of churn greater than 80%. How do you architect this without risking incorrect actions or abusing discounts? Wrong answer, just use flows and trigger off insights. Correct answer, design a decision gateway combining AI, business context scoring, and human validation tiers.
Context and challenge.
1. Context data sources, Salesforce CRM, account, opportunity. 2. Context data sources, Data Cloud, behavioral data, events, usage patterns. 3. Context data sources, ERP, billing history, payment failures. 4. Context data sources, Marketing Cloud, engagement scoring. 5. Context data sources, AI-based customer health score. 6. Risk, incorrect AI assumptions. 7. Risk, sales rep losing control. 8. Risk, over-offering incentives. 9. Risk, regulatory restrictions, for example, sector-specific pricing rules.
The interview question.
How would you architect a system where AI decisions based on Data Cloud insights execute selectively, with governance, override capabilities, and context-aware limitations? Think, layered decision gating plus risk mitigation plus no blind execution.
Integration strategy, model-based action gating.
1. Multi-system data unification, Data Cloud ingest operational plus behavioral data, generate AI health or revenue risk scores. 2. Tiered decision execution, risk less than 60% points to suggestion only. 3. Tiered decision execution, risk 60 to 80% points to action proposed with approval. 4. Tiered decision execution, risk greater than 80% and customer strategic to auto-trigger plus exec validation. 5. Use decision execution gateway, combine AI result plus business context plus compliance rules. 6. Full action trace in Data Cloud Decision Journal. Here is the Apex implementation using AI score from Data Cloud to trigger gated workflow. Disclaimer, always test code in a non-production environment. We start by logging the context. Before the logic even runs, we record the account ID, the computed risk score, and the customer tier. This ensures that even if the automation fails or is disputed, we have a record of why the process started. The logic is segmented. Low risk. Just a suggestion. Medium risk. We need approval. High risk. We check the tier. Only Platinum customers get the auto-execution treatment, protecting the business from mass automated errors on lower value accounts. Here is the Java implementation at integration layer combining AI plus compliance plus override routing. Disclaimer, always test code in a non-production environment. The gateway reinforces the Salesforce logic. It verifies two conditions: is the risk extremely high, 0.8, and is this a strategic customer? Both must be true to allow auto-execute. This double-check prevents AI hallucinations from triggering costly workflows.
Trade-off evaluation.
1. Prevents aggressive AI-triggered incentive misuse. 2. Decision strategy based on risk and business tier. 3. Traceable execution model. 4. Balances automation with governance. 5. 100% automated, risky. 6. AI suggests, business approves, until maturity.
Risk and mitigation.
1. AI creates large discount, cap incentives via rule. 2. Wrong risk score, require threshold validation. 3. Over-automation, tier-based auto-execution limits. 4. Loop execution, add AI trigger cooldown logic. 5. Unjustified discount for regulated clients, compliance guard.
The interview-ready answer.
I would centralize decision-making using data cloud to collate behavioral, financial, and engagement metrics. An AI-driven risk score would feed into a decision gateway that evaluates both risk level and customer segment. Only when risk is critical and customer is designated strategic, actions like retention incentives trigger automatically, otherwise they require leadership approval. All actions are recorded in a decision journal for audit and rollback. This balances predictive automation with business control.
Architect-level enhancements.
1. Predictive escalations before risk crosses threshold. 2. AI self-adjusting incentive strategy based on controlled learnings. 3. Integrate smart cooldown timers for repetitive AI triggers. 4. Autonomous customer prioritization for strategic saves. 5. Time window AI logic, only during churn cycle windows.
Your turn, Section 5 Scenario 2.
How would you prevent AI-based pricing or retention incentives being triggered during blacked-out financial control periods, for example, end of fiscal quarter? Comment using this format, Section 5 Scenario 2, your answer. Now AI understands broad context. But what if the entire cloud fails? The next level is availability. The architecture must allow real-time system failover from Azure to GCP, or AWS, without losing AI state. Next, Scenario 3, multi-cloud failover with stateful continuity, Azure to GCP disaster strategy.
Scenario transition.
So far, we have enabled AI-based automation with controlled execution. But what if the AI platform itself goes down? Or worse, the entire integration cloud? In enterprise architectures of 2026+, uptime cannot depend on a single cloud provider. Enterprise systems need multi-cloud failover, stateful AI model persistence, and continued integration flows without resending or losing API calls. This scenario tests if you can architect autonomous continuity across clouds, even during platform failure.
Scenario 3, multi-cloud failover strategy.
Architecting seamless real-time failover without losing integration state, AI context, or transaction consistency.
The scenario.
Your AI-based integration platform is running on Azure. During peak financial cycle, Azure region experiences a critical outage. The system must immediately fail over to equivalent GCP services without dropping transactions, retriggering duplicate actions, or resetting AI model state. How do you architect a cloud-agnostic, self-recovering integration layer that ensures stateful continuity during failover? Wrong answer, use multi-region replication. Correct answer, architect stateful handover with event-driven tokenized transfer and context preservation.
Context and challenge.
1. Requirement, no transaction loss during cloud outage. 2. Requirement, no double execution after failover. 3. Requirement, AI models must retain context to avoid decision restart. 4. Requirement, failover must be transparent to Salesforce flows. 5. Risk, Azure outage. 6. Risk, GCP latency risks. 7. Risk, model state reinitialization errors. 8. Risk, composability disruption.
The interview question.
How would you architect multi-cloud integration failover, Azure to GCP, ensuring full continuity of operations and AI inference state without user disruption? Think, event ledger, transaction fingerprinting, AI state containerization.
Integration strategy, stateful, predictive failover.
1. Use global event mesh, Kafka/pub/sub/async API transactional events written to central ledger. 2. Implement transaction fingerprinting. Every request includes unique execution token to prevent reprocessing. 3. AI context mirroring. Use model state sync, periodic checkpointing, and shared embedding stores. 4. Auto failover logic. Health monitoring auto switches routing based on thresholds. 5. In-flight replay. Exact once resume only incomplete events post failover. Here is the Java implementation of transaction fingerprinting for exact once execution. Disclaimer: always test code in a non-production environment. This method is the heart of the deduplication strategy. Before processing any event, we check the global event log for the transaction ID. If it exists, we know this event was already handled by the primary cloud before the crash, so we skip it to prevent double execution. Here is the Apex logic ensuring resumed sync after failover. Disclaimer: always test code in a non-production environment. When the secondary cloud, GCP, takes over, Salesforce replays the pending queue. Crucially, it does not just blindly retry. It passes every event through the token manager. Only events that were not successfully processed by Azure are allowed to run on GCP.
Trade-off evaluation.
1. Zero downtime failover across clouds. 2. No duplicate actions. 3. AI retains decision context. 4. Fully transparent to Salesforce. 5. Complex orchestration model. 6. Ideal for mission-critical industries, banking, healthcare, defense.
Risk and mitigation.
1. Duplicate execution, fingerprint gating. 2. AI state loss, containerization plus checkpoint replay. 3. Latency spike, adaptive cloud routing. 4. Failover bounce, introduce time-based lock window. 5. Unauthorized cloud shift, compliance-controlled cloud grouping.
The interview-ready answer.
I design a cloud-agnostic integration layer using an event-driven ledger with transaction fingerprint tracking. If Azure fails, routing shifts to GCP while only pending, unprocessed events are resumed. AI model state is preserved via checkpointing and shared embedding stores, preventing reanalysis. Failover is governed by health metrics and token-based non-replay logic, ensuring no duplication or data loss. This provides autonomous continuity with zero business disruption.
Architect-level enhancements.
1. Use federated AI model deployment with real-time embedding replication. 2. Predict cloud failure using AI-driven observability. 3. Introduce silent failover simulation, dark mode testing. 4. Failover cost awareness, switch based on pricing bias.
Your turn, Section 5 Scenario 3.
How would you prevent multi-cloud failover loops, for example Azure to GCP to Azure to GCP, from repeatedly switching mid-transaction? Comment using this format, Section 5 Scenario 3, your answer. We just built resilient cross-cloud architecture. Now let's step into next-gen composability. How do you design enterprise integration with Zero ESB, using API plus Event Mesh plus AI? Next, Scenario 4, Composable Enterprise Architecture, Zero ESB integration using APIs plus Events plus AI.
Scenario transition.
So far, we've built resilient and intelligent integrations. But legacy enterprises still rely on ESBs, centralized middleware platforms that act as single choke points. In 2026 plus architecture shifts, systems do not depend on centralized integration hubs. Integration becomes self-sustained, activated via API Mesh plus Event Mesh plus AI-driven routing. Logic moves to edge and application layers. This scenario evaluates whether you can decompose integration logic and self-orchestrate without a traditional ESB, while preserving control and visibility.
Scenario 4, Composable Enterprise, Zero ESB Architecture.
Architecting integration using API Mesh plus Event-Driven plus AI Decisive Orchestration, without a centralized ESB.
The scenario.
Your enterprise is migrating off MuleSoft or ESB to a fully composable model. Each business unit wants autonomy in integration logic, AI-driven where possible, without creating siloed systems. Integrations must run independently, use APIs or events, avoid central routing delays, and adapt at runtime based on context. How would you architect an enterprise-wide zero ESB integration fabric without compromising control? Wrong answer, use direct APIs between systems. Correct answer, use composable API mesh, event-driven autonomy, and AI-based workflow orchestration.
Context and challenge.
1. Traditional ESB flaws, single failure point, slow governance cycles, low adaptability to AI-based routing. 2. Composable enterprise needs, domain ownership model. 3. Composable enterprise needs, AI or orchestrator decides routing dynamically. 4. Composable enterprise needs, API mesh for synchronous calls. 5. Composable enterprise needs, event mesh for async flows. 6. Composable enterprise needs, shared policy enforcement.
The interview question.
If you are asked to architect a composable integration platform where no single ESB controls all flows, how do you ensure reliability, governance, and adaptability using APIs, events, and AI? Think, hexagonal architecture plus AI decision transformer plus domain-driven integration.
Integration strategy, composable architecture blueprint.
1. Use API mesh for real-time sync data flows. Each domain publishes discoverable APIs. 2. Implement event mesh, Kafka/PubSub event hubs for async transactional communication. 3. Embed AI orchestrator, decides whether to trigger API or event route based on context, load, and cost. 4. Localized integration logic, each domain controls its own orchestration, micro-orchestration model. 5. Policy and observability via edge gateway, no central ESB, but centralized visibility. Here is the Java implementation of AI routing between API and event-based pathways. Disclaimer, always test code in a non-production environment. The routing engine evaluates the business context, not just technical availability. If the request is high priority or requires real-time feedback, like a user-facing transaction, it routes immediately to the synchronous API mesh. If the operation is bulk or can tolerate latency, it offloads it to the event mesh. This decision happens dynamically at the edge, preventing the synchronous API layer from being overwhelmed by background tasks. Here is the Apex orchestration logic for composable integration inside Salesforce. Disclaimer, always test code in a non-production environment. Inside Salesforce, the pattern mirrors the enterprise strategy. The composer checks the is time-sensitive flag. It executes a direct callout for urgent needs or publishes a platform event for async processing, decoupling the implementation details from the business trigger.
Trade-off analysis.
1. No central bottleneck. 2. Domains maintain autonomy. 3. AI-based routing adapts dynamically. 4. Transparent governance via policy gateway. 5. Initial complexity. 6. Long-term resilience, adaptability, and agility.
Failure modes and mitigation.
1. Domain isolation, use shared API or metadata registry. 2. No central direction, use AI orchestrator hub. 3. Debug complexity, enforce distributed tracing with Trace ID. 4. Inconsistent policy, define governance layer at edge.
The interview-ready answer.
I would design a zero ESB composable architecture using API mesh for synchronous integration and event mesh for asynchronous messaging. Each domain manages its own orchestration logic. Routing decisions are driven via AI orchestration engine, which selects route dynamically based on business urgency, load, and cost. A centralized policy gateway guards security and compliance but doesn't control execution, preventing bottlenecks while maintaining control.
Architect-level enhancements.
1. AI-driven integration strategy optimization. 2. Cost-aware routing, API versus async at peak hours. 3. Predictive orchestration based on KPI risk. 4. Context-aware API prioritization. 5. Integration compiler, self-modifies orchestration logic.
Your turn, Section 5 Scenario 4.
How would you prevent uncontrolled point-to-point chaos when building zero ESB integrations, allowing autonomy while keeping long-term maintainability? Comment using this format, Section 5 Scenario 4, your answer. Composable systems are agile, but that means integrations can evolve fast. Now, how do we govern ETL transformations using AI, ensuring data quality before sync? Next, Scenario 5, AI-powered ETL governance, smart mapping and data quality inference.
Scenario transition.
We eliminated ESB dependency through composable architecture. But composability increases integration speed, which means more risk of incorrect or low-quality data flowing through systems. Today, most ETL transformations rely on static mapping or developer knowledge. Tomorrow, they will be managed by AI. In 2026 plus architectures, AI doesn't just map fields, it evaluates data health, suggests transformation, predicts anomalies, and blocks sync if confidence is low. This scenario tests whether you can design an integration that is both self-optimizing and self-protecting.
Scenario 5, AI-powered ETL governance.
Integrations that self-detect data mismatches, infer correct mappings, and auto-block low-quality syncs using AI.
The scenario.
Your ETL engine syncs financial transactions from core banking to Salesforce. An AI mapping validator detects that 8% of recent data loads have value format inconsistencies and predicts that 2.1% may lead to reporting inaccuracies. Before the sync executes, AI recommends, reject the sync or remap formats and retry under observation. How do you design this decision loop? Incorrect answer, run data validation before push. Correct answer, implement AI governance layer that validates structure, context, and integrity before ETL execution.
Context and challenge.
1. Common ETL risks, format mismatch, dates, currency. 2. Common ETL risks, field mapping drift after system update. 3. Common ETL risks, low quality or incomplete records. 4. Common ETL risks, implicit transformation, developer only knows rule. 5. Future-ready ETL, AI detects mapping anomalies proactively. 6. Future-ready ETL, automated transformation suggestions. 7. Future-ready ETL, ETL can self-stop if data risk is high. 8. Future-ready ETL, human override available.
The interview question.
How would you architect an AI-driven ETL system that prevents data corruption by auto-detecting mapping issues and blocking sync until mapping is either approved or corrected? Think, pre-sync AI validation, risk scoring, override controls.
Integration strategy, ETL with AI governance layer.
1. AI observes historical syncs, learns stable mapping patterns and tags inconsistent transformations. 2. Pre-sync AI validation, structural check, schema, context integrity check, value range, quality index evaluation. 3. Decision gating, risk 0.20 to auto-execute. 4. Decision gating, risk 0.20 and 0.45 to auto-transform and revalidate. 5. Decision gating, risk at 0.45 to block and require human input. 6. Mandatory trace logging, AI inference plus mapping changes saved. Here is the Java implementation for AI governance of ETL sync. Disclaimer: always test code in a non-production environment. The system starts with a health check. If the data quality score generated by the AI model meets the high confidence threshold, 80%, the ETL job proceeds automatically. This covers the happy path for clean, standard data. Here is the self-optimizing capability. If quality is moderate, the AI suggests a fix, for example, reformatting dates or normalizing currency. Instead of failing, the system attempts to auto-repair the dataset and resubmits it for processing, reducing manual intervention. Here is the Apex implementation for invoking transformation via platform event. Disclaimer: always test code in a non-production environment. Safety first. If the AI assigns a high-risk score, 0.45, the load is immediately blocked. This status triggers an alert for a human data steward to review the anomalies, preventing potential database corruption. For low-risk anomalies, we apply the AI repaired status. This keeps a clear audit trail that the data was modified by an algorithm, not a user, which is crucial for traceability.
Trade-off analysis.
1. Prevents mass data corruption. 2. AI-driven mapping improvements reduce manual maintenance. 3. Blocks sync if business risk detected. 4. Provides traceable evolution. 5. Requires strong data lineage tracking. 6. Use audit logs for post-validation.
Risk and mitigation.
1. AI incorrect transformation, allow human approval. 2. System update breaks mapping, anomaly detection triggers. 3. Mass sync failure, staged sync execution. 4. Delay affects SLA, prioritize critical data streams.
The interview-ready answer.
I'd introduce an AI-powered ETL governance layer that evaluates schema compliance, value integrity, and mapping consistency before sync. Based on confidence scoring, ETL is either executed, auto-corrected, or fully blocked if high risk. Each decision is logged for audit and rollback. This ensures data governance at integration level and removes dependency on human-performed mapping validations.
Architect-level enhancements.
1. Pre-ETL simulation mode with predicted performance. 2. Integration cost versus risk optimization, AI decides when to sync. 3. Automated rollback if downstream integrity violations detected. 4. Adaptive learning, AI improves over time based on mapping outcomes.
Your turn, Section 5 Scenario 5.
How would you prevent automated AI mapping correction from causing issues in heavily regulated datasets, for example, financial statements, where even minor formatting changes could legally matter? Comment using this format, Section 5 Scenario 5, your answer. We've now controlled ETL governance with AI. Next, what if an integration fails in runtime? What if the system could detect issues before failure and activate self-healing? Next, Scenario 6, Self-Healing Integration Architecture, Predictive Rollback and Autonomous Error Resolution.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked and system design. Required for your Salesforce jobs interviews like Salesforce LWC developer jobs, Salesforce technical architect jobs, Salesforce solution architect jobs, Salesforce service cloud consultant or specialist jobs, Salesforce test engineer jobs, Salesforce DevOps engineer jobs, Salesforce marketing cloud developer or consultant or specialist jobs, Salesforce admin jobs, Salesforce developer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based interview questions and answers, real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer. System design questions and answers where almost 90% of the people are failing to answer. With detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Scenario transition.
Until now, our architectures reacted to events. But next-gen systems don't just respond, they predict and self-correct. In 2026 plus architectures, when an integration detects increasing latency, abnormal failure trends, repeated retries, or unexpected AI inference confidence drops, instead of waiting for integration failure or operational impact, the system proactively switches to backup routes or last known good configuration. This is not rollback, it's preventative stabilization.
Scenario 6, Self-Healing Integration Architecture.
Predictive anomaly detection with autonomous rollback and route adaptation.
The scenario.
You're integrating Salesforce with a core payment gateway. During peak activity, API latency climbs 100 to 180 to 250 milliseconds over 3 consecutive calls. The system predicts that the next increase may cause timeout and failed transactions. Before failure occurs, it switches automatically to a backup payment route, or local cache-based hold, keeping operations seamless. How would you architect such a self-healing mechanism? Wrong answer, use retries and fallback. Correct answer, use predictive anomaly analysis plus AI-directed route switch plus consistency guard.
Context and challenge.
1. Requirement, detect deviation before failure. 2. Requirement, switch integration flow automatically. 3. Requirement, ensure state consistency. 4. Requirement, optional human oversight, post-switch. 5. Requirement, avoid cascading failure loops. 6. Failure scenario, API congestion. 7. Failure scenario, partial network outage. 8. Failure scenario, AI confidence drop. 9. Failure scenario, third-party response mismatch.
The interview question.
How would you architect a self-healing integration that predicts potential failures and activates alternative workflows before business impact occurs? Think, anomaly capture to preventive action to state alignment to learning loop.
Integration strategy, self-healing flow.
1. Runtime anomaly detection, monitor latency, failure trend, retry count, AI drift. 2. Predictive trigger, if system health drops below threshold to emit pre-failure _alert. 3. Smart route shift, switch to backup API/cache/async retry model. 4. Copy last valid state, maintain transaction integrity. 5. Post-restore adjust, return to primary route when stable. Here is the Java implementation of predictive failover trigger. Disclaimer, always test code in a non-production environment. We maintain a sliding window of recent performance metrics. We do not care about the average from an hour ago, we care about the exact trend of the last few transactions to detect immediate instability. This logic identifies the anomaly. It is not just checking if latency is high, it checks if latency is accelerating. If the response time jumps by 50% continuously, we predict a crash is imminent. Here is the Apex implementation handling predicted integration failure. Disclaimer, always test code in a non-production environment. Based on the monitor's prediction, the router acts before the failure happens. It proactively switches the traffic to a backup route or queue, ensuring the user transaction completes successfully. We log this as a preempted failure. This distinction is crucial for analytics. It tells us the system saved itself, rather than reporting a crash, proving the value of the self-healing architecture.
Trade-off evaluation.
1. Prevents failure instead of reacting. 2. Ensures uninterrupted business trail. 3. Adjustable sensitivity, AI-driven threshold. 4. Enables learning-based improvement. 5. Requires high observability maturity. 6. Best fit for mission-critical systems.
Risk and mitigation.
1. Too early switch, tune AI threshold. 2. Infinite flip-flop, cool-off window. 3. Backup channel cost, integrate cost-aware routing. 4. Discrepancies across switches, capture transaction state and replay. 5. False positive repair, auto-review escalation.
The interview-ready answer.
I'd architect a self-healing integration where an anomaly detection engine monitors failure trends and latency changes. If predictive indicators exceed thresholds, the integration automatically transitions to backup routing or cached execution before business failure. Each switch records decision context and can roll back later if conditions stabilize. This improves resilience proactively rather than reactively.
Architect-level enhancements.
1. AI predicts failure based on historical patterns. 2. Introduce health-based routing, multi-path execution. 3. Implement synthetic transaction testing. 4. Use predictive rollback, revert configuration before complete outage.
Your turn, Section 5 Scenario 6.
How would you avoid false positives in self-healing logic, ensuring it doesn't overreact to minor latency spikes? Comment using this format, Section 5 Scenario 6, your answer. Self-healing guards stability. But what if the failure isn't technical, it's a business or risk decision? Next, AI must block actions if associated risk exceeds acceptable boundary. Next, Scenario 7, AI risk scoring integration, auto-blocking strategic decisions.
Scenario transition.
Self-healing protected us from technical failures. But in 2026 plus architectures, not all failures are operational. Many are business risks. AI not only predicts technical anomalies, it predicts behavioral, financial, compliance, and fraud risks. Imagine a transaction that looks normal but resembles a known fraud vector, or a pricing exception that violates compliance rules. AI must stop the transaction, not just log it. This is where risk-aware integration becomes a competitive and compliance differentiator.
Scenario 7, AI model risk scoring integration.
AI that detects, flags, and auto-blocks high-risk actions before they hit downstream systems.
The scenario.
Your Salesforce org syncs orders to ERP. A Gen AI model trained on fraud and anomaly patterns assigns a risk score equals 0.92 to a suspicious order. Before sync occurs, the integration platform halts the action and labels it as high risk, blocked. Compliance team gets notified with evidence. How do you architect such a risk-scoring firewall that prevents unsafe transactions from propagating? Wrong answer, do risk scoring after data sync. Correct answer, intercept the action using AI risk scoring before executing integration.
Context and challenge.
1. Risk dimensions, fraud detection, compliance breach, money laundering indicators, creditworthiness anomaly. 2. Challenge, AI requires complete context. 3. Challenge, blocking must not break transaction state. 4. Challenge, need for explainability and audit trail. 5. Challenge, must support override workflows.
The interview question.
How would you design an AI-driven risk firewall that evaluates transactions and stops dangerous or non-compliant operations before they sync to downstream systems? Think, risk thresholds, explainability, override governance, pre-execution gating.
Integration strategy, enterprise risk firewall.
1. Pre-integration risk scoring. Before sync, AI analyses pattern and context to generate risk score. 2. Decision gate, 0.40 is normal, 0.40 to 0.75 is warning, require human approval, 0.75 is auto-block. 3. Risk ledger, store model version, input vector hash, reasoning, timestamp. 4. Override workflow, only compliance or admin roles can override with reason captured. 5. Autoblock integration, prevent propagation to ERP/banking/external API. Here is the Java implementation of pre-integration risk scoring. Disclaimer, always test code in a non-production environment. The engine calls the AI model synchronously. In a risk scenario, we cannot afford eventual consistency. We need the score now to decide the immediate fate of the transaction. This is the auto-block logic. If the AI is highly confident that this is fraud or a compliance breach, we stop the process dead in its tracks. No human intervention is required to stop the damage. Here is the apex logic applying risk gating before integration push. Disclaimer, always test code in a non-production environment. In Salesforce, we persist this decision. By setting the status to risk blocked, we lock the record. Validation rules can now prevent any further edits until a compliance officer reviews it. Only if the score is safe do we trigger the downstream integration. This ensures that the ERP system is never polluted with risky or fraudulent data.
Trade-off evaluation.
1. Protects downstream systems from bad data. 2. Ensures compliance, SOX, AML, KYB. 3. Early stopping reduces remediation work. 4. Full audit trail supports legal defensibility. 5. Must manage false positives. 6. Override workflow keeps system productive.
Risk and mitigation.
1. AI false blocking, add human review gate. 2. User bypass, enforce API level risk gate. 3. AI drift, periodic retraining and drift detection. 4. Black box decision, capture explainability metadata.
The interview-ready answer.
I'd implement a risk firewall that evaluates transactions pre-integration using a GenAI-driven scoring model. Transactions exceeding critical thresholds are automatically blocked before hitting downstream systems. Medium-risk items go through human approval. Every decision is stored in a risk ledger with model version and explainability for legal defensibility. This ensures only safe, compliant operations flow through the enterprise.
Architect-level enhancements.
1. Temporal risk scoring, based on time-based anomaly patterns. 2. Behavior-linked risk, user profile patterns. 3. Multi-cloud risk propagation prevention. 4. Dynamic, context-aware thresholds. 5. Predictive mitigation, suggest remediation steps.
Your turn, Section 5 Scenario 7.
How would you architect a system that prevents AI risk blocking from stopping mission-critical actions, for example, hospital discharge, government authorization, while still maintaining safety? Comment using this format, Section 5 Scenario 7, your answer. Risk scoring protects the business. But what about protecting the budget? Next, we architect AI that routes integrations based on cost, token usage, and real-time resource pricing. Up next, Scenario 8, Cost-Aware Integration Routing, AI-Based Resource Optimization.
Scenario transition.
Risk scoring protects the business. But what about protecting the budget? Next, we architect AI that routes integrations based on cost, token usage, and real-time resource pricing. API and compute costs are skyrocketing in 2026 plus, Gen AI tokens, cloud surge pricing. Enterprises want integrations that auto-switch to cheaper routes, throttle high-cost operations, and avoid unnecessary Gen AI calls. This is cost-aware orchestration, a critical 2026 skill.
Scenario 8, Cost-Aware Integration Routing.
AI that routes integration calls based on cost, token burn rate, load prices, and peak hour optimization.
The scenario.
Salesforce triggers a customer data enrichment request using a Gen AI service. Cost per Gen AI call spikes 4 times during peak hours. AI monitoring system detects the surge and decides, route enrichment through an alternate cheaper data provider, queue non-urgent requests for off-peak windows, or allow urgent ones through, but compress token context. How do you architect such adaptive, cost-aware integration? Wrong answer, use scheduled flows or batch jobs. Correct answer, use AI-driven cost strategy plus real-time routing engine plus policy-based throttling.
Context and challenge.
1. Cost risk, Gen AI token burn during loops. 2. Cost risk, peak traffic cloud compute surge fees. 3. Cost risk, expensive API calls triggered unnecessarily. 4. Cost risk, high-cost marketplace endpoints, finance, identity verification. 5. Success criteria, AI observes cost and usage patterns. 6. Success criteria, integration system chooses routing path. 7. Success criteria, non-critical jobs postponed automatically. 8. Success criteria, human override for emergency processing.
The interview question.
How would you architect an integration that dynamically switches routes or delays execution based on real-time cost signals or API token consumption? Think, load-aware decisions, cost multipliers, AI budget policy engine.
Integration strategy, cost-aware routing graph.
1. Cost profiling engine, tracks cost for each API/Gen AI endpoint. 2. AI decision engine, classifies workload into urgent, normal, deferrable. 3. Routing logic, urgent to execute on best available route. 4. Routing logic, normal to choose lowest cost provider. 5. Routing logic, deferrable to queue for off-peak window. 6. Token optimization layer, trim prompt context automatically for Gen AI. 7. Budget guardrail, blocks or reroutes once cost threshold exceeded. Here is the Java implementation of AI-driven cost-based routing. Disclaimer, always test code in a non-production environment. The first check is urgency. If the transaction is business critical, for example, live customer checkout, we bypass cost checks entirely. Performance and availability always trump cost for urgent workloads. For non-urgent work, we check the current market rate. If the API cost or compute load is surging, peak threshold, we defer the workload to a queue, waiting for the price to drop. Here is the Apex implementation applying cost-based throttling. Disclaimer, always test code in a non-production environment. The dispatcher receives a cost index, a normalized score of current expense. If the index is high, 0.80, we push the record to a deferred queue immediately, avoiding the expensive callout. Only when the cost index is acceptable do we allow the direct synchronous call. This simple logic prevents budget blowouts during cloud surge pricing events.
Trade-off evaluation.
1. Saves cost dynamically. 2. Use case-aware prioritization. 3. Supports hybrid AI plus rule-driven logic. 4. Prevents unexpected billing spikes. 5. Needs careful governance to avoid delaying critical actions. 6. Solution, solve with urgency tagging and override logic.
Risk and mitigation.
1. Delays affecting business timelines, use tier-based urgency. 2. AI misclassification, human override panel. 3. Overuse of alternate providers, cost-quality balance scoring. 4. Excessive queuing, enforce aging policy, max delay time.
The interview-ready answer.
I would architect a cost-aware routing engine that monitors real-time API cost, token burn, and platform pricing. The engine classifies workloads into urgent, normal, or deferrable. Urgent tasks run immediately, while normal tasks pick the cheapest provider. Deferrable tasks move to off-peak windows. If AI cost increases, the system auto-switches to alternative routes or reduces context size. Budget guardrails block excessive usage and generate alerts. This ensures financial efficiency without compromising business delivery.
Architect-level enhancements.
1. Multi-provider price benchmarking, Azure versus GCP versus AWS. 2. Predictive cooling windows, based on historical cost spikes. 3. Cost-based circuit breaker. 4. Auto-prompt trimming for Gen AI to reduce tokens. 5. Carbon-aware routing, future ESG requirement.
Your turn, Section 5 Scenario 8.
How would you ensure that urgent workloads bypass cost throttling safely without blowing the integration budget? Comment using this format, Section 5 Scenario 8, your answer. We've optimized for cost, now let's optimize for intelligence plus human governance. Next, we design hybrid orchestration, AI decides, humans validate at key checkpoints. Next, Scenario 9, hybrid orchestration, AI plus human review.
Scenario transition.
We just built cost-aware routing where AI decides how and when integrations run. But enterprises cannot fully hand over high-stakes decisions to AI. Especially in sectors like finance, healthcare, defense, and public sector compliance. Some decisions must be human-reviewed. This scenario tests if you can engineer an architecture where AI decides 80% of the path, and humans validate the critical 20%.
Scenario 9, hybrid orchestration, AI plus human review.
Architecting AI-driven workflows that include human intervention at strategic decision gates.
The scenario.
AI analyzes customer behavior and recommends a custom pricing offer. If AI confidence greater than 90%, system is allowed to auto-apply. If between 60 to 90%, it requires a sales manager approval. If less than 60%, action is blocked and escalated for manual investigation. How do you design this human-in-the-loop architecture so AI drives decisions but humans retain strategic control? Wrong answer, send approval emails. Correct answer, architect a multi-layer orchestration engine with decision tiers, human gates, and audit lineage.
Context and challenge.
1. AI responsibilities, generate recommendations, determine confidence level, suggest best route. 2. Human responsibilities, validate ambiguous decisions, overrule incorrect AI logic, provide rationale for override. 3. Goal, keep AI efficient. 4. Goal, avoid unnecessary human delays. 5. Goal, ensure legal and strategic safety. 6. Goal, provide traceable rationale.
The interview question.
How would you architect a workflow where AI automates decisions but human reviewers handle high-impact or risky branches? Think, confidence thresholds, business rule filters, explainability, override capture.
Integration strategy, hybrid governance flow.
1. AI confidence and risk classification, high confidence to auto-approve, MED confidence to human review queue, low confidence to block plus escalate. 2. Stage-based processing, decision stage to action stage to human gate stage. 3. Human gate workflow, approver sees AI recommendation plus explanation, must confirm or override, reason captured as compliance metadata. 4. Distributed orchestration, Salesforce Flow or Apex for decision routing, external workflow engine for complex chains. 5. Full AI lineage logging, include model version, input signature, confidence, and human override reason. Here is the Apex implementation of hybrid AI or human approval gate. Disclaimer, always test code in a non-production environment. For the happy path, where AI is extremely confident and risk is low, we enable straight-through processing. This handles the bulk of the volume instantly. When the AI is unsure, it does not guess. It creates a task for a human manager. Crucially, it provides the context so the manager is not starting from scratch. Here is the Java implementation for orchestration engine routing rules. Disclaimer, always test code in a non-production environment. The orchestration engine enforces the safety net. If confidence drops below 60%, it routes to block and escalate, ensuring that low-quality AI predictions never impact the business without manual oversight.
Trade-off evaluation.
1. High automation, reduced manual workload. 2. Human safety gates, reduced compliance risk. 3. Clear split, AI executes, humans validate nuance. 4. Traceability supports audits. 5. Need to avoid delays, timebox human review windows. 6. Escalation logic ensures SLA compliance.
Risk and mitigation.
1. Bottleneck from too many human reviews, fine-tune thresholds. 2. Reviewer bias affects decisions, require justification. 3. AI overconfidence, validate with periodic recalibration. 4. No record of override, mandatory override metadata.
The interview-ready answer.
I'd create a hybrid orchestration model where AI classifies decisions by confidence and risk. High confidence, low-risk tasks execute automatically. Median confidence tasks trigger a human review gate, where managers review the AI rationale before approving or overriding. Low confidence or high-risk tasks get blocked until compliance reviews them. Every decision is logged with model version, confidence, and human comments. This preserves automation speed while ensuring strategic and regulatory control.
Architect-level enhancements.
1. Dynamic routing based on reviewer performance metrics. 2. Auto-escalation if review exceeds SLA. 3. Confidence decay for outdated AI models. 4. Reviewer-guided reinforcement learning. 5. Multi-level approval routing based on deal or risk size.
Your turn, Section 5 Scenario 9.
How would you architect hybrid orchestration to handle multi-step approvals where AI may approve Step 1, but Step 2 requires compliance review, and Step 3 requires executive sign-off? Comment using this format, Section 5 Scenario 9, your answer. Now we have hybrid orchestration. But can AI orchestrate customer journeys before humans even intervene? The next scenario completes Section 5, and the entire Integration Mastery series. Next, Scenario 10, AI-charged customer journey triggers, predictive activation before user action.
Scenario transition.
So far, AI has helped us automate workflows, route decisions, evaluate risk, heal systems, and optimize cost. But in 2026 plus architectures, AI doesn't just react, it anticipates customer behavior and triggers journeys proactively. Think about a customer likely to churn before contacting support, or a buying signal emerging 3 days before a sales rep notices. This scenario tests whether you can architect AI-driven predictive journeys across channels, without overwhelming users or violating compliance.
Scenario 10, AI-charged customer journey triggers.
Predictive activation. AI triggers engagement before the customer takes action.
The scenario.
Data Cloud detects behavioral changes indicating a customer is 85% likely to downgrade. AI recommends triggering a proactive engagement path, customer success outreach, personalized retention content, or a one-time service enhancement. But the system must not trigger journeys too often, overmessage regulated customers, or interfere with active support cases. How do you architect this? Wrong answer, trigger journey builder when score threshold. Correct answer, use a predictive, guardrail-driven activation engine with AI plus rules plus anti-fatigue logic.
Context and challenge.
1. Data sources, usage patterns, data cloud, marketing signals, support case sentiment, billing or renewal lifecycle. 2. Challenge, limit repetitive triggers, journey fatigue. 3. Challenge, avoid collisions with other journeys. 4. Challenge, provide explainability for each trigger. 5. Challenge, maintain compliance for restricted segments. 6. Challenge, ensure AI predictions don't over-automate journeys.
The interview question.
How do you design predictive journey triggers powered by AI, while enforcing guardrails, explainability, and strict activation limits across multiple systems? Think, journey governance, AI confidence, orchestration layering, cooldown windows.
Integration strategy. Predictive Journey Control Plane.
1. AI signal aggregation, consolidates churn risk, buying intent, usage drops to generate trigger score plus confidence. 2. Multi-layer activation guardrails, frequency cap, 1 per 15 days, conflict guard, case open to block, compliance lock. 3. Predictive journey execution router, high intent to auto-trigger, moderate to trigger but require approval, low to store insight only. 4. Journey outcome feedback loop, success or failure feeds back to model improvement. Here is the Apex implementation for AI-triggered journey activation with guardrails. Disclaimer: always test code in a non-production environment. Before acting on any AI signal, we check the fatigue rules. If this customer was engaged in the last 15 days, we stop immediately. This prevents journey fatigue and ensures our high-value outreach is not perceived as spam. Only if the AI is highly confident, greater than 85%, and the intent score is strong, 0.80, do we auto-trigger the journey. We immediately update the timestamp to reset the cooldown clock. Here is the Java implementation for AI-driven journey routing decisions. Disclaimer: always test code in a non-production environment. The middleware router reinforces the tiering strategy. Medium confidence signals are routed to a human work queue for review. Low confidence signals are simply logged as insights, enriching the customer profile without interrupting operations.
Trade-off evaluation.
1. Protects customers from over-automation. 2. Predictive journeys create proactive CX. 3. Human review ensures nuance for mid-confidence signals. 4. Compliance rules prevent risky triggers. 5. Over-triggering journeys, solved via frequency capping plus guardrails. 6. Balanced AI plus business rules, safest architecture.
Risk and mitigation.
1. Journey collision, use journey arbitration engine. 2. Over-messaging, anti-fatigue limit plus cooldown. 3. Wrong AI prediction, approval required mid-range threshold. 4. Regulatory violation, segment-based compliance lock. 5. Feedback loop missing, incorporate journey outcomes into AI model.
The interview-ready answer.
I'd architect predictive journey activation using a multi-layer governance model where AI provides the intent score and confidence, but activation respects guardrails like frequency limits, compliance restrictions, journey collisions, and conflict windows. High confidence signals auto-trigger journeys, medium confidence signals go to human review, and low confidence signals only update insights. Every trigger is logged for explainability and tuning. This enables proactive customer engagement without automation risk.
Architect-level enhancements.
1. Multi-journey priority resolution engine. 2. AI-led trigger cooldown prediction. 3. Unified customer fatigue index. 4. Time of day and lifecycle-aware journey timing. 5. Feedback learning loop, model sees outcomes and adjusts trigger patterns.
Your turn, Section 5 Scenario 10.
How would you prevent multiple AI-triggered journeys from competing when a customer has simultaneous signals, for example, high upsell intent plus medium churn risk? Comment using this format, Section 5 Scenario 10, your answer.
Section 5 Wrap-up.
Section 5 wasn't just about solving integration challenges, it was about designing the digital enterprise of 2026 and beyond. You've now built systems that are autonomous, predictive, self-healing, risk-aware, cost-optimized, compliant, and AI-orchestrated. This level of architecture is rare. This is the difference between being a senior architect and being the architect companies trust with billion-dollar digital transformation programs.
What's next?
In the next section, we pivot from what to design to how interviewers test your thinking across the full spectrum of architectural challenges. You'll learn how to handle live design problems, what-if breakdowns, risk mitigation prompts, trade-off scenarios, failover logic questions, and strategic future-proofing challenges. Section 6 reveals the underlying psychology and frameworks behind world-class interview performance. Master it, and you won't just answer questions, you'll control the interview.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Salesforce jobs interviews like Salesforce LWC developer jobs, Salesforce technical architect jobs, Salesforce Solution Architect jobs, Salesforce Service Cloud Consultant or Specialist jobs, Salesforce Test Engineer jobs, Salesforce DevOps Engineer jobs, Salesforce Marketing Cloud Developer or Consultant or Specialist jobs, Salesforce Admin jobs, Salesforce Developer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based interview questions and answers, real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Section 6, Interview Scenario Types.
How top tech companies evaluate Salesforce and enterprise integration architects in 2026 plus. You now understand every major integration scenario, from legacy systems to AI-governed architectures. But interviewers don't simply ask questions. They test how you think under constraints, pressure, and evolving context. This final section reveals the spectrum of scenario types recruiters use, and how elite architects respond to each.
Real-world evaluation.
1. The types that FANG, Fortune 100, Big Four consultancies, and CXO-level panels use to evaluate real-world readiness. 2. The types that separate senior candidates from enterprise architects. 3. Mastering these scenario categories gives you the mental model to dominate any unexpected question.
The 6 major scenario types.
1. Live problem solving, design architecture for real-time sync of 30M records under 2 seconds. 2. What if breakdown, what if ERP is down mid-transaction. 3. Risk mitigation, which patterns prevent replay attacks. 4. Trade-off challenge, when not to use platform events. 5. Failover logic, AI flow breaks, what do you do? 6. Strategic thinking, how do you future-proof this ETL for 2027?
Section 6 Introduction.
This section will teach you how to think like an interviewer, and how to respond as a world-class architect. Master these 6 scenario types, and you can answer any Salesforce or integration question thrown at you, regardless of domain, system, or technology.
A note on code syntax.
In this series, we use architectural pseudocode. While the syntax resembles Apex or Java, it is designed to demonstrate logic, data flow, and resilience patterns rather than compile-ready syntax. As architects, we focus on system behavior, allowing you to apply these logic patterns to Apex, Java, MuleSoft, or any enterprise integration layer.
Scenario transition.
Everything we've done so far was about designing high-value architectures. But interviews test something deeper, your ability to think clearly under pressure, structure chaos into clarity, and design a viable solution live with incomplete information. This is scenario type 1, live problem solving. These scenarios are time-bound, intentionally ambiguous, and your first 60 seconds matter more than your final answer.
Scenario type 1, live problem solving.
Design an architecture for real-time sync of 30M records under 2 seconds. We now break down how an elite architect responds.
What interviewers are really testing.
1. Frame the problem before solving it. 2. Identify constraints, technical, legal, operational. 3. Select patterns intentionally. 4. Explain trade-offs. 5. Avoid perfection, aim for feasibility. 6. Drive the conversation instead of reacting.
Correct response structure.
1. Clarify requirements. 2. Identify constraints. 3. Propose architecture options. 4. Choose the best fit solution. 5. Explain trade-offs and risks.
Step 1. Clarify requirements.
Before designing, I want to clarify, are the 30M records changed at once or continuously? Is the 2-second requirement end-to-end or per record batch? Is data consistency strict or eventual? Can we use streaming platforms like Kafka or Kinesis?
Step 2. Identify constraints.
1. API limits. 2. Daily CDC limits. 3. Backpressure capacity. 4. Near real-time versus real-time definition. 5. Ordering guarantees. 6. Idempotency requirements. 7. Regional compliance, if cross-border.
Step 3. Propose architecture.
1. Capture changes using CDC or event mesh. 2. Push into Kafka or Kinesis stream. 3. Partition records by entity key for parallelism. 4. Use microbatch processors, 100 to 500 records. 5. Write to target using bulk API v2 in parallel. 6. Apply idempotency stamp to avoid duplicates. 7. Monitor latency plus throughput with autoscaling. Here is the Java implementation for microbatch streaming processor. Disclaimer: always test code in a non-production environment. We enforce strict microbatching. Even if the stream sends 5,000 records, we slice them into manageable chunks of 500. This ensures that the downstream bulk API ingest is optimal and does not time out. We submit asynchronously. The processor does not wait for the Salesforce commit. It fires the batch and moves to the next chunk immediately, maximizing throughput. Here is the Apex implementation of idempotency check before ingest. Disclaimer: always test code in a non-production environment. In a high-speed streaming architecture, duplicate delivery is possible. We protect the database by checking a sync log using the external ID before processing. If it exists, we skip it, ensuring data integrity.
Trade-off thinking.
1. Microbatching ensures high throughput. 2. Streaming prevents API overload. 3. Idempotency avoids corruption. 4. Parallelization reduces latency. 5. Requires event streaming infrastructure. 6. Achievable under 2 seconds end-to-end for each micropipeline.
Risk and mitigation.
1. Latency spike, auto-scaling via partition count. 2. Duplicate events, idempotency log. 3. Large payload, dynamic microbatching. 4. Ordering issues, partition by primary key. 5. Failover, replay logs with offset tracking.
Interview-ready answer summary.
I design a streaming-driven sync with CDC to Kafka, microbatch processors, and bulk API v2. Idempotency ensures correctness. Partitioning ensures parallel low-latency sync. Autoscaling ensures load stability. This architecture consistently achieves real-time throughput under 2 seconds. This answer blows away interviewers because it is structured, feasible, and demonstrates understanding of enterprise complexity.
Your turn, Section 6 Scenario Type 1.
If the requirement changed so that data consistency must be strict, no eventual consistency allowed, how would you modify the architecture? Answer in this format, Section 6 Scenario Type 1, your answer. Now that you've mastered live problem solving, let's move to something interviewers use to break weak candidates instantly, the what-if breakdown scenario. This is where your architecture gets stress tested. Next, Scenario Type 2, What-If Breakdown.
Scenario transition.
Live problem-solving tests your ability to design. But what-if breakdown tests your ability to defend, adapt, and evolve your design. Interviewers introduce sudden failures like, what if ERP is down, what if the third-party API throttles you, what if the payload doubles, or what if the AI model confidence drops. This scenario tells the interviewer whether your architecture is robust, or surface level. You're not just giving an answer, you're proving architectural resilience thinking.
Scenario Type 2, What-If Breakdown.
The interviewer breaks your architecture mid-flow to test resilience, depth, and adaptability.
The scenario prompt.
What if your ERP is down mid-transaction? Most candidates panic here. They want to see if you understand system behavior under partial failure, idempotency, retry patterns, distributed transaction control, and graceful degradation patterns.
Correct response strategy, the architect's way.
1. Identify the failure mode. 2. Contain the blast radius. 3. Maintain transaction consistency. 4. Provide recovery and business continuity.
Step 1 and 2. Identify failure and contain blast radius.
1. Failure mode, no synchronous writes possible. 2. Failure mode, no guaranteed real-time acknowledgement. 3. Failure mode, business system, Salesforce, must not corrupt data. 4. Containment, switch from sync to async pattern. 5. Containment, queue requests in a durable event store. 6. Containment, use circuit breaker to stop repeated failures.
Step 3 and 4, maintain consistency and provide continuity.
1. Consistency, introduce transaction tokens or idempotency keys. 2. Consistency, if ERP eventually comes back to replay only once. 3. Consistency, temporary state stored in Salesforce, pending sync. 4. Continuity, create pending ERP sync banner for sales or service users. 5. Continuity, allow non-financial updates but block financial ones. 6. Continuity, auto-resume once ERP is restored. Here is the Java implementation of ERP down detection plus failover queuing. Disclaimer, always test code in a non-production environment. This is the circuit breaker pattern in action. Before attempting the transaction, we check the health status. If the ERP is down, we immediately divert the transaction to a failover queue with an idempotency key, preventing data loss without crashing the thread. Here is the Apex implementation of marking Salesforce record for async ERP replay. Disclaimer, always test code in a non-production environment. On the Salesforce side, we do not fail the user operation. Instead, we mark the record status as pending sync. This allows the business to continue working while the system handles the technical outage in the background.
Trade-off thinking.
1. Async queue prevents losing transactions. 2. Circuit breaker prevents repeated failures. 3. Idempotency ensures no double posting. 4. State flags keep Salesforce business safe. 5. Longer latency, acceptable during ERP downtime. 6. Business remains operational.
Risk and mitigation.
1. Queue overflow, add autoscaling plus partitioning. 2. Long downtime, business escalation path. 3. Data mismatch, replay reconciliation job. 4. Missed events, durable event store with offset tracking.
Interview-ready answer summary.
If ERP is down, I shift from synchronous posting to a queued async model using durable events. A circuit breaker stops further ERP calls, and transactions are marked pending sync. Once ERP is restored, the system replays only unprocessed transactions using idempotency keys. Salesforce users continue working but financial posting is deferred. This protects consistency, prevents duplicates, and maintains business continuity.
Your turn, Section 6 Scenario Type 2.
What if the ERP comes back online but returns stale cached data for 2 minutes before real recovery? How would your architecture detect and avoid corruption? Answer using this format, Section 6 Scenario Type 2, your answer. You've now seen how to defend your architecture mid-crisis. But the next interview scenario type is even more important. How do you protect your system from threats before they happen? Welcome to the risk mitigation scenario. Next, scenario type 3, risk mitigation, which patterns prevent replay attacks.
Scenario transition.
Live problem solving shows how you design. What if breakdown shows how you adapt. But risk mitigation shows whether you can protect the enterprise. Interviewers want to know, do you understand integration vulnerabilities? Do you apply patterns like idempotency, signatures, circuit breakers, encryption? A risk mitigation question instantly reveals the difference between a developer and an architect. A developer thinks about success paths. An architect thinks about failure, threat, and exploitation paths.
Scenario type 3, risk mitigation.
Designing patterns that prevent threats, corruption, or operational failure before they occur.
The scenario prompt.
Which patterns prevent replay attacks? Replay attacks occur when an attacker, or system bug, resends a previously valid transaction to trick systems into double execution. This is extremely common in integration flows.
What interviewers are testing?
1. Cryptographic signatures. 2. Nonce plus timestamp validation. 3. Idempotency. 4. Windowed acceptance periods. 5. Event sequencing. 6. Deduplication stores. 7. API level versus platform level security.
Answer framework, 3 layers.
1. Layer 1, detect replay attempts. 2. Layer 2, block or neutralize them. 3. Layer 3, maintain system integrity after blocking.
Layer 1, detect replay attempts.
1. Nonce, unique random token per request. 2. Timestamp window, for example, reject requests older than 5 minutes. 3. Signature mismatch, HMAC-based integrity. 4. Sequence number violation, expected versus received index. 5. Duplicate external IDs. 6. Hash-based request fingerprinting.
Layer 2, block or neutralize.
1. Idempotency keys, only first execution allowed. 2. Transaction logs, detect duplicates. 3. Deduplication record store. 4. Event bus exactly once semantics. 5. Circuit breaker when duplicates exceed threshold. 6. Reject requests outside acceptance window.
Layer 3, maintain system integrity.
1. Keep audit logs for security team. 2. Alert suspicious replay behavior. 3. Queue isolation, move suspicious events into quarantine. 4. Token invalidation if breach suspected. Here is the Java implementation of a replay prevention signature check. Disclaimer, always test code in a non-production environment. First, we verify integrity. We recalculate the HMAC signature of the payload. If it does not match what the sender claims, the message has been tampered with or is fake. We reject it immediately. Next, we check the nonce, number used once. If we have seen this random token before, it is a replay attack. If not, we add it to the store to prevent future replays. Finally, we check the timestamp. We only accept requests generated within the last 5 minutes. This limits the attack window and prevents attackers from resending old valid requests hours later. Here is the Apex implementation for idempotency-based replay blocking. Disclaimer, always test code in a non-production environment. In Salesforce, we rely on the database. Before executing any logic, we query the execution log using the unique idempotency key provided by the external system. If a record exists, we know this transaction was already processed. If it is new, we insert the log record immediately. This claims the key, ensuring that any subsequent attempts, even milliseconds later, will fail the check, guaranteeing exactly once processing.
Trade-off evaluation.
1. Strong protection against duplicates. 2. Zero corruption with idempotent architecture. 3. Works across multi-cloud or multi-system flows. 4. Timestamp plus nonce ensures secure request origin. 5. Requires storage for dedupe and nonce tracking. 6. Necessary for regulated and financial systems.
Risk and mitigation.
1. Clock drift, use tolerant time windows. 2. Stolen nonce, single-use plus expiration prevents reuse. 3. Replay at event level, fingerprinting plus sequence numbers. 4. Man in the middle, HMAC plus TLS enforcement. 5. High volume nonce store, rolling cleanup.
Interview-ready answer summary.
I prevent replay attacks using a layered approach. At the API layer, I use HMAC signatures to validate message integrity, nonce to ensure one-time execution, and timestamp windows to reject old payloads. At the integration layer, I use idempotency keys and deduplication logs to prevent duplicate execution. If replay attempts occur, events are quarantined and a security audit is logged. This ensures replay attacks cannot corrupt data or trigger repeated financial transactions.
Your turn, Section 6 Scenario Type 3.
How would you prevent replay attacks in event-driven architectures where multiple microservices consume the same platform event or Kafka topic? Answer in this format, Section 6 Scenario Type 3, your answer. Risk mitigation shows whether you can protect systems. But the next scenario type reveals another dimension: can you choose between multiple valid solutions, and justify your choice? Next, Scenario Type 4, Trade-off Challenge, when not to use platform events.
Scenario transition.
Risk mitigation shows your defensive thinking. Trade-off challenges test your judgment. Not every powerful tool belongs in every architecture, and senior architects must know when to avoid over-engineering. Interviewers deliberately pick popular tools or patterns and ask, when should you not use platform events, when should you avoid CDC, or when should GraphQL be harmful? They want to know whether you understand capabilities versus limitations, and benefit versus cost. Good architects use tools effectively. Great architects know when to avoid them.
Scenario Type 4, Trade-off Challenge.
When interviewers test whether you understand when not to use a tool or pattern.
The scenario prompt.
When should you not use platform events? This sounds simple, but it's a deep judgment test.
What interviewers are really testing?
1. Pattern literacy. 2. Throughput awareness. 3. Failure behavior understanding. 4. Business impact reasoning. 5. Scalability versus durability logic. 6. Backpressure strategy. 7. Total cost of operation.
Correct answer structure.
1. Identify what platform events are. 2. Identify what platform events are not. 3. Provide scenarios where they break down. 4. Offer alternatives plus trade-offs.
Step 1. What platform events are?
1. Low latency pub sub messaging. 2. Event-driven orchestrations. 3. Reactive workflows. 4. Multi-system async notifications.
Step 2. What platform events are not?
1. Guaranteed durable retention. 2. Long-term replay. 3. High-throughput ingestion. 4. Ordered, partitioned parallelism. 5. Complex event transformations. 6. Cross-cloud transactional delivery.
Step 3. When not to use platform events, the goldmine list.
1. When you need durable event retention, Kafka equals months or years, PE equals hours. 2. When volume greater than 200K events or day consistently, risk of limits. 3. When ordering matters, PE doesn't guarantee strict ordering. 4. When replayability is critical, CDC better for ledger-style events. 5. When events must survive org deployment changes. 6. When consumers must reprocess historical events. 7. When you need multi-tenant cross-org message routing. 8. When messages exceed 5 million/day, limits plus backpressure. 9. When integration must recover from outages gracefully, Kafka or SQS safer.
Step 4. Provide alternatives.
1. Use CDC for change-based sync with replay. 2. Use Kafka or PubSub for durable, replayable events. 3. Use Streaming API for finer-grained selective subscriptions. 4. Use Direct REST for low-volume deterministic updates. Here is the Java implementation illustrating backpressure detection. Disclaimer: always test code in a non-production environment. Before publishing, we check the daily limit. This simple check prevents the system from hitting the hard limits of the platform event bus, which would cause silent failures or dropped messages. Here is the Apex example enforcing event fallback logic. Disclaimer: always test code in a non-production environment. If we are approaching the daily limit, for example, 180K events, we dynamically switch strategies. Instead of publishing another event, we fail over to a direct REST call or a queued object, ensuring the data still moves even when the event bus is saturated.
Trade-off evaluation.
1. Platform events, great for low-latency reactive flows. 2. Not great for durability, recovery, or high-throughput ingestion. 3. Characteristics, light, flexible, but limit-bound. 4. External streaming platforms, better for durability plus parallelism.
Risk and mitigation.
1. Event loss on consumption failure, use durable queue fallback. 2. Too many retries flooding PE, circuit breaker. 3. Consumer unable to keep up, throttle and persist events outside SF.
Interview-ready answer summary.
Platform events are excellent for real-time PubSub inside Salesforce, but I avoid them when durability, high-volume throughput, strict ordering, or long-term replay is required. In such cases, Kafka or PubSub are better fit because platform events are limit-bound and not designed for large-scale durable event processing. This answer is principal architect level and demonstrates mature pattern selection.
Your turn, Section 6 Scenario Type 4.
When would you avoid using Change Data Capture, CDC, even though it's extremely powerful? Reply using Section 6 Scenario Type 4, your answer. Trade-off challenges test judgment. But the next scenario type tests your ability to manage system degradation and continuity under pressure. This is where architecture meets reliability engineering. Next, Scenario Type 5, Failover Logic, AI Flow Breaks, what do you do?
Scenario transition.
Trade-off questions test your judgment. Failover logic questions test your resilience engineering mindset, the ability to ensure the business keeps functioning even when key systems fail. Modern integrations rely heavily on AI inference services, external cloud APIs, and microservices. But these systems have failure modes, latency spikes, AI hallucinations, throttling, or outages. The interviewer wants to see if you can stabilize the system before it fails catastrophically.
Scenario Type 5, Failover Logic.
What do you do when a critical dependency breaks mid-operation, especially AI-driven flows?
The scenario prompt.
Your AI flow breaks, what do you do? This vague scenario is intentionally designed to see how deeply you understand failure states of AI-enabled integrations. Most candidates answer, retry the AI call or call an alternate model. These are surface level. Top architects consider confidence, accuracy, trust, latency, model drift, and downstream impact.
What interviewers are really testing?
1. Detect AI failure early. 2. Switch to fallback logic. 3. Maintain transaction consistency. 4. Avoid propagating incorrect AI output. 5. Offer a degraded but safe experience. 6. Design predictive failover, not reactive.
Correct answer structure.
1. Detect failure, technical plus behavioral indicators. 2. Switch to safe fallback path. 3. Prevent propagation of corrupted decisions. 4. Restore AI path using stabilization logic.
Step 1. Detect AI failure.
1. Technical failures, timeout, 5xx error, rate limit exceeded, model unavailable. 2. Behavioral failures, AI-specific confidence threshold. 3. Behavioral failures, output violates schema. 4. Behavioral failures, output violates policy/guardrails. 5. Behavioral failures, drift detected in predictions.
Step 2. Switch to safe fallback path.
1. Use rule-based engine instead of AI. 2. Trigger human review. 3. Use cached last known good inference. 4. Defer action until AI stabilizes. 5. Gracefully degrade feature, for example, insights unavailable.
Step 3. Prevent propagation.
1. Block downstream integration. 2. Mark record as AI review required. 3. Log AI failure context, model version, input hash. 4. Notify business owners if risky.
Step 4. Restore the AI path.
1. Reprocess queued requests. 2. Validate output confidence. 3. Compare with rule-based prediction. 4. Update drift monitoring metrics. Here is the Java implementation of AI failover detection plus fallback. Disclaimer: always test code in a non-production environment. This captures both failure modes. We check for technical errors, 500/timeouts, and behavioral issues, low confidence. If either occurs, we do not crash, we queue the request for later analysis and immediately return a deterministic rule engine decision to keep the business moving. Here is the apex logic applying degraded experience when AI fails. Disclaimer: always test code in a non-production environment. Transparency is key. We explicitly tag the record as being in fallback mode. This informs the user that the insights they are seeing are rule-based, not AI-based, managing expectations and maintaining trust.
Trade-off evaluation.
1. Ensures business continuity. 2. Prevents AI misinformation from propagating. 3. Human-in-the-loop acts as final safety net. 4. Drift plus confidence monitoring prevents hidden failures. 5. Adds operational complexity. 6. Necessary in regulated or mission-critical domains.
Risk and mitigation.
1. AI output looks valid but is wrong, require confidence plus schema validation. 2. AI unavailable, degrade gracefully plus use cached inference. 3. Queue overflow, implement backpressure plus limits. 4. Human review delays, SLA-based escalation. 5. Failover flip-flop, cooldown window.
Interview-ready answer summary.
If the AI flow breaks, I detect both technical and behavioral failures using confidence thresholds, schema validation, and drift checks. On failure, I trigger fallback logic, rule-based decisions, cached outputs, or human review depending on criticality. I block downstream execution to prevent propagation of incorrect AI decisions. Once AI stabilizes, queued transactions are reprocessed with confidence gating. This ensures continuity, correctness, and safety in AI-driven integrations.
Your turn, Section 6 Scenario Type 5.
If the AI service is partially available, responding intermittently, how would you design a stabilization mechanism to avoid thrashing, flip-flopping between AI and fallback modes? Answer using Section 6 Scenario Type 5, your answer. Failover logic tests resilience. But there is one final scenario type, the one that distinguishes senior architects from enterprise strategists, the ability to think years ahead. Next, Scenario Type 6, Strategic Thinking. How do you future-proof this ETL for 2027?
Scenario transition.
Failover logic tested resilience under failure. But strategic thinking tests your ability to architect for the future, for systems, teams, and regulations that may not even exist yet. This is the scenario type used in enterprise architect panels, CTO interviews, and multi-year digital modernization initiatives.
Scenario Type 6, Strategic Thinking.
How do you design systems that survive scale, industry change, compliance evolution, and technology disruption?
The scenario prompt.
How do you future-proof this ETL for 2027? This sounds simple, but it requires system-level foresight. Most candidates answer, use APIs and keep logic modular, or keep the system scalable. These are generic and weak. A real architect answers like someone planning 3 to 5 years out.
What interviewers are really testing?
1. Long-term thinking. 2. Architecture evolution patterns. 3. Cloud neutrality. 4. Compliance foresight. 5. AI integration readiness. 6. Scaling beyond current limits. 7. Minimizing future migration cost. 8. Governance maturity.
Correct strategic thinking framework.
A high-level strategic answer must address these 5 pillars: scalability, extensibility, compliance evolution, AI readiness, and cost and operational sustainability.
Detailed pillar strategy.
1. Scalability, switch between batch, micro-batch, and streaming depending on load. 2. Extensibility, use metadata-driven mapping and pluggable transformers. 3. Compliance, log every ETL transformation to a lineage tracker for future audits. 4. AI readiness, ensure ETL is model pluggable and drift aware. 5. Cost sustainability, cost-aware routing and auto-scaling with constraints. Here is the Java implementation of a pluggable AI-driven transformation step. Disclaimer: always test code in a non-production environment. This interface is the core of future-proofing. It defines a contract for transformation without locking us into a specific implementation. This is the strategy pattern in action. Today, we might use a rule-based strategy. Tomorrow, when AI is ready, we simply swap in this AI-powered strategy. The rest of the ETL pipeline does not change. This represents true adaptability. Here is the Apex implementation supporting metadata-driven ETL mapping. Disclaimer: always test code in a non-production environment. Instead of hard-coding field maps, we fetch them from a custom metadata configuration. This allows business rules to evolve and fields to change without a single line of code deployment.
Trade-off evaluation.
1. Future-proof logic, stable for years. 2. Metadata-driven mapping, adaptable to change. 3. AI-ready, leverages predictive ETL. 4. Cost-aware, affordable long-term. 5. Compliance-ready, avoids retrofitting later. 6. Slightly more complex upfront, massive long-term ROI.
Risk and mitigation.
1. Over-engineering, start with modular baseline, grow gradually. 2. Model drift, monitor and retrain periodically. 3. Changing compliance landscape, dynamic policy engine. 4. Multi-cloud inconsistencies, use vendor-neutral patterns.
Interview-ready answer summary.
To future-proof an ETL for 2027, I would design around 5 pillars: scalability, extensibility, compliance evolution, AI readiness, and cost sustainability. This means dynamic ETL modes, batch or streaming, metadata-driven mappings, lineage tracking for compliance, pluggable AI-based transformations, cost-aware scheduling, and modular pipeline stages. This ensures the ETL remains adaptable, compliant, and efficient as data volume, regulations, and AI capabilities evolve.
Your turn, Section 6 Scenario Type 6.
How would you future-proof an event-driven architecture so it remains relevant and scalable over the next 5 years? Reply using this format. Section 6 Scenario Type 6, your answer.
Section 6 Wrap-up.
You've reached the end of the interview mastery spectrum. You now know how to think, respond, adapt, and architect across every scenario interviewers use, from live problem-solving to strategic foresight.
The complete mental model.
1. Live problem-solving. 2. What-if breakdown. 3. Risk mitigation. 4. Trade-off challenge. 5. Failover logic. 6. Strategic thinking. With this framework, you are no longer guessing how to answer. You are controlling the interview. You are leading the conversation. You are demonstrating mastery, not memorization. This concludes Section 6. Now you are fully prepared to face any architectural interview scenario in 2026 and beyond.
The architect you become after this.
You've just completed one of the most advanced Salesforce and enterprise integration architecture series ever made on YouTube. Not a collection of tips. Not a list of recycled questions. But a roadmap, a transformation, built for the architects of 2026 and beyond. Over the last series, you didn't just learn patterns. You learned how to think like an architect.
Section 1 Legacy and Transformation.
You learned how to modernize the past without breaking stability, how to migrate monoliths, transform COBOL-driven processes, and handle batch orchestration with surgical precision.
Section 2 Core Enterprise Integration.
You explored the foundations of modern integration, APIs, events, streaming, middleware, OAuth governance, multi-cloud sync, contract negotiation, and the patterns that define enterprise-grade systems today.
Section 3 Complex Cloud and Enterprise Scenarios.
You went deeper than 99% of architects ever go: multi-org integration, SAP or Workday orchestration, migrating ERP to cloud, pricing complexity, distributed caching, multi-region conflict handling, and metadata consistency under scale.
Section 4 Regulated and Secure Architecture.
You stepped into the world where mistakes cost millions. Where data residency laws, HIPAA, AI auditability, and federated identity aren't buzzwords, they're the difference between compliance and catastrophe. You learned how to architect systems that can stand in front of regulators, auditors, and legal scrutiny.
Section 5 Future-Ready AI Architecture.
You entered the frontier where only next-generation architects operate: AI-triggered workflows, Gen AI decision layers, AI risk scoring, self-healing systems, cost-aware routing, composable enterprises, multi-cloud failover, and predictive journeys. You didn't just prepare for 2026, you built a skill set that will be relevant for the next decade.
Section 6 The Interview Scenario Spectrum.
1. Live problem solving. 2. What-if breakdown. 3. Risk mitigation. 4. Trade-off scenarios. 5. Failover logic. 6. Strategic foresight.
From reacting to leading.
You learned how to frame answers at a level that commands the room, the level where interviews stop feeling like evaluations and start feeling like technical leadership discussions.
What this series truly made you.
1. You can design architectures across clouds, domains, industries, and regulations. 2. You can defend your solutions under stress. 3. You can architect with AI, for AI, and around AI. 4. You can survive every failure mode, and design for ones that haven't happened yet. 5. You can speak in the language of CTOs, directors, and principal architects.
Shaping the next era.
This series didn't teach you answers. It taught you the frameworks to generate any answer. You're no longer reacting. You're no longer guessing. You're leading. If you've made it this far, you are not just learning Salesforce architecture. You are shaping the next era of enterprise systems.
The architects of the future.
The people who win the next decade aren't the ones who memorize tools. They are the ones who understand one. Patterns. 2. Resilience. 3. Governance. 4. Strategy. 5. And the courage to design boldly.
Your final call to action.
1. If this series elevated your thinking, comment the section and scenario that transformed you the most. 2. Share this series with one architect who needs this level of depth. 3. Subscribe, because the next series will go even further, into AI-driven enterprises, global scale systems, and architect leadership mastery. You are no longer preparing for interviews. You are preparing for leadership. Welcome to the next era of architects.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Salesforce jobs interviews like Salesforce LWC developer jobs, Salesforce technical architect jobs, Salesforce Solution Architect jobs, Salesforce Service Cloud Consultant or Specialist jobs, Salesforce Test Engineer jobs, Salesforce DevOps Engineer jobs, Salesforce Marketing Cloud Developer or Consultant or Specialist jobs, Salesforce Admin jobs, Salesforce Developer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based interview questions and answers, real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years experienced candidates, and for 5 or above years experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.